for a distraction-free environment. Thank you.
honorable dignitaries, invited guests, officials from state and central government, officials from various industries, students, and officials of Cipet IPT Kochi. I am very delighted to invite you all to the industry interaction meet organized by Cipet IPT Kochi. We will start the program with the blessings of Almighty. I request everyone to rise for the prayer song.
ഹരിത സുന്ദര സന്നിധി തിരുനാഥനിന്റെ പ്രണാമം അരുണശോഭിതമാനിടെ അതിനാഥനിന്റെ പ്രണാമം ഹരിത സുന്ദര സന്നിധി തിരുനാഥനിന്റെ പ്രണാമം അരുണശോഭിതമാനിടെ അതിനാഥനിന്റെ പ്രണാമം പുലരിയുണരും യാമം മമനാഥനിന്റെ പ്രണാമം ഹരിത സുന്ദര സന്നിധി തിരുനാഥനിന്റെ പ്രണാമം അരുണശോഭിതവാനിടെ അതിനാഥനിന്റെ പ്രണാമം.
It's our esteemed pleasure to welcome our distinguished guests to this memorable event of the day. I invite Head Academics Manager Technical, Cipet IPT Kochi,
Respect, very warm good morning to 100% here. Respected Chief Guest, Sri P. Rajiv Sir, Honorable Minister for Law, Industries and Choir. Respected DG Sir in his absentia, distinguished Dean, External Linkage from Digital University, Professor Alex James, Guest of Honor Srimati Ambli Madam from Kinfra, Guest of Honor Sri Sunil, President, Kerala Plastic Manufacturer Association, distinguished professors and scientists, dignitaries, members from industry and associations, dear students, members from press and media, ladies and gentlemen. It is my profound pleasure to give presidential address on this August occasion of inauguration of Industry Interaction Meet being held as a part of International Conference Bpgc 2024. Cipet Kochi has been organizing every year the international conference on biopolymers, and this time this is an international event where we have 78 presentations and from 5 different countries. And Cipet has been training around 2,000 candidates, including entrepreneurs, for industry exposure training, and 300 candidates for placement-linked skill development program. And we are there tying up with HLL and Homeco for development of the packaging containers. And we are the certifying body for the compostable plastics. And it is happy to note that some more industries are coming forward for setting up biodegradable products in Kerala. And we are also certifying the same. And Cipet, and as a part of today's industry meet, we are also having signing an MOU with Indian Graphene IGIC engineering and products for technical assistance for graphene-based advanced polymer composite under Graphene Aurora program in combination with Digital University of Kerala. And I express my sincere thanks to Dynamic Dean Professor Alex James for taking it to the fast track on the same. On behalf of Cipet, I would like to congratulate Honorable Minister for great achievement for achieving top rank in for implementing ease of business norms for making Kerala proud. Cipet is indebted to Industries Department, sir, for our expansion, and we are looking for further expansion, sir. We seek your support again and again. And as far as the petrochemicals industries are concerned, it is having an average growth rate of 10%, and it is essential to have to diversify the refineries, not only the petrol, diesel, to another petrochemical products also, where BPCL is coming up with a polypropylene plant in Kochi. And there is a huge potential for the same, and we are conducting the industry meet for discussing the major possibilities of the investment in Kerala for technically diversifying the same into different other products. And with this, I conclude, and I request Honorable Minister for convening for the MOU exchange between IGIC and also Digital University of Kerala for graphene.
The lighted lamp is the symbol of auspiciousness and our culture. To mark the
Thank you very much to all the dignitaries. I request the Honorable Minister, Shri P. Rajiv, to address the gathering with a few words. Sir, please.
Dignitaries on and off the days. മലയാളികളല്ല കൂടുതലും തോന്നുന്നു അല്ലേ? മലയാളികളുണ്ട്. Then better to speak in English. Then today I have a very hectic schedule. That is why I would not like to take more time for my inaugural speech. Anyway, I would like to congratulate Cipet for organizing this conference, international conference on biopolymers and green composites. This is the 9th conference hosted by Cipet. I think I was here for some other conference. Last year also I was present for. At that time I think it is national conference. This time though it is enhanced as a international conference. That is why I am compelled to speak in English, otherwise Malayalam would be better. The government is trying to strengthen the connect in between higher education institutions and industrial establishment. That is one of the major focus area of the government for strengthening the ecosystem of the state. Digital University Professor Alex is here. He is seriously involving in this type of activities. We were together in UK to signing the MOU with universities like Stanford for graphene activities as a part of the delegation led by Honorable Chief Minister. 2 days back we have signed an MOU with Digital University and Kinfra for handing over the space for graphene Aurora project. We are in the forefront on this new emerging thing, wonderful material of the future, graphene. And one of the Kerala company has already manufactured graphene, Kumi, with collaboration of KUSAT and some foreign university. I think they are marketing it as the Grapheno. And we are trying to attract more investment to this sector. As Mr. In his welcome address, the director has mentioned, Kerala has improved its position in the ease of doing business. We were in the 20th position 3 years back in 2020 ranking. That means nobody was behind us at that time. Then we could improve our position to 15th. Then now it is number 1 in ease of doing business. The 2024 ranking process is already started. The first part, reforms part, is already finished. October 15th was the last day. We could finish more than 98% of reforms till today. But the major thing is this ranking is exclusively based on the feedback, 100% feedback. This time it has little changed, 70% objective and 30% objective and 70% subjective feedback. Earlier it is fully based on feedback of the investors. 2020 was actually, we could got a position on achiever category, but feedback was very poor. That is why we were in the aspirants category with the 15th rank. This time we got the berth in the top achiever category, and we are in the number 1 in the top achiever category with topmost position in 9 group reforms. Andhra Pradesh with 5 group reforms and Gujarat with 3 group reforms. Actually, as per our manifesto, that is our government's LDF manifesto, that is the that gave direction to all of us, and we are working on the basis of that manifesto. As per the promise in the manifesto, we could achieve the number 1 position in 2026. Then we could achieve in 2022 ranking itself. Then it is a big challenge for us to maintaining this number 1 status in the coming ranking also. Kerala is not well known for its industrial achievements. Kerala is well known for its model of development focusing on social indicators, human development index, education advancement, and health sector improvements. But if we are thinking about industry, not that much good. Kerala is good for tourist, God's own country, nice place. But industry, some difficulties are there. There was the presumption prevailing in this all over the world. But this presumption is far away from the facts actually. Kerala is now contributing, Kerala companies are contributing 24% of the turnover of the medical device companies of the country. 24% of the turnover of the medical device industry is coming from this small state. Kerala is a very small state, only on geographically and demographically. But other things, Kerala is a big state. Even health and education and greenery, clean air, these type of indexes, Kerala is a very big state. But always we are talking in our speech, Kochi Kerala, small Kerala. That is creating this impression. Then Kerala companies are only 6% of the medical device companies of the country. These 6% of the companies contributing 24% of the turnover of the medical device industry of the country. And Kerala is the global hub of spice processing. 65 to 70% of the oleoresin used by the world is manufactured by the state of Kerala. Then we are focusing on these type of industries. If somebody is coming to me for asking 3,000 acres of land for a big manufacturing industry, it is difficult. Land is the one shortcoming of the state of Kerala. We cannot do anything to improve this. It is small landscape. One side is belongs to CRSZ, other side is belongs to Western Ghats regulation, in between wetland regulation, ecologically very sensitive. The population and forest ratio is very high. Now the wild animals are demanding more space for their activities. They are coming to the cities also. This is the picture of the landscape of the Kerala. And the cost of the land is very high. But the major advantage of the state of Kerala is highly skilled human resources. That is why we are focusing on knowledge-based industries. If we are starting a big garment industry in the state of Kerala, for the workforce, that industry should depend on migrant labor. Nobody from the state of Kerala is interested to working in this type of manufacturing industries. Then if the salary is around 10,000 rupees per month in this manufacturing garment or other industries, if they are engaging 10,000 employees, then the total salary is only 120 crores per annum. IBM started its campus in Kochi 2 years back. Now they had recruited more than 3,000 professionals. Average salary per annum per head is 20 lakhs. That means 600 crores per annum is the salary. 3,000 for 600 crores. Here 10,000 for 120 crore rupees. Then where should I focus? This 3,000 for 600 crores annum salary normally going to Kerala economy. Most of them are Keralites. A reverse migration is happening. If a big manufacturing industry, most of them are migrant labor. The money will flow to other parts of the country, not giving boost to our own economy. That is why we are focusing on this. Yesterday I have a discussion with just one world leaders in semiconductor design. They have recruited 150 people. Now I am going to inaugurate the next week of their campus in Kochi. The annual salary per annum, that is 70 lakhs. Niche technology. Why they are coming to Kerala? The experts are available here. That is why they are coming to Kerala. I had a discussion with the 50 semiconductor designers, Keralites. They are working all over the world. They are thinking to come back to Kerala if you are providing all facilities. Then this is the advantage of state of Kerala. The highly skilled human resources, a thriving ecosystem for knowledge-based economy. And the state government is committed to transform the society into a knowledge-based society and the economy into a knowledge-based economy. That is why we have focusing on this connecting between research and higher education institution along with along with industrial establishment. We have established the first digital university of the country, digital university. All emerging technologies, AI, blockchain, machine learning, big data analysis, robotics. They are training thousands of young talents of the state of Kerala. Then, but that is not sufficient. A mismatch is still existing in between the need of the industry or the requirement of the industry and the skill of the outcome of higher education institutions. Now we have decided to establish campus industrial parks. The novel idea, first time in the country. Campus industrial park. Higher education institutions can establish an industrial park if they are owning more than 5 acres of land. Other than the sufficient land for running that higher education institution as per the guidelines of regulatory authorities like UGC, ICT or Medical Council, then they can apply online. Then we will give an industrial status for this higher education institution for establishing a campus industrial park. Then the students can work there. If you have established a campus industrial park, a student in the plastic technology or biopolymer or any other technology, he or she can work in the industrial units. They can avail hourly based wage from the industry. And our request to the higher education department to give credit or bonus mark or grace mark to the student against the working hours if she or he is working in the same category. If a BTech student or a BSc computer student, if she or he is working in a IT company in the campus industrial park, in addition to the wage, they will get a credit from the higher education institution. Within a week, we got 80 expression of interest from higher education institution, 80. Our goal is to establish 25 in this year. We are working on the online applications. And also we have decided to establish private industrial park. Private industrial park. Within a year, we have given developer permit to 30 private industrial parks, 30, within a year. The same status as the government industrial park. Government is not intervening in other activities. We are establishing a single window clearance board for the private industrial park. The last assembly session, we have made a amendment to the existing act to give a birth to the COO CEO of the private industrial park as a permanent invitee to the single window clearance board. The existing act is not permit the government to include the CEO or the head of the private industrial park to the single window clearance board. That is why we have amended the existing act in the last concluded assembly session. And then he has say to in this giving permit to the industries unit. And before the inauguration of the private industrial park, we are giving the notification to declaring that area as an industrial area. The same status of the KINFRA or KSIDC government industrial parks. Then I would not like to take more time because some other program, Honorable Chief Minister is also here in the district and also in my constituency. We have decided to host the Invest Kerala Global Summit on February 21st, 22nd at Kochi. We have decided 3 years back this date, but the normal phenomena of this global investors meet, conversion rate is around 10 to 15%. Declaration is very big, but the conversion rate, if you are going to the analysis of this global investors meet of different states, the conversion rate is very limited. That is why we have decided the conversion rate should be more than 50 to 70%. Then we have adopted a new industrial policy 2023, giving 22 priority areas focused on this knowledge industry, this AI and new emerging technology, robotics and graphene, logistic park, food technology, food processing technology, and maritime and sector. These are some areas in these priority sectors. We are grouping this to 3 or 4 focus areas for this investors meet. And prior to the investors meet, we have hosted a international generative AI conclave along with IBM in Kochi. Then we hosted a roundtable on robotics, that is over, a roundtable on maritime logistics, and roundtable on bioconnect, that is life science, that was hosted at Tirunelveli. Then 12 roundtables prior to this global summit, and roadshows. Chennai roadshow is over, Bangalore is also over, planned for Mumbai and Delhi, thereafter Middle East, and some online programs. Then we have decided to adopt some sub-policies and frameworks. Graphene framework, ESG, environmental social governance framework, and AI. And GCC, we are focusing global capability centers. Kerala has big potential for that also. And our IT policy, new policy is almost ready yet to be published. It will also give some space for private IT parks. After finalizing all these documents and these roundtables and conclave, we are going to host this global summit, Invest Kerala Global Summit. And we have a plan to establish a skill university also, like a PPP model, by the initiative of the industries along with the industries establishment. We are working on that concept. And this is the right time for the state of Kerala. We are already taking off to lead the country in Industrial Revolution 4.0. It's very difficult, either the 4.0 or 5.0. Very difficult to demark in between industrial revolutions now. Earlier, they have taken centuries from industrial revolution to second to 3, to 4. Now it is very difficult. In our students' days, the teachers can teach the students using their study notebooks of their student days. Now it is very difficult. The first some student, when he reached the last sem, the most of the technology he learned from the first sem is already outdated. That is the speed of the technology of the day. That is why we have decided to make our higher education system more flexible, to adapt the changes in the technology. Curricula, syllabi, pedagogy, everything should be flexible. Otherwise, it had taken more than several years to adopt some changes in the syllabi. Most of the academic community is thinking about changing the notebook which they have kept for teaching the students. That was the major apprehension to change the syllabi earlier. Now everything has been changed. The concept, presumption, everything has been changed. I think the contribution of Cipet, they are doing several good activities here, but they can contribute more to the industry sector. New emerging technologies, this green polymer technology or this biopolar starch and other thing, how can you use, how can utilize the natural fibers like coir, and that will, I have now seen a product utilizing coir with a bipolar. Then this give more scope for the traditional industries. They are challenging or struggling now for their getting market for their products. Then these type of additions or value additions will give more momentum. Kerala government has now introduced the Kerala brand. Kerala is well-known brand for the world for other aspects. Now we have introduced Kerala brand. Ethical and quality, two aspects are there. Quality by the reputed agencies. Ethics, percentage of the woman participation, the labor, child labor, environmental issues. If they are clearing the criteria, then we are giving a hologram and a video QR code is there also, how it is manufacturing. Then I hope more contribution from Cipet to strengthen our industries of the state of Kerala and also giving more contribution to the economy of the state of Kerala. By these words, I inaugurate the 9th series of International Conference on Biopolymers and Green Composites hosted by Cipet Kochi. Thank you.
Thank you very much, sir. We are very much honored to have the Most Honorable Minister, C.P. Rajiv, to grace this occasion with his esteemed presence. It's our privilege to present a small token of our gratitude to you, sir. I request our beloved Joint Director and Head, Dr. K.A. Rajesh, to honor the Honorable Minister, C.P. Rajiv, with the memento. Thank you all. I would like to welcome Professor Dr. Alex James, Digital University, Kerala, to address us with the felicitation speech.
Good morning, everyone. I was not prepared for a speech, but I'll still anyway talk because I'm a professor. I can talk anywhere. So when I came to India, like around roughly around 2019 end, just before the COVID, first thing was like, I was very confused. Why am I here? Because many things that I found at that time didn't comply with the expectation one would have. So first thing that I got hit was like, in an academia, all the places I've been, there is practically no difference between academia and industry engagement. So when I was doing my PhD, I had a startup company. I raised around $30 million. We had many things going on and all those things. And I was also doing like some research and teaching and all those things going ahead. And this was very natural thing. And when I came here, like the first thing is, hey, why do you want to do that? Right? That's the first question you get. Like, why do you need to talk to industry? Over the years, another thing that we found in industry and as well as in academia is the best way to learn engineering is actually by doing. There is no other real way to learn anything. You learn by failure, You learn by trying out things. You learn by exploring things. And is it something that is feasible today in many of the British era kind of policies and other things that we are stuck with? Especially in academia, if you look, people are not that easy to change. You basically get stuck in certain things and certain ideas, and it's very hard to move because your belief system is very core and hard rooted. If you go to industry, this is not possible. Because if you don't change your belief system, you don't exist in the market anymore. You're more worried about what the customer wants, what the end user wants. Now, why are we not doing that in academia? It should be very obvious. Like, if you want to take your student and make it like industry ready, then you need to know what the end user needs. So, if I spend 1 or 2 hours teaching someone, will they actually learn? Does anyone really ask that question? Is teaching really the way to go about learning? So in neuroscience, there is a very good study which they conducted on all the lectures that people were giving for hours, and in almost every study it is very consistent that there is no person in this world who can actually listen and comprehend things more than 15 minutes. So which means if I'm going to give a lecture of 1 hour, 45 minutes your mind is asleep. And who is getting satisfied there? The teacher is getting satisfied because I'm able to learn and relearn. The only person who is actually learning there is the teacher themselves, because you are repeating the information many times, and rest of the audience is happily sleeping, and they are all happy because they get attendance, and that is a requirement, and finally they'll prepare for an exam, they get grades. But does anyone really think about learning? And this is the question. So one thing that we tried in the university is first thing that I did when I took over as a dean of academic is let's completely remove classrooms. And I had so much opposition on that. Okay, how do you teach if you remove classrooms? So redesign the space such that even if you don't teach, the student should learn. So if you start thinking about learning, the entire approach changes. So first batch of students, when they came in, we only have postgraduate research programs. So we don't have undergrad. So students who come into the program are usually undergrad students from very different kind of colleges. Everyone used to coming to college at 9 o'clock and going at 4. They look for the time and things like this. Now the first thing that we said to them, okay, we don't have timing. It's a 24/7 learning environment. When you want to teach and when you want to learn, it's between you and the faculty who's in charge. We give you 24 hours, a full day for your classes to conduct, and whichever way you want to do it, at the end of the day, you need to ensure that there is a real outcomes coming in. And obviously all the programs today in India are outcome based, which means it's never talking about teaching, it's talking about outcomes. And it also means that it's not talking about lecturing, it's actually talking about contact hours. Now there is a fundamental difference between learning and teaching and delivering the content and making it as contact hours. If you're a contact hour, I'll see employee-employer relation rather than seeing it as a guru-siksha relation. There is a fundamental difference there, if you want to make people industry ready. So first semester, everyone struggled. Pretty much hundreds of complaints. Students couldn't handle it. They were exhausted because, we have labs open. People are sitting late night. They're coming in the morning, Second semester, now we didn't have to do anything. They are automatically there. They're actually we were giving rewards to failures. So if you have, failed more, you get more marks, right? So they need to submit the reports. They need to actually show that they tried this, they have done this, and at what level are they achieving it. And this continued for a year. And the second year, we took another strange decision. You can say strange because we say we will not invite any campus companies into the campus. So then we'll say like, why are you doing that? Because one thing what we find is like, as and when the campus placement idea comes in, people get a placement and learning stops. So we said like, to the companies also who came and said, don't give them offers, you take them as interns. Test them out, see how they work, let them learn. Then once you see like that, how they perform, because, interviews don't tell like how the people are, the learning habits are like, practices and all those things are different. So few people went into industry, almost all of them went into industry in very specific areas like of their specialization. So, I can say next 1 year they were in industry completely transformed. So at the end of the day, all the industries, like, these were the first batch of students. I think they all went to specific things like Collins Aerospace and many of them, all very specialized jobs on the specialization they studied. And they were not looking for, this was a very interesting thing that happened. Some CEOs came for discussion and they were interacting with the students and they were talking about jobs and all these things, and the students started talking back to them and saying like, no, we are not worried about jobs. No. We'll get a job, like I want the right kind of job. And the CEO came back and said, what kind of breed is this? They're not worried. Usually everywhere I go, like, there are hundreds of people saying, give me job, give me job, give me job. And here you have people who are saying like, we're not worried. And the second time when we continued this, we had like MTech program and MSc program. MSc program, students are coming from BSc background. And the second, the first batch, I would say, a lot of them who could, and it's a VLSI program, someone who has absolutely no background in designing a chip, in 2 years they were able to design a full layout. And during one of the interviews, like a guy from Broadcom asked me, okay, are you sure are they really like an MSc graduate? Because they were confused and they were asking again and again and again, verifying their designs, asking questions. I didn't understand why they were asking like a half an hour or 1 hour, and then finally they told because they couldn't really trust that someone who has finished BSc physics, then an MSc in electronics is able to actually do a complete physical design and layout and to that level. And that's all what I want to say, that industry and academia interaction shouldn't be seen as strange. It should be seen as something very natural. I can also give one last example. So we had some work with randomly, someone approached me from army saying that we have something to do. Can you help do it? So when I looked at the problem, then I could see there is a need for electronics. There is a need for material science. There is a need for algorithms. There is a need for, looking at antenna designs, all sort of things, all in a single system. Only challenge we had is we need to deliver it in 48 hours. Okay. So we didn't know whether it works. I took people from my group. My group is also very strange. I have people from chemistry, physics, maths, electronics, mechanical, all sort of. Because we look at solving problems, so we don't look at what their background is. So they came in. We put it in to them and said can we do something? So we had 6 volunteers. Didn't sleep for 2 nights. We didn't know whether it will work. It was delivered to the army and it worked perfectly. And that was all it told was that, it was not that 48 hours. It's actually what it led to that 48 hours. Because there is a lot of things they had tried, failed and things like this. So they were able to put things together, connect things together very fast. Someone from material science will only think about material science, right? So here when you have an interdisciplinary kind of team, we are using material science and machine learning. We are using something like software development along with electronics. all going in, and we're not really saying, okay, we don't classify as like you are a computer scientist, you are an electronics, you are a polymer engineer. We don't do that. And that era of science and technology is way, way past. Today, like if you look at internationally, any place you go, any research lab, any serious place you go, you don't see classifications anymore. You simply see like, you have problems to solve, and for delivering that problem, what is the kind of expertise that you need? You don't look at like, all those stuff. What you look at is, are you capable to do it? Right? So do you have the skills to do it? Do you really have the knowledge to do it? Are you mentally prepared to do it? And that's what I see the last word, mentally prepared. What Kerala is going through, it is just a perception issue. And perception issue comes from the mind to change. The only change can happen if you want to be the change. There is no other possibility. You cannot expect someone else to come and solve the problems for you. It doesn't exist. I have went to like universities, I've been to places where it started from zero. And within 3 years, like, we managed to, at least have certain level of international recognition. Last 3 years, we had like an IEEE Circuits and Systems Society activities. When I came here, there was absolutely no activity. With my students, and we just ran around, got many people in. And we had many activities going on in a year. By the second year, this particular chapter got the region, like Asian Best Chapter Award. The year later, this got like in this year, it got like the Global Chapter of the Year Award, putting us in map. And all because, you just decided you want to do something, right? And there were many people who believed that, like, they want to do it. And that's all. Like, it's all it takes is that, taking that first step and having that mind to just go about it. Challenges, whatever it is, there will be, right? Even if you have a perfect policy, there will be challenges. Unexpected challenges always happen. But how do you find solution to those challenges are the key thing. Do you have a mind to change? Do you have a mind to push it hard enough to make those changes? Is the only thing. And that's all what it takes. And so far, my experience in being in places where there are so much bureaucracy, from Europe to Russia to US to Australia, all the places I've been to, like, all the places have its own challenges. And in all the places, like, the difference is just the acceptance of failure, and it's okay to fail, and it's okay to take risk, and it's okay to, like, go about trying different things, and don't worry about the rest. It will happen. That's all what I would like to say, and I'm really looking forward for this collaboration, because like why we wanted to have collaboration with Cipet is, like, they think very much like in terms of values and many things, like they think like an industry. I always like to see myself as, like, an academic body with a soul of industry. Okay, so I see the same kind of thing with Cipet, and I think, like, there is a long journey that we are looking at. Thank you.
Thank you, sir, for your insightful words. I request Shri J. Sunil, President, Kerala Plastics Manufacturers Association, to deliver the felicitation speech.
Good morning, all. Honorable Minister Sri P. Rajiv, and in the absentia, DG Cipet, Dr. Shishir Sinha, Professor Dr. Alex James, very smiling professor. We are not bored for a single minute, and I'm sure your students will have the same experience. Srimati Ambali TB, General Manager Kinfra, Dr. K. Rajesh, Head Cipet Kochi, all other dignitaries on and off the dais. On behalf of Kerala Plastic Manufacturers Association, I heartily congratulate Cipet Kochi for conducting this international conference on biopolymers and green composites. I also use this occasion to note that Cipet Kochi is moving forward in a very positive and very constructive way. We have been associating with Cipet for quite some time, and recently they have received the NAC accreditation and some more certifications. Congratulations. As you are aware, the government of India has banned single-use plastics from February 2022. Almost 10-15 items were in either completely banned or partially banned. So one of the most used and common item that was banned is the plastic bags, especially the carry bags. It has been very common in use, very economical, very comfortable. So all on a sudden, we, for us, who represent almost 800, 900 small, medium industrial units in Kerala, it has come as a shock. In fact, Government of Kerala, 2 years before itself, has banned some products like this carry bags. But subsequently, central government has banned the cutleries and all. So, on that background, this conference is very vital because to use biopolymers as an economic, as an environmental alternative to conventional plastics is a matter of great significance for protecting the environment and taking the industry forward. Because as we all are in fact aware that plastics is an integral part of our daily life. Plastics we cannot survive. That's a reality. So some of the products that have gained a negative trend or a negative name, that has to go, no doubt about that. We, in fact, never challenged the ban of plastics in any of the court in our country. Our only contention, only difference with the government was that government should have given ample time for us to sell out the stocks, which the state government didn't do. So it is very significant that Cipet is conducting this meeting, and also Cipet is giving certification for whoever has an intention to manufacture compostable products. But the time taken and the cost involved is a little bit higher. So technology has to be developed so that it can be made affordable, or rather economically affordable to those people who are in the industry. Their activity has blocked. So to switch over, Cipet should develop new technology and make it affordable to industrials like us. Then coming back to the significance of plastic manufacturing in our country, last year I have attended a technology conference which has been conducted in 6 major cities in India. Government has published a booklet and it has given all the details narrating that 1 year India is importing finished products worth 40,000 crores. That study was very comprehensive, item-wise, country-wise, and amount-wise. You won't believe that this mobile which we use, the cover of this mobile itself, India is importing mobile cover worth 200 crore rupees in a year. And water bottle, maybe of higher nature, India is importing 400 crore rupees water bottle in a year. And this is, they have given it in a booklet and asked our industry to grow to an extent that at least half of it should be manufactured under Make in India project. So, potential for plastic industry in India is very high. And 2 months back, as a continuation of that meeting, there was another meeting in Habitat Center, New Delhi, which also I have attended. That was conducted by DCPC, Department of Chemicals and Petrochemicals. The director present there, she has talked hardly 5 minutes. That was a full day meeting. She said, we came here to hear from the industry what all soaps, what all assistance you require, like TUF, Technology Upgradation Fund and all. We are ready to give the industry what all support. In this backdrop, I have recently talked to one of the Deputy General Manager, Mr. Mahesh of BPCL. They are setting up a polypropylene plant in Kochi, which you might have all known. And the Kinfra is expected, or they are planning to set up a plastic park. I think that planning and all is in the basic preliminary stage. So, if a BPCL petrochemical plant comes up in Kochi and one plastic park is coming up either in Cochin, Mr. Mahesh told me that if more export-oriented units are there, they will set up the plant in Kochi, or else it can be set up in that economic corridor which is going to come in Palakkad. Anyway, government is moving with such a step. In fact, in our informal discussion, we industrialists, we fear that how many of us have grown to such a level to occupy that stage or that platform. I'm speaking this because purely those who are related with industry and academics are present here. If policymakers are here, we won't be able to disclose our fear. But my humble request as a president of our organization, what we have seen that people are not coming up to utilize these facilities. If that 40,000 crores of worth finished products which are imported every year, we can get at least 5,000 or 10,000 crores of finished products manufactured in our state, then that will be a great step forward. So, my humble request is that our children, they are blindly going abroad. That is much discussed area now. So, you should, even those who are in industry, should take a very courageous step forward to utilize these opportunities. And I'm sure that Cipet is doing their level best to support the industry. Many of our units are using these facilities, including testing and all. Before winding up, we, from our part, as an industrial association, moving forward with a social commitment, we are supporting some of the students of Cipet and Cochin University with the scholarships and awards. Those who are engaged in polymer studies, we are supporting them. And from our Silver Jubilee year, 2 years back, we have set up an environmental award for each one, for an individual and an organization, with a cash prize of 50,000 rupees and a citation for those involved in limiting plastic pollution or collecting plastic waste and giving for recycling. We have given the award for the last 2 years, and now we have announced the award for 2024. So, it is a matter of our existence too. So we request all of us to understand and appreciate the significance of this industry, and also let us together, the industry, from industry side and Cipet side, we can move forward and utilize the opportunities coming up for plastic production in our country. Thank you.
Thank you, sir. Your words are truly inspiring. Now I would like to request Srimati P.L. Ambali, General Manager, Kerala Industrial Infrastructure Development Corporation, KINFRA, to present the felicitation speech.
Good morning to all. Actually, I am familiar with the expanding, so we are expecting more feedstocks by 2027. I think already some discussions were going on with the BPCL and the Cipet, and also KINFRA is setting up a petrochemical park in Kochi, and we are planning to earmark a zone for plastic industries in Palakkad, because from Coimbatore as well as Thrissur side and northern side, industries can be set up in Palakkad. So I think this is the right time to inform all the investors how KINFRA and industrial department can help all of them to set up a unit in Kerala itself. I am very proud to see that my entrepreneurs from other parks are here, because they have a success stories by setting up industries in Kerala. Actually, what Alexa told was right. If we want a change in any field, first we have to change our mind setup. Actually, last 4 years, all the staff, actually I'm representing KINFRA, means from department side. So our staff in all the departments are trained, and earlier what we are providing is we will be providing a land or built a space, or my sister concern organizations will provide a loan. That's all what we are doing earlier. But now what we are doing is we are ready to stand along with investors, so that if you have any trouble in either marketing or getting additional benefits like incentives, or any shortage in infrastructure side, if anything has to be changed, or even Minister is very supporting for making changes in the policy matters also. That is why actually KINFRA formed it is 31st year. And this year we announced an exit policy. Our land disposal policy itself has been changed. Even our investors know very well that there is some problem with the exit policies. If a genuine investor don't want to continue, while he is transferring the unit, some issues was there, because he has to get payment difference in lease premium. It's a major amount. But such policy changes we made, and it is easy also, because only depending on the operations, only a percentage has to pay. That means if difference in premium is 2 crores, he has to pay only 10% of that amount if 7 years already passed after production. And also I would like to share about the facilities KINFRA has now in throughout Kerala. That means we have from Kasaragod itself, we have new land expansion in Kasaragod side. And we have 31 industrial parks throughout the Kerala, both the built-up areas as well as land. Built-up area means it's a standard design factory buildings. You can, after incubation, I have seen incubation units in Cipet. Once they are incubated, it will be difficult for them to take a big factory setup. Instead of that, they can take 2,000 or 3,000 more square feet area, and can, to next level, they can rise your industry. After that, once it is okay, they can take a land and start their own unit. Such facilities KINFRA is offering. And regarding, Minister sir already told Kerala is #1 in ease of doing. I think most of the our investors are, established investors are aware about our KSIFT facility, which is useful for starting your industry. Just after registering that, you will get another 3 years time for taking all the permissions, all the licenses. Before that, you can start your construction. I think it is beneficial to the startup units, because otherwise they will take a lot of time for taking approvals and all. Such benefits or facilities already provided. Those things you can avail, and also you can, there's no need for approaching a KINFRA person. There will be officers at panchayat level, block level, like that. So any of the officers, whether it is a DIC officer or KSIDC officer, you can approach and any of your problems will be immediately attended. If it has to go up to minister's level, there are portals where we can upload. You yourself can do, otherwise our officers will take up and solve the issues. And also KSIDC, KFC has introduced new schemes for getting financial assistances. Earlier, additional collateral securities are required. At present, I think KSIDC has new schemes which is beneficial to investors. Even using our KINFRA, even though it's a leased out land, that can be considered as a security. To particular amount, loans will be given according to that itself, or additional funds only required collateral securities. Like that, I think it's a investor friendly. Kerala has been changed. It is the official, not the official records, as ministers are told. It is from the feedback of investors only that rating has come. Actually, my request is you should utilize the present investment environment in Kerala. And some of the guests are from outside also. I request they can make a unit in Kerala itself, so that our plastic side industries can be grown to a level using BPCL feedstock and all. So that's all. I will be here if any assistance or further interactions are required. Thank you for the opportunity, Cipet. Thank you. Thank you all.
Thank you, ma'am, for your informative speech. It's our privilege to honor our honorable dignitaries with a small token of our gratitude. I humbly request Sri S. Vijayakant, Senior Technical Officer, Cipet IPT Kochi, to present the memento to Professor Dr. Alex James, Digital University, Kerala. I request Sri A. Shankar Ganesh, Senior Officer, Cipet IPT Kochi, to present the memento to Sri J. Sunil, President, Kerala Plastic Manufacturers Association. I kindly request Dr. K.P. Bhuvana, Head Academics Manager Technical, to present the memento to Srimati P.L. Ambali, General Manager, Kerala Industrial Infrastructure Development Corporation. Thank you all. I request Sri S. Vijayakant, Senior Technical Officer, Cipet IPT Kochi, to propose the vote of thanks.
Good morning, everyone. It has been such an honor here to be a part of this wonderful event. On behalf of Cipet, I would like to extend my heartfelt gratitude to our Honorable Minister for accepting our invitation in his busiest schedule to grace the occasion. Today we had the opportunity to hear your thoughts and will be surely here to encourage us in your future events. Next, I thank our DG Cipet for continuous support in improvement of the Cipet. Then I thank our joint admin head, Dr. K. Rajesh, who has always been a supportive our initiatives and encouraged for this drive of excellence. Thank you, sir. Then I thanks Professor Alex sir from Digital University for the continuous improvement and innovative in the teaching, and also coming forward for making the MOU with Cipet for the various collaborative research projects in faculty exchange and student exchange and various R&D projects. Thank you, sir. Then I thanks Mr. Sunil sir, KPMA President. From the establishment of Cipet Kochi till now, KPMA has been the full background to the Cipet Kochi. Yes, and also for various activities, they are continuously supporting. The Cipet has been built so far because of their support also. And also they are come forward for the various scholarships and meritorious for our Cipet students. Thank you very much, sir. And I thank the Ambly madam from the Kinfra for coming here in short notice, and also for what are the exploiting in the plastics industries, how the setup can be made, and what are the different sources available. And also we are having the next session where we can discuss about technical sessions, what are the different advancement in plastics. So I welcome to that event also, madam. Then finally, I want to congratulate all the industries, and just a clap to all the industries who have come over here for attending the function, because without the industries, Cipet has always been the backbone to the industries. Without the industries, the Cipet has not been grown. So we thank the industries for coming over here and supporting to the Cipet every time. Thank you, sir. And I thank the press and media and all the event management and our team Cipet Kochi for organizing this wonderful event. Thank you. So,
Thank you, sir. As we bring this inaugural session to a close, let's honor our nation with unity and pride. I request all the dignitaries on the dais and the audience to rise for the national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
now I'll all the industrialists and participants to go for the high tea, and after high tea we have the technical session at the boardroom second floor. All the industry peoples are requested to attend the program, sir. Thank you. Conference will parallelly continue here.
Sir, the industry interaction meet is scheduled in the second floor boardroom, and the international conference will be continued in the same hall after the tea break.
Check. I request Dr. Manjula ma'am to welcome Dr. Prashant Raghavan sir. Professor Prashant Raghavan is a professor and head at the Department of Polymer Science and Rubber Technology, Kochi University of Science and Technology, and visiting professor at Gyeongsang National University, Republic of Korea, and Scotland's Rural College, UK, and MG University, India. He is listed in top 2% scientists in the world from 2020 and worked with a couple of Nobel laureates, including Professor John B. Goodenough, who received a Nobel Prize in Chemistry in 2019. Professor Prashant worked at Nanyang Technological University, Singapore, Energy Research Institute at NTU and TUM Create, Technical University, Munich, Germany, Rice University, USA, Edinburgh University, UK. And Professor Prashant was selected for the Brain Korea Fellowship, Sage Research Foundation Fellowship, Brazil, Estonian Science Foundation Fellowship, European Science Foundation Fellowship, Faculty Recharge, University Grants Commission, etc. And Professor Prashant was received many international awards, including Young Scientist Award, Korean Electrochemical Society, Bharat Vikas Yuva Ratna Award, Educational Excellence Award, Dr. S. Radhakrishna Bharat Shiksha Best Teacher National Award. His current research focuses on nanoscale materials and polymer composites for printed and lightweight charge storage solutions, including high-temperature supercapacitors, batteries, and triboelectric nanogenerators. Professor Prashant has published many research papers in high-impact factors journals and a number of books and book chapters, and has around 9,000 citation and H-index of 50. He is serving as editor or editorial advisory board member of many SCI international journals and member in Board of Studies and Academic Council in a couple of universities. He is also an elected Senate member in Kochi University of Science and Technology, CUSAT. Professor Prashant is a book series editor for Springer, Nature, Elsevier, Taylor and Francis, CRC Press, etc. Apart from science and technology, Professor Prashant is a poet, activist, and a columnist in online portals and printed media. I request Dr. Prashant sir to chair the plenary 2 and keynote 2 section of this day. I would like to hand over the session to Dr. Prashant sir.
A very good morning for everybody. So today, and thank you for a very nice introduction. So I would like to chair this session. First, we have the first plenary session by Professor Mohan Jacob. He is the Dean of Research Infrastructure at James Cook University with a strong focus on sustainable materials and very apt person to deliver a plenary session here. And he has made a significant contribution to the development of novel materials for the industrial and environmental applications, including graphene-based composites, biochar, and plasma-modified surfaces. His interdisciplinary research spans across areas such as renewable energy, biofueling resistance, and waste-to-resources technologies. He has published over 250 peer-reviewed research articles in interdisciplinary and focused journals with a very high impact factor. And he received over $12 million research fundings. He is consistently listed in the top 2% scientists in the world, listing by Stanford University and Elsevier. According to the last 4 years, he is listed in the top 2%. His research is globally recognized for its innovation and sustainability and practical relevance, making him a highly regarded in this field. In addition to this, his research, Professor Jacob is dedicated to mentoring the next generation of scientists with a strong focus on fostering industry collaborations and translating research into the real world application. I welcome Professor Mohan Jacob to this session, and now the floor is open for you. And we are a little bit late because of some inconvenience happened. So please try to finish in the right time. Like the 45 minutes is for the plenary sessions. 35 minutes for the plenary session, and I request you to finish it in time. Thank you very much for the smooth, then we can complete the session in a very smooth way. Thank you very much.
Thank you very much, Professor Prashant. Thanks for a very kind introduction there. So I'll be talking on the microwave and our plasma-based resources for developing carbon nanomaterials there. My name is Mohan Jacob. I'm from Gemsuk University in Australia, and my talk is also basically contributed by some of my PhD students who already finished their work in the last couple of years, who obviously also the names are listed here. So those who are not familiar with like where a university is, I basically given a map of Australia. And you just remember that, okay, Australia is around 2.5 times bigger size as India. And so we are basically in the northeastern part of Australia. So it's the Townsville. And Townsville is next door to the Great Barrier Reef. And so I've basically given some pictures so that you basically like those who are interested to basically visit the place. Okay, obviously it is a very nice touristic place, and also academically also basically like you are most welcome to basically visit James Cook University there. So this is an overview of my talk. I'll be giving a small introduction about the sustainability and also the nanomaterials that. I know the focus of the conference is probably slightly different but okay, I try to basically like come back into those kind of topics, especially like the biopolymers and the green composite materials that. Also, I'm basically using different types of plasma sources for developing the nanomaterials, especially graphene materials. So the two particular sources I'm basically using is the microwave plasma and also the RF plasma there. So these days, we are talking about the carbon footprint, particularly achieving a net zero. Now, every country in the world now got a particular target. They need to actually achieve the net zero by certain year. I don't know exactly what's the year India has to actually achieve the net zero, but for Australia, we need to actually achieve net zero like 50% by 2035. And then by 2050, we need to achieve the full net zero or target there. We are basically talking more about developing the materials. And obviously, like when we are looking, especially looking like nanomaterials, there are different sources we are basically using, including chemical vapor deposition, pulse laser ablation, laser pyrolysis, cold gel process, lithography, etc. So all these processes consume large amount of energy. So obviously, if you're consuming more energy, that means obviously there is a large amount of emission is also happening there. Directly or indirectly, those emissions are happening there. Now, let's look at the nanomaterials itself. So always we need to still look the total emission happening. That is from the initial fabrication stage to the final disposal of the like whatever the application that you basically develop that one there. Now, for example, like typically we always was interested in talking about the emission when we are using the materials there. So, for example, like we're all talking about the electric cars. We never talk about how much emission is happening during the time of the manufacturing of the electric car, but we only basically focus more on the when we are running the vehicle. That's the time we are basically looking into that. But anyway, that's a completely different topic. What I'm saying is that okay, we need to always basically look from the beginning to the end of the life. So if you look in the nanomaterials, you need to look at the raw material extraction, obviously the extraction of the material is a very like energy consuming process. And also most of the time we basically mine the materials, then that material will be transported to another place for refining that one or processing that one. Then that material will be transported to another place for fabrication of things of the application stage, like that. So then the fabrication technique itself, okay, many of these ones, as I mentioned before, many of the applications we are using for the nanomaterial fabrication is a high energy consuming techniques there. In addition to that, most of these techniques also produce many byproducts there. So all this basically start contributing towards the emission now the last part of that is the transportation and the processing. That's basically like we basically made the material, but then okay, you need to apply that into an application that, and so that time also you need to do the purification, cleaning, and then once it is there, okay, the logistic of basically moving that around to or like exporting that to another places and so on that. So all these things, okay, we need to basically look and see that, okay, how much energy is basically used and how much it is basically contributed towards the emission process there. Now, while looking that, I can basically say that, okay, if you're looking overall, the transportation is one of the biggest contributor for the emission. And similar to that, the electric power generation, power distribution, um, and the waste happening during the power usage, etc., also contributing there. But another major one is basically the manufacturing. So the manufacturing industry is responsible for around 12% of the global emission there. So that means we had to basically start looking into the approaches, what approaches we can take to reduce the emission in there. Now, the second thing is we are basically interested in improving our quality of life. And when we are basically improving the quality of life, obviously we are basically producing more and more waste material there. So one of the biggest contributors is like the building and demolition, coming from the building and demolition of materials there. Similar to that, there are many other materials, maybe like the plastics or the office materials, glass, then like the organic materials, the food waste, and so on, also basically going into the landfill there. So that also basically contributing towards the emission there. So is it possible that we can basically find methods to reduce the emission by using less energy consuming techniques for the manufacturing and also like utilizing some of these waste materials for the purpose of developing the new materials that you want. Obviously, like most of the people here probably will be talking about the plastic, and plastic is more popular due to its versatility and the flexibility, the low cost, durability, and also it is very easy to manufacture. And the other thing is, okay, it is less degrading the environmental changes that you want. Annually, we are producing around 380 million tons of plastics around the globe there, and of which only 10% is basically recycled, and maybe around 12% is burned there. The remaining is basically contributing towards the environmental pollution, particularly as a plastic pollution there. Now, recently we all basically probably start talking more about the microplastic, because the microplastic is found pretty much everywhere now. The drinking water, it is the marine water, fresh water, or like even our body, it is saying that okay, we have plenty of microplastics we are consuming in there. It is probably as part of the food, or like even by breathing, we are basically consuming more of the microplastic there. So the microplastics comes in so many different forms there. So for example, like it may be in the fibers, like our cloth will have the cosmetics that we are basically using will have, the water bottle we are using, it will have, the disposable plates we are using, it will have the microplastic. And for example, like the tire and the wear and tear of the different vehicles and like that, all contributing to waste of microplastic. So the first part I basically wanted to look is, okay, like, can we basically use these microplastics for something useful there? So for that, I'll start looking more towards the carbon nanostructures. Now, the carbon nanostructure, typically, okay, like we got the graphene material there, or sorry, like the polarine material, one zero-dimensional or one-dimensional material like carbon nanotubes or the graphite materials, etc. But there is a reasonably latest arrival, which is, I can't say it is a new material, it is 2 decades now. So it is called a graphene. So graphene is a single layer of carbon atoms there. So it is a covalent bond with the 3 neighboring carbon atoms, and also it got a strong sigma bonds and weak pi bonds with a few layers there. So typically we say that okay, graphene is considered as one of the best man-made materials ever happened. So what makes graphene so important? And so first thing is it is very thin because it is a single layer of carbon atoms there. So it is pretty much like around 0.34 nanometer thick. Now it is highly electrically conducting material there. So that means okay, it is a low resistive material there. In addition to that, it is also a thermal conducting material there. And the surface area of the material is very high. So like 1 gram can basically cover over like 2,500 square meters, or like 1 football stadium can be covered by 3 grams of the material there. It is impermeable for most of the, even including the gases there. So even though it is very thin, the strength of the material is very high. Also, it is very stiff material, but it is stretchable. In addition to all these things, it is a transparent material too. That means, okay, if you're looking for conducting transparent materials, again, this is a good material there. So you can basically see that a number of different properties are built into this particular material that you under. So how we can synthesize this wonderful material? So we can use a top-down approach, or we can use a bottom-up approach. We can do that one. The mechanical exfoliation, that is how the initial invention happened there. We can use, but obviously the quality is not the best, but also you can't produce in a commercial scale there. You can use a chemical synthesis or chemical exfoliation methods. You can use that one there. And in addition to that, you can also use like the epitaxial growth or chemical vapor deposition, which is again okay, like more energy consuming that one in there. So in order to overcome that energy consumption, what I'm basically like doing is using some of the plasma based synthetic methods there. So the plasma processing, it is a complex interaction between the gas phase chemistry, and also it is interaction between your radicals and the plasma, and also there's the interaction between the surface phase chemistry and the conditions related with that. So overall, if you're still looking, you need to still look into 3 different areas, that is plasma chemistry, plasma physics, and the surface chemistry there. So in order to achieve the plasma, I can basically use 2 different sources. One is the radio frequency, which can be capacitively coupled, or it can be inductively coupled. Depends on what kind of configuration that you basically got. And also you can use the microwave energy for like producing the plasma there. Now the schematic of the microwave plasma system is it is shown here that. So you can basically see like it is a reactor, and there's a microwave energy is fed into this reactor that, and the pink color that you basically see, that is basically the plasma that. Now to that plasma, if you can basically like put any kind of material, it will basically start changing its properties that, because the plasma is a very high energy state that. Now, there are a couple of advantages of using this particular technique, because you don't need to use a substrate. You don't need to basically heat the material, because typically if you wanted to make graphene, it's around more than 1000 degrees centigrade, you're basically making the material. But you don't need to basically heat the material, and you don't need to use gases like hydrogen for that. It's a scalable process, and also it will actually give a high production rate that one there. So this is basically showing the way that you basically like the material is fabricating. That is the top left is showing the plasma, and without any of the chemicals or the precursors for that. The second one is basically showing we are applying some of the like the precursors into that. You can see that okay, there is a color change, which basically shows that okay, some interactions start happening there. So the material will dissociate within that plasma region, and the growth will happen there. And then due to the agglomeration of that material, you can basically like collect that material, And this the one on the right side shows the SEM image of that, and the one below that is the TEM image, and that shows like around like 0.37 nanometers. That's a interlayer distance. You can see that one there. Now, as I mentioned initially, like there's a huge interest is in the microplastic because of the problems it is creating at the moment. So what we are thinking is, okay, can we basically able to produce this micro like a graphene from the microplastic without these materials, like any of the sources of these plastics going into the landfill that. So you can basically see that is the microplastics. It is that's the white one there. Now we basically put that microplastics into the microwave plasma, and that microplastic is basically converted into graphene within like 1 minute of time that. So you can see that, okay, it is a very fast process. We are not using any kind of chemicals, because every time you basically try to process something with another chemical, that will create another problem there. So in this case, okay, like it is a direct process. There's no chemicals involved. It's a direct heating of the material that, and we're basically getting the graphene from that. So you can see the Raman spectrum of the material that we produce. You can see like 400 watts, 500 watts, 600 watts, like that. You can see mostly like all the three are basically showing very similar kind of Raman. That means, okay, even the power like 400 watts can produce a reasonable quantity of the graphene material that. And this the XPS basically shows the carbon and the oxygen. You can see 98.79% is basically the carbon, and 1.2% is oxygen that. So that shows that, okay, it is like highly rich in the carbon material itself that. And that shows the SEM and the TEM of the graphene produced from the microplastic there. So the yield of this one is quite good. Like we get around 5% yield that. So for example, okay, if you got like say like 1 kilogram of that one, you can basically get a 5% yield of the graphene from that. Now, by considering the value of the graphene, you can see that, okay, it become like a highly profitable kind of material that you can basically produce that. So there is no need of basically like these materials going into the landfill, but we can basically use that for making a highly valuable product that. The second thing we basically did is, again, okay, using the microwave plasma. Again, the reason we are using this plasma systems is to reduce the amount of energy required for making the nanomaterial. Now, if you wanted to make nitrogen-doped graphene oxide or any doped graphene oxide, you had to basically do 3 different processes. You need to first make the graphene, then you make the graphene oxide, then you basically dope the material with whatever the material that you wanted to basically get that one there. So in this case, okay, we are basically making the graphene, nitrogen-doped graphene oxide, and we are basically making that from aniline in there. So in this case, we are basically using something like 80 watts microwave power, which is very, very small power that. You know that, again, the normal light that we use at home is typically like the fluorescent lamps are like mostly 40 watts. Okay, these days, okay, more LEDs are coming, but the normal fluorescent lamps are like 40 watts or something like that. So you can see that, okay, like using a very small amount of the energy, you can basically produce good quality graphene that. So this shows the Raman spectrum. You can see the 80 watts material. You can see there's a 2D peak, which is the signature peak for the graphene that. So that shows the SEM and the TEM picture of the graphene oxide, and also basically showing the XPS there. We use we can basically make wonderful materials that, but if there is no particular application that you can identify for that, there's no much point of basically like making that material. The material property may be excellent, but if there is no real application, what's so much point of that? So that's why mostly we try to find an application also for that. So we try to basically look at the water contact angle of these materials that, and try to apply that for the water purification that. So you use like a membrane coated with the graphene oxide, which is used for the water purification purpose. We also basically use the same material for like the biofouling material that, okay. to prevent the biofouling. You use that one there. Another application we tried is use as a sensor. So we use like a electrochemical sensor. So you can see that we are using this for the oxalic acid detection there. So it's basically showing a very good response for that. You can basically see like a very small concentration of oxalic acid even can be detected using this method. And you can see every time when you inject small amount of the oxalic acid, you can see there's a change in the current there. So we also like try to apply other materials like ascorbic acid, glucose, uric acid, etc. But you don't see any changes in the current level there. That means it only basically detecting the oxalic acid there. So you can basically use this as a kind of a disposable kind of sensor for detecting the oxalic acid. Now, again, we got a high focus on using sustainable sources. So far, like we are basically using some of the materials which is a waste or something like that. But now we wanted to use more like sustainable sources for that. So typically we are looking some of the agriculture products. For example, like here you see like a tea tree, which is like a plant. Particularly it's a plant in Australia. And we also basically tried using like a orange or orange peels and like that. So create the essential oil from that and use that in the plasma, and which also basically produce the graphene and then apply that for some applications there. So one of the typical one we use is the tea tree oil. You can see that 200 watts microwave power is applied, and we basically got the graphene and material there. You can basically apply more power, and obviously like the production rate also will be much higher that. But overall you can see that by increasing that power, the quality is probably not increasing hugely that, but obviously you can produce more of the material that. So obviously there is a compromise. You can basically find what power is good for producing the maximum, for getting the maximum yield that. That's the experience, and you can see like we did a comparison of the material that we basically produced and compare that with the conventional materials like ethanol or methane, etc., used for producing the graphene. That you can see that typically they are using higher power, and also like the production rate is also like around like 2 or less than 2 like that. Now when we basically use the tea tree oil, you can see that we use a 200 watts power, and we basically got like 1.37 that. So it is more or less use a less power using a environmentally friendly source and getting a reasonable quantity of the material, which is good for commercial applications there. We also basically try to use that for detection of the duron, which is basically it is a pesticide, also herbicide, and you can see like we can see that you can detect the this herbicide in different concentrations there. Now, the next method that we are basically using is the radio frequency plasma. So when we use the microwave plasma, obviously you don't need to basically use the heating in there. You don't need to use a vacuum, but the material that you're basically getting is in the powder form. So typically, if you're going to make some electronic devices, probably it become more challenging there. So those challenges can be basically overcome by using RF plasma. So if you're using radio frequencies here, so the radio frequency signal is used to set up a time varying electric field between the plasma and the electrode. And this electric field accelerates the electron in and out of the plasma and that electrons gain energy and ionize the local gas there. So this is the reactor which is basically shown here. So in this case, if you wanted to make a graphene, you need to basically heat the system. So, but the advantage is you don't need to heat to very high temperature. Like again, it is relative, as I mentioned before. Typically in a CVD, you're like a heating to around 1100 degrees centigrade. But in this case, you need to heat somewhere between like 500 and 800 degrees centigrade only. So you can basically substantially decrease the amount of heating required for that. And it is a very fast process. But there are disadvantages like, you need a substrate. The production rate is also much smaller compared with the other techniques that had. So you can basically see this is the graphene produced using the RF plasma. So this curly kind of the appearance that you basically see here, that is basically showing the graphene. And this is not a conventional graphene. This is called a vertical graphene. And this vertical graphene, the advantage is the surface area is quite big. So if you're basically looking more for like the supercapacitors or battery or storage applications, you need more surface area. And for that purpose, these materials are good. The other advantage is, okay, you can see that, okay, the time that we use is like 1 second. Okay, we also shown 1 minute, 2 minutes, and 4 minutes. But the bottom one is basically showing 1 second. Okay, 1 second, that is probably it is a bit misleading, because you had to basically heat it to say around 500 degrees or something like that. So you need a couple of hours to heat that one. But once you basically achieve that, you use the plasma only for like such short period there. So the minute you basically turn the plasma, you can basically turn it off, and you still basically get a reasonable quantity of the material there. And the quality of the material is also really, really good there. We did the water contact angle for this material, which is basically shown here. It's around 130 degrees, which was basically one of the highest which is reported for the pure graphene material there. We also use that for baking the memory devices, like it's a switching memory. You can see high resistive state and the low resistive state depends on when you apply the voltage and you turn off the voltage, etc. We use the same material for making supercapacitor. Here you can basically see that, okay, it's a very small area. It's like less than 1 millimeter thickness, and the diameter is also like 1 centimeter there. So that such a small device can produce around 630 farads there. The other thing we also try to do is, okay, we try to make the solar cells using the graphene there. So it's not a completely a new work, okay, using graphene for making solar cell. But the change that we basically did is, okay, we didn't transfer the material. We basically like build the material onto a substrate and build the solar cell onto that. So it's a transfer-free graphene material that we basically make and make the solar cell for that. And typically it is for organic solar cell, not the silicon-based solar cell. So you can see the efficiency is a bit over 8%, which is really good that one there. Now, the other thing is, again, okay, this probably is more applicable for this particular conference too. Like we basically make the polymers, materials using the same technique there. But in this case, okay, we are doing at the atmospheric temperature, and we can basically like make a plasma-based polymeric material. And these materials are real like it is a hard material, but it's a transparent material, and you can basically see that, okay, like it can be applied onto different surfaces because we are not heating. So it can even apply to another plastic surface itself because it is doing at the room temperature itself that one there. And the example which is basically shown here is applying that on a solar cell, where you can basically see that, okay, like the efficiency remain same for much longer duration there. We can also use the material that for an antibacterial coating also there. Now, this is the last thing I just wanted to mention. Sorry, I'm just rushing these ones. We are basically talking about making materials and having different applications and like that. All these basically produce different kinds of waste material that I heard in the inaugural function, people are talking about the plastic production and that. But all these basically have byproducts, and byproducts is going to be a problem. Also, the plastic itself got a certain lifetime, it become a problem too. So how we can basically like resolve that problem there? So we basically made a microwave-based pyrolysis system. It is my own design, and we basically made everything here. So that's the system that you basically see here. It's around like 30 liters in size. We can basically like process any kind of waste material in this one. Okay, when I say any kind, probably I'll say any non-metallic one. It can be plastic, it can be tire, it can be paper waste, it can be coffee, it can be agriculture waste. It can be pretty much anything. You can basically process in this particular system. And the processing time is also quite small there. We scale up, so you can basically see like any of these waste, it will convert that into a biochar. And that biochar we can basically like apply into, for example, like concrete, or like the biochar can be basically like treated to basically make a graphene in kind of materials to that one, and then apply into electronics or water purification or different applications there. Now we scale up the system that we basically shown here. So we can basically like our scale up system can process something like around 1 ton during a daytime. Like when I say daytime, mostly like 10 hours of the time, we can process that one there. And so that is another way of basically like converting the materials into some useful materials that one there. So overall, this is the take home message. If we can basically use the microwave or the radio frequency plasma, that is a greener alternative for the conventional methods, because we can produce the materials at a lower temperature. The processing time is very, very short, and the energy efficiency is very high. And we are not producing any of the toxic materials, and we are not producing other byproducts, which is become another problem there. So, and also the total carbon footprint is very, very small there. So that brings me to my conclusions. That is a plasma-assisted nanomaterial fabrication is a sustainable fabrication technique, and you can basically use either microwave or the RF plasma for making value-added nanomaterials, which will basically have different applications there. So thank you very much for all the listening in.
Okay, thank you very much for Professor Jacob for a very an excellent talk over this production of the graphene and its application, especially in the supercapacitor. And now the floor is open for discussions, and a few questions are expecting from the audience.
Professor Jacob, it was a fantastic presentation. I really like the idea of producing graphene from microplastics. It's a fantastic idea. See, my question is, these microplastics will be collecting from the nature. It will be contaminated, right? So
yeah, that's true. Yeah.
So the properties you are expecting to get from the graphene, would it be the way, the grade you are expecting from these microplastics because of these contamination issues?
Yeah, you are very right about that one. If you basically collect these materials from the environment, you're basically seeing the contamination, especially there may be soil contamination or things like that. It will be that will definitely affect the quality of the material that you're basically getting there. Now, one of the important things is some of these materials don't really need high quality or like highly purified materials for certain application. One of the example is like the concrete. So if you wanted to apply like a graphene in concrete, you don't really need to have such a high purity graphene material itself there. So we had to basically understand, like where this application it is there. And then depends on that, we can basically try to understand, what methods we need to basically use. You can how to approach, you can basically clean the material first and then apply that. Obviously that is become more labor intensive, and also there is other things involved in that one there. So if you are really looking for making a highly purified graphene material or carbon materials, probably we had to basically do that cleaning process before that. In that case, we can use that for like the electronics application, the battery storage applications, and so on there. But the compromise is, if you don't want it to basically do that one, we can still make the value-added products, and then we can apply that into like the building industry there.
Thank you, Professor Jacob.
Thank you.
Any other questions?
Yes, Professor Mohan Jacob, it's excellent talk. And actually, I think you have used a microwave-based pyrolysis technique, right?
Yeah, so that is the last one.
Yeah.
The previous ones are plasma system.
Yeah.
So don't confuse between the plasma
Yeah.
and the pyrolysis. We got both. Yeah.
Yes, actually, controlling these, process parameters or the product quality using this microwave-based system is a bit challenging, right? So how you are able to address that?
Yeah. So always there is a challenge in some of these things. It is there, but if you're using like the microwave pyrolysis systems, okay, we basically made the materials using at the different power levels, different like the vacuum levels and like that. But more or less, okay, like we basically got very similar kind of properties for the end product there. Now I know that okay, there's a small difference in the yield, and also there's a small change in the properties, etc. So overall, we had to basically, again, as I mentioned before, we had to basically look and see where we are basically going to apply the byproducts there. So it depends on where you basically wanted to apply the byproducts. You can basically design the systems in that. Now the microwave plasma systems, that one, obviously, even if you're basically changing your parameters, say for example, like okay, using 200 watts power or 500 watts power, most of the time you can basically get the very similar kind of property that one there. But obviously, okay, there are challenges. It is there. I fully acknowledge that challenges there.
Yeah. Thank you. Any questions from the students? Anyone? So I have one small clarification. I would like to get a small clarification basically on the, you are doing excellent work basically on the microplastics. It is a very good initiative. I know this is a very serious issue. So maybe I would like to get a clarification on how you are going to collect this microplastics and how you can be sorted out. If you could give some, guidelines, that will be better.
Yeah, so obviously like collecting the microplastic itself is very, very challenging, and we haven't done that part. So what we basically did is, okay, like we are trying to see that, okay, can we basically make a method where we can basically convert the plastic materials into the graphene so that, okay, most of these plastic which is going into the landfill, before going into the landfill, can basically someone basically collect it and then start using that one there. So you're fully right. Okay, like once it become a microplastic, it is pretty much like impossible to basically collect that one and for the application there. But the important thing is, if someone basically find that, okay, oh, this plastic, okay, got this much value, in that case, okay, they don't basically let it basically go to even landfill. That.
Okay. Any other questions? Any clarification needed? Okay, I think we can, I would like to congratulate you once again, and we would like to move to the next talk, that is by Professor Sabu Thomas. Professor Sabu Thomas is the former Vice Chancellor of Mahatma Gandhi University, Kottayam, and he is currently the chairman of Trivandrum Engineering Science and Technology Research Park. And he is also served as the Director of School of Energy Materials, School of Nanoscience and Nanotechnology, International and Inter-University Center for Nanoscience and Nanotechnology, and a former Director of School of Chemical Science at MG University, Kottayam. He obtained his PhD in Polymer Science and Engineering from IIT Kharagpur. He is an outstanding leader with the sustained international acclaims for his work in polymer science and engineering, polymer nanocomposites, elastomers, polymer blends, interpenetrating polymer network, etc. Polymer membranes and green composites and nanocomposite is one of the major area he is working, and he contributed a lot in this field. And Professor Thomas has received a number of national and international awards, which include Fellowship of Royal Society of Chemistry, Distinguished Professorship from Joseph Stefan Institute, Slovenia Medal, CSI Medal, and Sukumar Mathi Award, etc. Professor Thomas has published over 6,000 pre-reviewed international research publications and many number of book chapters, and he's edited a very good number of books with international publishers like Springer, Elsevier, etc. He's basically co-edited 35 published books for the Royal Society, Wiley, Woodheads, Elsevier, CRC Press, Springer, etc. And he is the inventor of 4 patents, and his H-index is 67, and he have more than 17,000 citations, and he is constantly indexed in the top 2% scientists in the world by Stanford University and Elsevier. And Professor Sabu is delivered over 300 plenary or inaugural and invited lectures in national and international meetings over 30 countries. I cordially invite Professor Sabu to deliver his talk over here on the topic nanostructured polysaccharides based biomaterials for water purification. It is a very hot topic. It have a lot of potential to get clear water. It will be scarcity, still it is the scarcity in the to get the clear water. So now the floor is open for you, Professor Sabu. Please go ahead.
Thank you. Can you see my slide?
Yes, it is visible, yeah.
Very good. Thank you for the
I
kind
think
words.
now he is in the Russia, correct?
Thank you. Thank you so much for the kind introduction. And dear colleagues, friends, I'm delighted to be part of you today. Unfortunately, I cannot attend the meeting offline, so I'm online. The title of my presentation is Nanostructured Polysaccharides for Water Purification. You can see I represent 2 organizations. One is Mahatma Gandhi University, my parent university, where I did most of my academic work. And now I represent also Trivandrum Engineering Science and Research Park. Okay. Water is a very important commodity. And we all know that 75% of the Earth's surface is covered with water. But you see, water everywhere, but nary a drop to drink. That is the situation now, my dear friends. Although we have 75% of water in the ecosystem, 97.5% of this water is salt water. We cannot drink it. And you will finally find that less than 1% of the world's fresh water is accessible for direct human use. Therefore, it is extremely important that we need to have cheap water purification strategies for our humanity. Water purification is very important for the Indian context because our population is the highest in the world, the biggest in the world. Therefore, researchers all over the world, including India, trying to find out cost-effective water purification strategies for our rural people. I want to show you a water scarcity map of the United Nations. If you look at this map, you will find that in 2000, 92% of the region had relative sufficiency. Look at this color. This color indicates relative sufficiency. But you see what is going to happen in 2025, just 1 year more. This is going to drop to 62%. And in 2000s, 5% of the region are stressed. But you see in 2025, 31% of the region are going to be stressed, water stressed. Similarly, in 2000, look at the scarcity, only 3%. Now what is going to happen? 7%. And look at India. Most part of India has problem. Look at the color. Water stressed. Most part of India, all part of India, water stressed. Therefore, dear friends, this topic has great relevance. If you look at the current water purification strategies, we can classify them into chemical means, biological means, mechanical means, 3 categories. Today, dear friends, what I'm going to do is I'm going to talk about how membranes could be utilized for water purification. Membrane separation is one of the most efficient methods to remove contaminants from water. Because membranes are porous, you can have surface charge, you can control hydrophilicity, hydrophobicity characteristics. And you see some of the membranes made in my laboratory, they are all flexible membranes, mechanically robust, highly porous, good elongation, good flexibility, hydrophilic character. My co-workers made so many membranes which are hydrophilic. And dear friends, they are tolerant to wide range of pH values. And they also have good chlorine tolerance. You know why chlorine tolerance is required? Because our water is increasingly contaminated with chlorine quite a lot. Now, if I put all the water purification strategies, what we use now, I start with the microfiltration. Microfiltration can handle contaminants, big contaminants up to 1 micrometer range. Then you have ultrafiltration process, nanofiltration process. Reverse osmosis can remove everything from water. I put everything in this slide in a very nice cartoon. Look at microfiltration. This is microfiltration. Water is coming, this is microfiltration membrane. Microfiltration can remove E. coli, oil particles, big macromolecules, colloids, suspended particles. If you look at ultrafiltration, can remove viruses and proteins. Nanofiltration can remove very small components. Reverse osmosis, that is, we currently practice worldwide. Last week I was in Saudi Arabia. Saudi Arabia has a very big plant, series of plants, because they have the biggest plant on reverse osmosis. Look at reverse osmosis, a very energy intensive process, a very good technique to remove all the impurities, including ions. That is why after reverse osmosis, if you look at the drinking water you buy from the shop, you add ions are added. Why? Because these ions are required for our body. When you use reverse osmosis even catches ions in the water. Of course, this is a good technique. The problem is it's energy intensive to remove all the ions. Variety of membranes are being utilized for water purification. Polyvinylidene fluoride, polysulfone, polyether sulfone, polyacrylonitrile, nylons. A large number of membranes are being used. Polymeric membranes are used. Dear friends, I also want to tell you that when you use polymeric membrane or any membrane, when you use for water purification, it's a very important process called fouling. Look at what is fouling. Fouling is associated with absorption of the impurities, of the pollutants. It could be organic absorption, colloidal material absorption, it could be scaling, it could be biogrowth. You see, these membranes are polymeric membranes, but they are all deposited with a large number of contaminants. So you have to clean periodically, otherwise you cannot have efficient separation process. Today, dear friends, I'm going to talk about nanocellulose. It's a very exciting material, renewable material you can synthesize from the nature. Look at some of the nice nanocellulose membranes made by my research group. They're able to make nanocrystals and nanofibers. What's the difference between these two? If you look at nanocrystal, they're very small. The length could be 200 or 300 nanometer. Diameter could be 50 to 75 nanometer. But look at nanofibers, the nanofibers, long. Could be more than 1 micrometer. Diameter could be 50 to 100 or 25 to 100. So we are able to make both nanocrystals and nanofibers. In my laboratory, what we do is we use steam explosion process. We remove lignin and hemicellulose by chemical hydrolysis. You can see this is a steam explosion chamber. You suddenly release the pressure, then you have an explosion. This explosion opens up the cellulose structure, and you have hydrolysis of lignin hemicellulose. See what we do in my laboratory. My PhD students collect agricultural waste, wash them quite nicely. We go for an alkali treatment. We get a slurry. And this alkali treatment is basically to remove lignin hemicellulose. You get a slurry, you go for an acid hydrolysis, maybe mild acid or a strong acid. A strong acid will end up in nanocrystals. Mild acid will end up in long nanofibers. Homogenization, you see what you get. Suspension of nanofibers in water. If you take a drop of it and examine under high resolution electron microscope, you see what you see. Tangled structure of nanocellulose fibers. Now, dear friends, what I'm going to do is, I'm going to show you some of the work we did for water purification. My PhD student and I looked at the water purification membranes. If you look at the commercial water purification membranes, they're all barrier construction. The bottom part is non-woven. It could be polyacrylonitrile. It could be polyethylene oxide, The top part is PVDF. This is a PVDF one. This is electrospark. And we found that commercial membranes are not very efficient. So one of the examples I wanted to show you is dye removal using a membrane. So look at a company producing beautiful textile, but they use crystal violet dye for dyeing purpose. And you see the exhaust, the effluent coming out. The effluent has a lot of crystal violet. So if you look at this slide, we will find that my PhD student, with the support of Brazil, made a small reaction. We made nanocellulose. And then we reacted with the Meldrum's acid. You know why we did? To introduce CO minus group on the surface. You see CO minus group on the surface. And then we purified the water. So this is the absorption capacity of the crystal violet as a function of time. It's a commercial filter. The company was using such a filter, not very efficient. Look at the filter coated with the nanocellulose. This is a filter again coated with the modified nanocellulose with the CO minus group. This is very efficient. This is impure water, this is pure water. And you might ask why this modified nanocellulose showed very high degree of separation. The reason is very simple. See, this is the coated filter. Coating has been done by my group. It could be spray coating or dip coating. And after coating, when you do the filtration, all this crystal violet is stopped on the top surface of the filter. Why? Because electrostatic interaction. Look at this. Electrostatic interaction. Let me show you another example. Probably you all know that water is increasingly contaminated with suspended particles. It could be metal oxides or such particles. So one PhD student, what we did is we took the commercial filter, we coated with the nanocellulose spray coating. You see what happened. We made a model system in the laboratory. We took water and made the water dirty by adding iron oxide particle. 200 nanometer size iron oxide, black in color, completely opaque. We filtered this water. You see all the iron oxide is on the top surface. These are all iron oxide particles. After filtration, we got the clean water. Look at it, it's 100% transparent. And this is the bottom part of the filter. Okay? So we are able to remove suspended particle from water. Suspended particle could be removed from water. Let me now show you oils could be removed from water. Water is now increasingly contaminated with the oil worldwide. Sinking of ships, leakage from the ship. Seawater is increasingly contaminated. It's very dangerous for sea animals, fish, microorganisms. Look at the work done in this area. Look at this is nanocellulose aerogel. You make a dispersion of nanocellulose in water and go for freeze drying. Look at the aerogel. And then you make the surface of aerogel hydrophobic by DAY-2 coating. Something like 7 nanometer coating you give. And the surface becomes hydrophobic. When you put in water, what will happen? You sprinkle in water, all the oil, this is red color, will be taken up by the aerogel because surface is hydrophobic, oil is hydrophobic. And the aerogel swells. You choose out the oil and recycle it, reuse it. Or if you don't want the oil, you burn it. This technology is very powerful technology. And the oil absorption is so high because of the capillary action, the surface is hydrophobic. Let me show you another interesting one. Professor Roy and group, you know what they did? They made nanocellulose. And then by tempo oxidation process. You know, this is the nanocellulose made by Professor Roy and group. You know what they did? They introduced alkyl group on the surface of nanocellulose and made it hydrophobic. You see, these are the alkyl groups introduced by Professor Roy and group. And then coat on the filter paper. You see, this nanocellulose is coated on the filter paper. After coating, what happens to water? It becomes, water cannot get into it because it's hydrophobic. Become water resistant because you have coated with hydrophobic nanocellulose. If you don't coat, you see, it takes up all the water. You know what Professor Roy did? He took oil water mixture, put the nanocellulose coated water into it. This nanocellulose coated water can take all the oil because it's hydrophobic. Look at this. This is a very good technique to purify water. And you see, look at the number of cycles done by Professor Roy and group. Quite stable. Let me show you another work did from my group. My PhD student made aerogel. Very simple. You can do it aerogel manufacturing. Then he modified with saline. Why? To make the aerogel hydrophobic. And then he found that the crystal violet dye in the textile industry could be absorbed. Okay? And we could remove crystal violet dye. Dear friends, probably you all know that water is increasingly contaminated with heavy metals. Copper, lead, zinc, chromium, all this. So we can remove chromium. Look at this chromium absorption. Look at 90% absorption process. We can also remove nickel, cadmium, lead. All this stuff could be removed. Nickel removed, cadmium could be removed, lead could be removed. Probably some of you might remember that our great grandfathers, they used to make rice straw. My grandfather was purifying water. I remember when I was small, he used to purify water using rice straw because we had paddy field and he used to take the rice straw and purify. Look at the efficiency. It's not bad technique. You get 50% efficiency of removal of heavy metals. But if you go to nano, what happens? 95% efficiency, 99% efficiency. So my dear friends, the renewable material, nanocellulose that you get from the agricultural waste could be a very nice material for removing heavy metals. 90% absorption efficiency. Dear friends, we can remove bacteria and viruses. Bacteria causes a lot of trouble. Cholera, diarrhea, a lot of trouble. So what you do is you just take the commercial filter, coat with the nanocellulose, you remove bacteria. They are bigger in size, so size exclusion. The whole size bacteria is bigger, so easy to separate, no problem. But dear friends, viruses are very tricky. They're very small. We were all suffering from coronavirus for 3 years. They're very tiny. So if you want to remove viruses using nanocellulose, dear friends, you have to do small chemistry. You react with the polyvinylamine. Simple chemistry. You introduce amine group on the surface of nanocellulose, positive charge. And once you have this amine group, it can have some sort of electrostatic interaction with viruses. Viruses have a negative charge because protein envelope. So viruses could be removed. I want to show you the bacteria removal efficiency. Logarithmic reduction value 6, pretty good. Logarithmic reduction value of viruses greater than 4. So viruses and bacteria, they could be removed. I want to show you another important thing. Typical electrospun fibers, electrospun fibers are being extensively used for water purification. Typical electrospun fibers, like you look at this structure, this is polyacrylonitrile, the blue one. It's blue one. Mechanically very weak. What is the strength? 4 megapascal or 4.2 megapascal. But if you go to the nanocellulose, look at the strength. This is 1-step coating, this is 2-step coating. You can go to 14 megapascal, 13 megapascal. So coating with the nanocellulose has a lot of uses. One is the efficiency of the membrane goes up. Durability of the membrane goes up. Become mechanically strong. Let me show you another example. I had a very good student. He was very good in making nanochitin in my laboratory. And we did some nice work. You know, my collaborator in Europe was using PVDF membrane to remove indigo carmine dye, being used in textile industry. She was using PVDF, and you know, see the efficiency of separation. You got only 22.3% absorption. Not very, industry was not happy. And I said, why can't we hybridize PVDF and nanochitin? We mixed PVDF and nanochitin. We did a very nice electrospinning membrane. Look at the separation efficiency, 88.9%. So you can hybridize nanochitin, variety of polymeric membranes, and the efficiency can be enhanced. Dear friends, we are also working on emerging pollutants now. We are working on flame retardants, working on UV filters, more UV filters. We are working on pharmaceuticals. We are working on microplastics, nanoplastics. Also emerging pollutants using nanocellulose. And dear friends, we are also using biochar. Biochar is a wonderful material. So these are our future studies. I'm sure the next time I'll be able to show you some nice work. We make biochar from agromass. We burn them in a controlled fashion, and then we make beautiful carbon. And this is a fantastic material for water purification. So this work is started in my group. I'm sure next time I'll be able to show you some interesting results. We're also doing some plasma treatment for water in cooperation with Slovenia. My concluding remarks are the following. Cellulose offers lots of possibilities, particularly nanocellulose. We can remove many contaminants. The textile dyes we use for textile industry, bacteria and viruses, heavy metals, oil particles, so several contaminants could be removed. So our aim is to now make very cheap cartridges for our village people, rural India. That's my plan. We are actually writing some good proposals. So this is a very important slide to give hope for the water. I think a lot of youngsters should work with water, come out with very simple filters, which could be reused many number of times. I'd like to thank all my friends, collaborators across the globe, my PhD students, Professor Rao is greatly acknowledged, Professor Sina Rao, and all the funding agencies, and my collaborators in India and abroad. Dear friends, I'm the editor of Nanostructures and Nano Objects. Those who work on nano, please submit an article to this channel. We are still waiting for the impact factor. But size score is quite good size score, very close to 9. This is my group. You can see my colleague Nanda Kumar and my group in chemistry. Welcome to Mahatma Gandhi University campus. This is our campus. And we are doing very well. We are also ranked internationally by Times. We have a very good company in the campus, so we are taking up this process, nanocellulose manufacturing in a big way. MGU Translation, we have a company in the campus. This is called MGU Innovation Foundation. This is the MGU Innovation Foundation. Those who want to work with our company, you can contact me. You see how many companies, these are the companies working in our small units working in our company. Dear friends, I'm also in charge of the Science Park of Kerala, Trivandrum Engineering, Science and Technology Park of Trust Research Park. And you see, this is the Trust Research Park coming up in Trivandrum. Those who want to collaborate with us, please contact me. We have many, around 10 companies now, and we are going to expand this. You can see our proposed science park. Dear friends, we have a conference coming up, international conference on polymers, composites, nanocomposites, biocomposites from November 8, 9, and 10. India-Kazakh International Conference, the joint conference with Kazakhstan. We have also a conference in Trivandrum, that is startup ecosystem. Those who work on startups, please come to Trivandrum. Those who work on polymers and nano, fundamental work, applied work, come to Kochi. Thank you very much for your patient hearing. Thank you. Thank you.
Thank you very much to Professor Thomas for an excellent lecture on the water purification, different methodologies and materials to get, we can purify the contaminated water and oil water separation. And now the forum is open for the questionnaires and clarifications. And any clarification or questions, please raise up.
I'm very happy to answer.
Thank you, Professor Thomas, for this wonderful presentation. I have a question regarding the removal of dye, which you have shown from using this nanocellulose. So is it possible to simultaneously adsorb both cationic and anionic dye using this nanocellulose?
Thank you. Thank you then.
This is Paramita from Isar Bhopal.
Yes.
So is it possible to remove or adsorb the cationic and anionic dye both together using this nanocellulose?
Oh, sure. That is what we are going to work. You see, we are going to make layered construction where you can catch both anionic and cationic. We are able to make the cellulose positively charged cellulose layer, a negatively charged cellulose layer. Yeah, we have one shot. Our idea is to one shot to catch everything.
At the moment, because the cellulose surface is negatively charged because of the...
We can make it positive because of the... You're right, because of the sulfuric acid treatment. Acid treatment negatively charged. But if you react with amine, you can put amine group on the surface.
Right.
So we can engineer any type of surfaces.
Yes, so do some surface modification with some cationic polymer and then...
Sure, definitely. There's no doubt in that.
Thank you.
Our idea is single shot catch all these impurities.
Yes, definitely. Thank you so much, Professor Thomas, for this wonderful presentation.
Thank you. Bye-bye.
Hello, sir. This is Deepthi here. So just wanted to ask you about the typical thickness of these membranes that you utilize for such kind of filtration applications.
You see, what we have done is, we have taken commercial membrane. Commercial membrane is actually of varying thicknesses we can get in the market. Then we give a coating. The coating is very thin coating, few micron coating on the surface.
But suppose you are talking about electrospun membranes for this application, Just the electrospun membranes, do you think can be a replacement for the commercial?
Yeah. Yes. You see, if you look at the typical membrane, the bottom part is non-woven and the top layer is PVDF. Over the PVDF, we gave a coating. Yes.
Thank you.
Thank you.
Any more questions? So I have a small clarification needed. Basically, this you are using this nanocellulose or cellulosic material filters for the absorption of dyes from the, especially like from the textile industries. This textile industry is facing a very big problem, and my clarification needed is basically your material, your filter material what will be the efficiency? How much percentage of the dye can be absorbed from the contaminated water? Because there are in the Tamil Nadu, there are many textile industry. They are facing a serious issue, and they are in the they are forced to close down the industry because of this pollution of the dye. What they are doing, they are collecting this contaminated water and evaporating the certain amount of this water from that, and then storing it in the containers. So they have no more space to keep these containers. So that's they are facing serious issue. And if we could take up this issue to purify this, absorb all these dyes, then it will be a great contribution to the textile industry in India.
Very good, Dr. Prashant. Your comment is well taken. If you use nanocellulose-based membranes after coating, you can remove very close to 95% of the dyes. Sometimes you have to do repeated cycling process. First cycle, second cycle, third cycle, you can definitely remove it. And then you clean the membrane, you dissolve everything, and then you recycle the stuff, whatever sorbed on the membrane. So if you do repeated cycling, you can achieve very high level of separation. So we are actually working with some textile companies to make cheaper membranes for them. Yeah.
Okay. And one more thing, basically the oil-water separation, using this cellulosic material, how many cycles we can go with this cellulosic
material? 10
Okay.
cycle. Yeah.
Okay.
10 cycle. The only thing is, Dr. Prashant, the only thing is we have to give a good coating on the surface of nanocellulose. That you have to find out the cheapest coating, hydrophobic coating. Then you can take, and also the capillary reaction. Good level of absorption.
And what about when we are squeezing out this membrane for, removing the oil? Is it affect its surface morphology and porosity or pore morphology?
Yeah, when you squeeze it out, of course it affects the morphology. Some of the pores get, sometimes if you do it in a very aggressive manner, some of the pores might get damaged. Okay. But if you do a very systematic way, we can reuse it. 7 times we can reuse it, but the efficiency will be slightly less.
I was basically worked on this in this direction with Professor Puligalajan. That is we are made the porous aerogel kind of ceramic materials and absorbing.
Have you made nanocellulose or ceramic?
No, it's not the nanocellulose. It's a ceramic material. So we are absorbing this oil and then it is burning. Or
Or you squeeze it out.
If we could
dissolve with some solvent.
Yeah. Okay, thank you, Professor Thomas. And any more questions or any clarification from the audience? Students? Okay, then we are running out of little bit of time, and so I would like to move to the next session. Before that, I would like to congratulate and once again thank you very much for excellent talk over here. Thank you very much. Yeah.
Thank you.
So now we are moving to the concluding remarks of this plenary talks. We had 2 plenary talks from Professor Jacob and another one from Professor Thomas. And the first talk was on the microwave and RF plasma for the waste management, such as production of the nanomaterials, especially the graphene from the biomass and microplastic. The talk is very beautiful, and it is detailedly explained how we can produce scalable and high quality graphene from the microplastic or the waste materials. It is highly impressive talk which glimpses the conversion of microplastics to graphene by a simple method such as RF and microwave plasma technique. We are sure that this extra pure graphene have a potential application in energy storage, where we need extra pure graphene for the fabrication of the anode and cathode materials, especially in the lithium-ion batteries, which is now powering our all portable devices and stationary energy storage devices, and also the supercapacitors. Some glimpses on the properties and performance of this graphene. He is prepared from this microplastic is showed in his lecture. And this also applicable for the other applications like water purification, catalysis, hydrogen storage, etc. As Professor Jacob talking lots on effort on minimizing the issues of microplastics. It is a hot topic, and very few scientists in the globe is working in this direction. And I'm also working a little bit on the microplastic, but it's a lot of challenges, and the major challenge is basically collection of the microplastics. That is Professor Jacob is already mentioned. The microplastic is a very serious issue, and very recently, the couple of years back, it is find out in the fetal babies, and it is going to make a lot of health hazards. You can imagine how this microplastic, the plastic what we are using, we are simply throwing into the soil or the water bodies, and it is how it is coming to the fetal babies. Okay, so that much serious this issue, and Professor Jacob is working a little bit on this direction to minimize the environmental issues of this plastic microplastics. And we can give a big clap to Professor Jacob for his enlightening talk and taking a little bit step on this direction. Followed by the talk of the Dr. Jacob, Professor Thomas gave an insight on the nanostructured polysaccharides based biomaterials for the water purification, especially in the nanocellulose and cytosine based materials. And his talk delivered us a clear picture on the nanostructured cellulosic materials and this biomaterials and their processing and fabrication for the efficient absorbing materials for the dye absorption and other metal oxide nanoparticles like Fe2O3 and the absorption of the crystal violet dyes. It is again a very serious issue from the textile industry. And I would like to mention one of our faculty from the Department of Polymer Science and Rubber Technology, Kochi University. He's also working on this direction, and very recently he's developed a new method to the purification of the water from the nanocellulose and the wax bead. It is a completely natural material. The most of the water filters, there is a synthetic materials along with the natural material. But this particular filter, it is called as, he called as the nanocellulose nanofilter. That is completely on the natural material, basically this nanocellulose and wax bead. And this the paper is published in the ACS, and maybe it's have a good potential for the commercialization. So now we are, and I would like to thank you both of the plenary lectures, Professor Jacob and Professor Thomas, for giving a this excellent and enlightening plenary talks. So now we are moving to the next session, that is the keynote address. We have four talks. One is from Dr. Roy Joseph from the Sri Chitra Institute of Medical Science and Technology, Trivandrum. And the second one is from Dr. Pramita Das, Indian Institute of Science Education Research, Bhopal. And Professor Sujit from NIT Calicut, and Dr. Deepthi Menon from the Amrita Vishwavidyapitham, Kochi. The first talk is going to deliver by Dr. Roy Joseph. He is a scientist G, senior scientist grade at a biomedical technology wing of Sri Chitra Tirunal Institute of Medical Science and Technology, Thiruvananthapuram. He is received his PhD from University of London and the recipient of Commonwealth Scholarship. It is a very prestigious fellowship. And he was visiting scientist in the Interdisciplinary Research Center in Biomedical Materials, Queen's Mary University, London, UK, under the Indo-UK Higher Education Link Scheme. His research interests include processing and testing of polymers for biomedical applications, mechanical and dynamic testing of polymeric materials, polymer ceramic biomass composites, sustained drug delivery system, radio-opaque polymers for medical application, surface coatings on devices, hydrogel system, curcumin solubilization for medical applications, etc. He has 53 international peer-reviewed publications in the leading international journals and 6 patents to his credits. I would like to cordially invite Dr. Roy to deliver his talk on the topic Applications of Alginate in Modern Healthcare. Now the forum is open for you. Thank you.
Good afternoon. First of all, I thank organizers for the invitation and introducing me to the audience. I titled my topic as Applications of Alginate in Modern Healthcare because the topic and the seminar topic itself is biopolymers. So I thought probably I'll talk more about the bio-based materials. So we'll go to that. Right, first, before I start my presentation, let me introduce my institute. I work in Sri Chitra Institute of Medical Science and Technology, Trivandrum. It's a medical institution. We are focusing mainly on the translational research. We are less interested in the citations and high impact publications, rather than we focus on the translation of the research which is happening, because right from the beginning of the institute, our professor, founding director, said that our work, usually in other institutions, people stop their work with the publication, and he said, we will start our work with the publication. Okay, so where people stop, we will start. So with that vision, the institute started, and right from the beginning, we are focusing on the translational research. In 1980s, we translated some technologies to the industry, which is still, the products are in the market, blood bag and heart valve. And today morning, our minister was talking about biomedical industry. Actually, this biomedical industry, that concept was introduced by Sri Chitra in India, and it was growing, and Kerala has a good reputation in that area, just because the vision of our founding director, Dr. Variyathan. Okay, this is an institution of national importance. I think I find it difficult to stand and see the stage. Okay. And we have we are a national institute of national importance, and we have the status of a university, so we can give degrees, not only degrees in the super specialty areas. Okay, because this is a postgraduate institution, and we don't conduct any undergraduate programs, and we have medical degrees like DM, MCH, then MD. Then we also have public health master's programs. Then we also work in the device development areas, which is multidisciplinary, where we have chemistry, biology. Yeah, this is much better, so that I strain less. Okay. We have 3 units in for the institute, which is a tertiary care hospital, where we have cardiac and neuro specialties. Then we have a research wing called biomedical technology wing, which is about 10 kilometers from the hospital. Then we have a public health wing where we do all these health science research. We also conduct many research academic programs, mainly MD, DM. I mentioned about it. We recently started a program called the Integrated PhD program, which is for the people who are doing MD and DM degrees or MCH degrees in the cardiac and neuro specialties. Because this is the first time in India we started this integrated program. Then we also have PhD programs in chemical sciences, physical sciences, biomaterial sciences, medical science, health sciences, bioengineering, etc. So since I see a lot of students here, I thought probably I will share this information with you, so that in case if you would like to do work in the medical device development and associated areas, you are welcome to join us. And the advertisement is already out there. 21st is the last date for applying for PhD. So if you are interested, you can apply now. We also started a MDEC biomedical engineering program, where people will be specializing in medical devices, biomaterials, and applied biosciences. It just started now, this year. And I was talking about 2 technologies in the beginning. These first 2 technologies, which was developed in 1980s. Which now still it is, these products are in the market. First one is blood bag. You know, this technology was out in early 1980s, and so far 2 companies are producing this product in Trivandrum itself, and they are exporting to about 80 countries, and they produce about 70 million bags per year. And the entire world production of blood bags, that is 1/3 of the world production of blood bag, is happening in Trivandrum based on our technology. Then next thing is a TTK Chitra mechanical heart valve. This is another product. You know, imported valves cost more than 1.5 lakhs, but because we have our own technology, these valves are available in India at a cost of 41,000, and already 2 lakh people are living with this heart valve. So this is the and many more technologies are in the pipeline. Some have been transferred to industry, and we all work. Our focus is on medical device development and transfer technology. So this is our focus. So now I'll go to my work, which I would like to share with you. So I'll be talking about alginates today. When I exceed my time, Prashant, please let me, please warn me, okay? Otherwise I'll go on talking. Right. So polysaccharides. Alginates are basically polysaccharides, and this is a natural product extracted from giant seaweed or algae. There are species of algae from which we can extract this product. These are some of the examples. Giant kelp, which is a principal source of alginate. And this is one interesting thing about this particular seaweed or algae is it is the fastest growing plant on earth. It grows about 30 centimeters per day. So this is a major source of alginate. And other thing is weed. Again, that is another source of alginate. And chemistry, if you look at the chemistry of alginate, this is a copolymer. It's a copolymer of L-glucuronic acid and D-manuronic acid. Generally, it is called polyuronic acid. And the structure is shown here, and we have in that polymer, natural polymer, there are glucuronic acid blocks and maluronic acid blocks and combined blocks of glucuronic acid and maluronic acid. And the molecular weight is in the range 35,000 to 1.5 lakhs. Okay, commercially, this actually we consume a lot of alginates. Do you know about it? See, if you consume ice cream, we are eating alginates. Okay, then in many water treatment plants, this has been used. Then a thickening agents in the food and pharmaceutical industry. And when you eat bread, again you are consuming alginate. So then in the medical applications, this is used as a hemostat. That means when you hemostat means the moment it comes in contact with the blood will clot. That is called hemostat. So it is used as hemostats. Again, it is used in the tablets and lozenges. Okay, I'll be talking about some of the applications of hydrogel in medical applications which I've been working. Okay, hydrogels are very important material because this hydrogel resembles our cells. You know that our cells contain more than 80% of water. So hydrogels can absorb this much of water and it simulates the features of the cells. So body really like hydrogel materials. So these are actually porous materials, and cells can grow into these materials, and if it is biodegradable, it is really useful. So alginates and hydrogels derived from these alginates are really useful. And in my work, most of the cases, I convert alginate into dialdehyde form of the alginate. This is usually done by a chemical reaction with sodium metaperidate. And this oxidation product will be dialyzed, and you can get the alginate dialdehyde. So you can see the double bonds. Oh, sorry. Okay, the point is not working. Okay. Right, so the chemical structure is shown here. This is alginate dialdehyde. This aldehyde group is actually reactive. So you can use it for further reaction with other materials. Okay, so when you oxidize this alginate, the molecular weight will decrease depending upon the degree of oxidation. And the more degree of oxidation, the less will be the molecular size. And this way you can control the viscosity of the material also. Then the oxidation product is again biocompatible, and we can it's biodegradable also. And one good advantage with this is it can react with the gelatin. Gelatin has amino groups, and this aldehyde and amino groups react easily, so that you can have hydrogels. Okay, so this is gelatin. So this is the type of reaction which is happening. Okay. So here we have this amino group of gelatin, and this aldehyde group of alginate dialdehyde, which will cross-link, and you can get the hydrogel. This is a reaction happening. And again, if you want to have different, this can be used as an injectable system. Okay, so depending upon the ratios of alginate, dialdehyde and gelatin, you can use it as an injectable system with a setting time ranging from 1.5 minutes to 90 minutes. So this can be adjusted by adjusting the ratio. And again, this can be controlled further by adding a catalyst called borax. Depending upon the concentration, you can adjust a wide range of applications, the setting time. So in the clinical applications, usually doctors prefer to have a setting time or working time to setting time range about 4 to 5 minutes. In that time, it should be able to set. That is usually mainly used for injectable applications. And coming to that, so again, swelling ratio, this is one important parameter. It can retain this much of water in it. And now I am going to an application side. It is called meniscal tissue engineering. So what is meniscal tissue? So this is the meniscus. Okay, this meniscus is actually enable us to stand straight, depending upon the again it is giving you flexibility and a shock absorbing capability, etc. And in some cases, especially for the athletes, there's too much of running and sudden training actually causes damage to the meniscus. In such cases, they either go for surgery or repair. Okay, this is the section of this is the shape of this meniscus. You can see, and the meniscus is actually work as a joint filler. It is also acting as a lubricant, shock absorber, and it gives stability to the knee. So this is a video which is not working. Okay, this is a type of damages which can occur in the case of meniscus. So this is minor damage, but these kind of damage are very difficult to repair, so they do the surgery. But this kind of damage can be repaired by stitching or by injecting some kind of hydrogel materials. So I'll just go. This is the way they inject. You can see that they take an injectable system, and this is the easiest and quick way of healing the injury. So they inject hydrogel material, where they can also add therapeutics like growth factors or drugs. Again, they can add cells into the hydrogel material so that the healing will be very fast. I developed a injectable system, and this is the approach which we used. Basically, it was formulated to have a working time of 4 to 5 minutes. Then we did the characterization, in vitro biocompatibility, in vivo and in vitro biocompatibility testing, and did the preclinical studies in a rabbit model. Okay, so as I said, the clinically relevant working time is 4 to 5 minutes. This is what clinicians wanted. So we formulate in such a way that it will set within 4 to 5 minutes. Okay, one good thing about this is you just mix it in the syringe. You can take one component, alginate dialdehyde, then next other component, gelatin, both in a solution form. Then mix it in a syringe. Then you inject into the injury site. So again, depending upon the borax content, you can adjust the working time and setting time. You can see that gelation time is 16 minutes to almost 2 minutes or 1.5 minutes by adjusting the concentration of borax. You can see this is gel inverted. This is one way of seeing the gelation. Okay, so this is very easy. You just mix both things together, put it in saline. This is saline. Then invert it. You can see that what is the working time and setting time. So again, in rheological, there are machines we call rheometers that can be used for sophisticated measurements, but both are acceptable. And again, some characterization we do. I am not going into much detail of that. Basically, it's a shift-based formation. So this is the indication that this is alginate dialdehyde and this is gelatin. This is indication that is cross-link is formed in that. Then I told it's a hydrogel. Hydrogel is a porous material. It can retain more than 90% of water into the system. So if you dry it and lyophilize it and see into the under microscope, you can see that these are all porous materials. These pores are very important because these pores, through these pores, tissues can cells can grow, and it can form a tissue. So that is called a tissue engineering. Okay, so you allow cells to grow and form a tissue, and this will actually, once the tissue formation is complete, this hydrogel matrix, or we call it scaffold. This scaffold will degrade and disappear, and the degradation products will be absorbed by the body itself. So this is the way this concept work. So next, once the initial characterization and the toxicology studies are over, then we will be going for the preclinical studies in an animal model. So here, we took the rabbit as a animal model. And you can see that rabbit knee is exposed. You can see the meniscal tissue exposed here. Then we made a injury here, okay, using a scalpel. That injury site, at that site you inject the hydrogel. In this case, we have a control material. Control means without hydrogel, you just keep it, stitch it back. And in the second case, which is actually test material, you inject the hydrogel, then stitch it back. And we also added some growth factors into that. So that is, growth factors are isolated from the blood, and you add that growth factors also into the hydrogel, then stitch it. So after suturing, you can see, then allow the animal to 1 month time you give for the recovery of the animal. Then okay, so then you sacrifice the animal. Okay, so this is the way it is. This is the native meniscus. That means before the injury. Okay, we do this. I think the resolution is not that good. So here you can see the control. That means without injecting the hydrogel material. Here you inject the hydrogel material, and this is the one with the growth factor called collected from the blood called platelet-rich plasma. Okay, so after different time periods, this is you do the histopathologic analysis. You retrieve the sample and do the histopathology analysis to see what is really happening by staining it. Okay, so there are different stains available. With the different stains, you do stain the tissue, then you see under microscope. You can see this is a control. That means without any hydrogel, you did this staining, and you after 1 month, what is happening? Okay, you can see that the injury site is not joined or fused together. Okay, so different staining. But this is a hydrogel material. You can see that it is fairly healed. But again, you can see some kind of incomplete healing. All right. So here you can see again. But in this particular case with the growth factors, the healing is very good. It is almost like a native native meniscus. Again, this is data collected after 3 months. In 3 months' time, most of this control, again, you can see the lines, fused lines, okay? But in the case of hydrogel, it is almost like a native tissue. That means hydrogel really helps in healing the wound, injury or wound. So, but with the growth factors, the healing rate is very fast. In 1 month itself, we have complete healing happening. But with hydrogel, complete healing is happening in 3 months' time. But with the control, there is incomplete healing. So we can see that hydrogel is really helping faster recovery of the patient. Okay, in all our research, we always include a clinician, because clinicians' input is really important. What really happens is many of the places people don't involve, researchers will have fantastic idea. But once you develop all these things, when you go to a clinician will say, this is not the one we wanted. So this happens many times. So we have a hospital, we always associate with the clinicians and ask their inputs. So clinicians will always have suggestions about how the device should be performing, how it should be, how it is used. So all these inputs we get from the clinicians. So we will have frequent interactions and meetings with the clinicians while the development process happening, so that at the final stage, we will have the correct product which will be accepted by the clinician. So we also, in our team, we always have students, then clinical advisors, then again, this is an animal experiment, so we need a veterinary doctor. We always have diverse range of people We have material scientists, we will have engineers, we will have veterinary doctors, we will have clinicians. All these teams, people will work together as a team so that the final product will be a success. Then I am going to quickly on the 3D bioprinting of tissues and organs. So this is a new technique which has been emerging, and now people are telling about developing organs in the laboratory itself and implanting in the patient. So this is and just quickly go through these slides because my time is very limited. So this is one of the major breakthroughs happened in the tissue engineering or 3D bioprinted tissue engineering. You can see a bladder, urinary bladder, bioprinted in the laboratory and implanted in the patient. This is happened in the US in 2011. All right. So again, they also developed a kidney from human cells. So this research is happening everywhere in the world, but they were the pioneers. Then one important thing about one important material which you recover in 3D bioprinting is bio-ink. Bio-ink is actually a hydrogel material with cells and growth factors and any other required things like drugs or something. But usually they have cells and growth factors. This is actually used to grow the organ in the laboratory. Okay, this is the way it is represented. You have cells, then you have polymers. These polymers need to be cross-linked, so you'll have a cross-linking agent into that. Then you have a three-dimensional network once it is cross-linked. So this is the medium in which the tissues will grow, or cells will grow into tissues. So this will be done in the laboratory, and later this once the organ is developed, it will be implanted into the patient. So this is giving a schematic representation where you print layer by layer, then you allow it to grow into an organ. Okay, actually this is a video but it doesn't work. The printing. Okay, we developed a 7-layer construct. This is actually been developed for a construct for liver. Then time is up, right? Okay, I quickly go to one more device which we developed, vascular graft. This is ballooning of an artery, okay, aorta, and this is happening in people with who smokes a lot. Okay, so this in the when you have this kind of disease, what happens is, in case it breaks, then the person will die, the patient will die. So this is called, that clinical condition is called aneurysm. Aneurysm is blood vessels growing like a balloon and breaking. So what doctors usually do is put a vascular graft, and this is the surgical procedure. You remove that particular aneurized area, then put a plastic tube, which is called a vascular graft. I just go through. This is the process of making vascular graft. You have first in the textile industry, they make a lay flat tubing. They'll be crimped into a graft. Then what I did was I applied a coating onto the vascular graft. So this is basically again an arginine dialdehyde and gelatin system. You can see this is applied because since it is a porous material, if it is a porous material, blood will ooze out through the walls of the vascular graft. This has to be prevented. That's why this coating was applied. So we did it in animal pig. This was implanted in a pig model. This is we have an operation theater for doing animal surgeries. This is the native vascular native aorta exposed by the clinician. Remove the aorta. Then we put our vascular graft there. You can see the surgical procedure. I'll just quickly go through that. Okay, so this is the graft which is coated with the hydrogel. Okay, right. We did angiogram to see whether this is working and it is in place or any leakage of blood through that. It was not there. Animal is recovering. This is explanted after 2 weeks. And again, you can see angiogram. You have taken out the graft. Then you see there is no blood clot. It's all clean. If you look at the CM, you can see tissues are growing inside. This is after 3 months, and control and test are given. Control is actually a commercial graft. Okay. So you can see that neointima, these tissues are formed inside. We call it neointima. It is formed and is sealed. Again, and we did the histopathologic analysis, and we found that the entire hydrogel coated on the surface was resorbed over the period of 6 months. This is my team. Thank you so much.
Thank you, Dr. Roy, for this excellent lecture on this alginate material in the medical application. And as he discussed here, alginate is a very important material, biomaterial, have a great potential in the biomedical application. And now, give him a good clap. Now, if you have any questions or clarification, please, now the forum is open.
Yes, Professor, it's excellent talk, and that too, you have done extensive work, especially, coming to this bioprinting. I think you have initiated and it's going on. Yeah. So I don't have much doubts, but I needed some clarification. Like, we are also working on bioprinting. Okay, so especially on bone implants, skin regeneration, and corneal patches, we are developing. So we have done up to in vivo studies. How to approach for clinical trials. We are in confusion. So if you give some light on it, then I think it will be helpful for our
Did you try in the animal models?
Yes. Skin patches we have completed in association with some veterinary university, Sri Venkateswara Veterinary University, and they have done the studies for our skin patches, animal studies, and as well as for cranial burr hole plugs also we have developed, and those things we have done with them.
Now, usually this was done with the ethics committee approval. You need to have an ethics committee.
Yeah.
And you need to identify a clinician to do these things, and you need to recruit patients. Actually, clinical trials are not that cheap. It is an expensive thing. So you need to have some funding. I would really suggest to have a industrial collaboration in this particular area.
Okay.
And with this help of the industry, you do that. Otherwise, if you are interested to transfer the technology to the industry, what happens is if you do it, this material development in your facility, they have to repeat the entire process in their own facility.
Yeah.
So ideally, at this stage, you transfer the technology and work with the industry and do the clinical trials. And there is BIRAC and many funding agencies are there now, support these clinical trials.
Okay. Thank you.
Thank you.
Thank you for a nice question. And
Dr. Deepthi is also working
Deepthi
in a similar area.
Is
so
quite, excited to ask many questions. So far, she is working in the biomedical. I expect many questions. Thank you.
No, I don't have many questions. I just wanted to know what is the typical thickness of the coating that you have given to the
Actually, the
vascular?
thinner, the better.
But how do you actually
Usually-
estimate the thickness?
Actually, the coating process, this is a crimped material with wavy nature.
Yeah.
So when I was doing the coating, we usually spend some 1 minute time, and in that time the solution concentration is adjusted in such a way that this will have thin coating. The coating thickness which we had was about 30 to 60 microns.
How did you measure that, sir?
You can cut it and see.
Okay.
Yeah.
Uniformly you get
Yeah, right. It is not uniform, and what I am saying is this wavy this particular graft has a wavy nature, So where there is, in one area you have a thickness maximum, about 60 microns. In the other area it is 30 microns. So this was the variations. But this in this particular case, we were putting in water first before implantation. So this hydrogel is almost like a rubbery material. So the stretching and bending would not actually debond the material. But if you do it in the dry condition, it will detach. So this was what we did, and we measured, and it was about 30 to 60 microns. That's the variation we had. Thinner the coating, better. If you it's more and more thick, means it is deboned and peel off.
Okay. Any other questions? So I have a small doubt. Basically, the alginate is you are getting from the different sources, right? So how you could make sure the uniformity in the properties for this particular medical application?
No, usually medical grade alginates are there.
Okay.
So again, whatever the material you get, we initially do the analysis. So we can do some cell culture studies and find out whether it is toxic or not. So raw material characterization is very important when we think about medical devices. So the best grade you need to collect, then do all the analysis first before you start modifying it and use it for medical applications.
So the source is not that much important, right?
Source is important, but if you choose medical grade, then usually it will be safer.
Okay. Thank you, Dr. Roy, for this enlightening talk.
I'm inviting Dr. Prashant sir to present a memento to Roy sir.
So now we are moving out to the next session. Next lecture that is going to delivered by Dr. Paramita Das. Dr. Paramita Das is received her PhD with a magna cum laude award from RWTH Aachen University, Germany, 2016. And after that, she did her postdoctoral studies in NTU, Singapore, and DTU, Denmark. After that, she is joined as the faculty in Indian Institute of Science Education Research, Bhopal, in 2018. She obtained her MTech and BTech degree in Polymer Science and Technology from IIT Delhi in 2011 and Calcutta University in 2009, respectively. She also completed her BSc in Chemistry from Calcutta University in 2006. She has more than 10 years of research experience in the field of colloidal self-assembly and functional nanocomposites. And she's published about 24 peer-reviewed international publications in the high impact factor journals, and one book and 10 book chapters into her credits. She has received 13 invited talks in many international conferences. She is a life member of Polymer Processing Academy India, the Society of Polymer Science India, the Indian Science Congress the Indian Science Congress Association India, Indian Institute of Chemical Engineers, etc. She received the Young Women Researcher Award in Polymer Science and Technology by Venus International Foundation in 2024. She is selected as a member of Indian National Young Academy of Science at INSA New Delhi 2024. I'm cordially inviting Dr. Paramita Das to deliver her talk.
Okay, thank you, Professor Prasanna, for this nice introduction. And I would like to thank the organizers for this invitation. So today I will talk about some of the research work which we have done on cellulose nanocrystals. So I'm going to talk about cellulose nanocrystals as novel sustainable nanomaterials for functional nanocomposites. So I'm from the Department of Chemical Engineering, Indian Institute of Science Education Research, Bhopal. And there in my group works on functional nanocomposites. So we design a little bit about what we work. So we design and develop novel polymeric nanocomposite materials incorporated with functional properties like gas and water barrier property, flame retardancy, proton transport, adsorption sensing, control release, etc., while maintaining beneficial material properties like we work on low density material, high performance like high performance materials having mechanical synergy and sustainability. So we work on polymer composites, nanocomposites, nanocellulose based material for environmental sustainability, waste to wealth, and slow release hydrogel fertilizer for smart agriculture, fuel cell membranes, and packaging materials. So in today's talk, I will briefly discuss about like the extraction of CNC from different biomass waste, and using that cellulose nanocrystal as a functional nanofiller, how we can develop a robust bioinspired nanocomposites, and in terms of functionality, we can prepare UV shield packaging films and flexible packaging. And using the cellulose, we can also use some adsorptive composite membranes. So here, most of the audiences having this polymer engineering background. So we all know that in our day-to-day life, we use most of the materials made of plastic. And then if you see this global plastic production data by industry sector in 2015, so around 400 million tons of plastics is produced every year, and out of that, approximately 36% plastics are used as a packaging material, single-use packaging material by the packaging industry. And these are basically designed for immediate disposal after use. So as we dispose, it leads to environmental pollution. So there is a global environmental concern due to plastic burden and the impact on health and environment. In a recent report by the Organization for Economic Cooperation and Development, that by 2060, the amount of plastic waste is going to be almost triple. And majority of this waste will come from the short-lived items such as packaging, low-cost products, and textiles. So as a possible solution towards sustainability, as a polymer engineer, what we do is this is some of the possible solutions towards sustainability is that replace the conventional dense plastic materials with lightweight and high performance materials, use some green synthesis procedure, or use the building blocks from sustainable sources, and use utilizing waste material and applying them in suitable application in an effective manner. So thinking all these possibilities in mind, our research group worked towards sustainable, mechanically robust, and functional materials. So we keep these parameters in mind that we are working, we are developing advanced nanocomposites to promote sustainability, and these nanocomposites should be lightweight material, should show some synergistic mechanical properties. By meaning synergistic means, we should have good strength, good stiffness, as well as good toughness. So all three combination of properties in the material. Because most of the time when we prepare composites, we see that either we improve the strength, then we are compromising with the percentage elongation,
or stiffness. Or if we have a better stiffness, then we have a lesser ductility. So how we can have all these properties together in one material? And then materials using building blocks for sustainable resources and using eco-friendly production procedures, focusing on energy efficient technique, synthesis procedure using room temperature and using green solvents. And we are now focusing on some of the SDGs developed by these United Nations, like SDG 6, 12, 14, and 15. So in developing towards these sustainable and high-performance materials, functional materials, we draw a lot of inspiration from the natural material. Here you can see some of the natural materials, like butterfly, it shows nice photonic colors, gecko, it shows physical adhesion, it can stuck to any surface, like mussel. This shows chemical adhesion, lotus leaf shows cell cleaning behavior, and nacre, it's a seashell, it shows outstanding mechanical properties, and then wood, and then crustaceans, the crabs and spider cells. These are the examples which shows outstanding mechanical properties because of their structural hierarchy. You know, all these materials are made of very simple constituents like calcium carbonate, some proteins and chitins. But how they grow, all these simple building blocks grow via self-organization into a hierarchical structure. So at different length scales, from nanometer to micrometer to centimeter. So from nano to meso scale, they showed structural hierarchy. And all these materials have higher amount of reinforcement engines. That's why it's called highly reinforced materials. And their properties are controlled by interfaces, because we have polymer, then soft phase, and then we have a lot of reinforcement. So there are a lot of interfaces present in such materials. So the interfaces and the interaction between the matrix and the pillar should be good enough so that these materials can have a stable interface and can exert very good mechanical properties. So here I'm showing one example. So we have all worked a lot on nacre. Now we are focusing on this crustacean cell. So if we see the skin of these exoskeletals, these are basically prepared by chitin molecules. Some of the chitin molecules, if we see in the Armstrong level, and then if we zoom out, this chitin molecules arranged in an anti-parallel fashion get this chitin nanofibrils. Then these chitin nanofibrils, with the help of some proteins, form these chitin protein fibers. And then these chitin protein fibers arranged in a helical manner, it's called the Boligan structure. So these composites are basically, this is the final stage. These composites have this higher order structure, which shows this helical structure like this. If it takes a 360-degree turn, it's called a complete pitch, and 180-degree turn, so it's a half pitch, and it's a twisted plywood or Boligan structure. Okay, so this is also seen in DNA. It's a helical strand is there. Not only that, if you see, check from their outer skin, from epicuticle to exo to endo, we see that there is a variation in the stacking of these fibers. So, and also in our in tooth, if we see the dentin and enamel, there is also some gradation we can see. So this gradation can be either in terms of composition, in terms of density, in terms of porosity. So if you see bamboo has different porosity from its outer skin to the inner skin. So this is called the functional gradient material. This kind of material present in nature, and it improves the mechanical property, it improves the toughness of the material, and you can, because of their gradient distribution of materials along the spatial direction. So in this presentation, I will talk about, show that how we can use cellulose nanocrystal to get this kind of structure. And we can, using that structure, we can get very improved mechanical properties. So cellulose nanocrystals, Professor Thomas talked about nanocellulose already, and he showed the use of nanocellulose in terms of water purification. So nanocellulose, these are very interesting material. I will say these are very gold standard material because, first of all, these are renewable. These has high aspect ratio. Aspect ratio means length to the diameter ratio. And they have a rich surface functionalities. And And this tensile strength, very high mechanical properties. The tensile strength is like 10 gigapascal, and Young modulus is like 150 gigapascal. Yet these are very light, low density material. 1.6 gram per centimeter cube is the density of cellulose nanocrystals. And because of their, and they are very basically twisted rod-like. They have this twisted rod-like structure. So because of, and on its surface, it has a surface charge, anisotropic surface charge distribution. So depending on like how we synthesize them, of course, by acid hydrolysis, which acid we take, whether we take sulfuric acid hydrolysis or we take hydrochloric acid or nitric acid, depending on that, several surface groups can be present on cellulose nanocrystals. But of course, majority it has this surface hydroxyl groups. And these surface hydroxyl groups can further be used for surface modification to bring some more surface characteristics on CNC for targeted application. So, and because of this anisotropic charge distribution and twisted rod-like structure, when you take this CNC dispersion and you evaporate the water, it starts to form this kind of helical structure. And this is the thin film which we prepare from cellulose nanocrystals, and this is the cross-section of the film and the SCM images you see. You can see this helical plywood structure, which is also similar to what we see in case of crabs. So, so this is very interesting material, and we can get this to a polygon structure from CNC. But this is a filler, and if we prepare the film also, we cannot use it in real application because this is very fragile. This is too brittle. So to make this useful in real application, we need to use some binder, some polymer. Okay, so that's how the concept of CNC-based composite comes. So here I am showing first some extraction process. So we use different sources. For example, orange peel, paper, office paper waste, rice straw, and all this biomass waste. These are from like all cellulose-based waste. These has, on the cell wall, we have these cellulose fibers, and we followed the same, this process like alkylation to remove the hemicellulose, and then bleaching to remove the, lignin and remaining part of the hemicellulose to get like from bundle of cellulose microfibers to cellulose nano or microfibers, and finally we do the acid hydrolysis to get the cellulose nanocrystals. Okay, now, and also we use the Wattman filter paper. That is as a control use, Wattman filter paper. This is the most purified form. So if we put it in a water, or it gives a pulp. So from there also, for when we use the Wattman filter paper, we don't do these steps because these are already done because it's a cellulose pulp. We just do the acid treatment to get the CNC. Now, here we use a facile mechanochemical extraction technique because in literature, if we see, people use this alkylation, then bleaching, then acid hydrolysis, but we have to do this, repeat these steps multiple times, and also some modification needs to be done depending on what is the source of extraction of CNC. Here we have used these 4 different types of, let's say these 3 different biomass sources, but we work on the process parameters, and we use a probe sonication assisted chemical extraction technique. This gives us, like this saves the use of chemical use, processing temperature, and repetition of steps. Because this probe sonication helps us to defragulate these fibers, and we closely monitor how the changes happens in a molecular level by doing the SCM images after each steps. So, and then we also check the width, how the width is changing as we go from alkylation, then sonication, then bleaching, then again sonication, and finally the acid hydrolysis. We have found that from different sources, the cellulose fibers which we get, basically this orange peel, this shows nice fibrils, and then from SCM, these are the SCM images of the CNC, and these are the TM images of the CNC. We calculate their aspect ratio. So we calculate the length and the width of the cellulose nanocrystals obtained from different sources, and this is the aspect ratio we calculated. And also we check their surface zeta potential and crystallinity. So we see that the CNC we obtain by this process gives us very good crystallinity, high crystallinity, and this is the, of course, this is the higher crystallinity obtained from the Wattman filter paper because this is the most, this is in the pure form. And This CNC also shows very good birefringence property. When we keep this CNC solution in between two plane polarized paper, we see these nice colors coming from its liquid crystallinity. And when we take 38%, it shows this liquid crystallinity. It arranged in a ordered fashion, and in between this plain polarized paper, we see this birefringence color. And also the color changes because of the aspect ratio. And also this CNC shows very good rheological properties. CNC shows shear thinning behavior. And also, if we increase the concentration in 100% dispersion, we see shear thinning and the viscosity. And of course, if we increase the concentration, viscosity increases. But if we see, compare their aspect ratio, higher aspect ratio CNC shows higher viscosity and higher shear thinning behavior, and also higher storage modulus. So these are all known facts for the fibers, but from cellulose nanocrystals morphology also we see this kind of observation. Then we use this CNC extracted from different biomass to see their composite property. To see their composite property. I don't know, that slide is not working. Okay, so what we have done here, this is the cellulose nanocrystals we prepared. This is the TM images of the cellulose nanocrystals. And here we use the surface functionality of this CNC. As I said, it has a lot of surface functional groups. We use the surface functionality of this CNC. We modify them with polydopamine. Okay, so polydopamine, we use a dopamine and we use a trees buffer and do the polymerization. It's a cell polymerization. And we modify the surface. This polydopamine has inherently black color. That's why the dispersion turns to black. And here from the TM images, you see some gray color coating along the CNC rod. This shows that that coating of dopamine is done around the CNC. Why we use polydopamine coating? Because polydopamine is also a natural polymer. It's a biopolymer, mucil-inspired polymer, and it has a very good adhesion. And if we, as I said, if we want to mimic the bio-inspired materials, the interface should be strong. So if we use the CNC, we modify it with polydopamine, we anticipate that we'll get a better interaction between the matrix polymer and the filler, which is the CNC. So this we call, so first we modify the CNC with the polydopamine and we vary the polymerization time to see how much coating we need. From AFM analysis, we see that, okay, as we increase the polydopamine coating polymerization time, the width increases, the width of the CNC increases, and also from elemental analysis, we see as we increase the polymerization time, the PDA content, the polydopamine content increases on the CNC. Again, from XRD, we confirm that the crystallinity peak, the crystalline nature, inherent crystalline nature of CNC doesn't change after modification of, so this modification takes place only on the surface. The internal structure remains stable. Only the percentage crystallinity decreases a little bit because PDA is an amorphous polymer. So it decreases the crystallinity a little bit. Then from the FTR and from XPS, we confirm that the polydopamine modification takes place because in the DCNC, that is the polydopamine modified CNC, we get this nitrogen peak. This is present in dopamine, amine functionality, but in CNC, we don't get any nitrogen peak. So this also confirms that polydopamine modification has been done successfully on CNC. Then after we confirm this polydopamine modification, we need to optimize which polymerization time we need to use. For that, now we prepare the composite with taking a free polymer, the matrix, which is the carboxymethyl cellulose, again a biopolymer. And we prepared the carboxymethyl cellulose CNC binary composite as for comparison. And also we prepared the cellulose CMC DCNC ternary composite. Why we call ternary? Because we have a free polymer, that is the carboxymethyl cellulose. We have CNC, which is the filler, and also we have a surface modifier, which is the polydopamine. So it's a 3-component system. So we call it a ternary composites. And we take this DCNC and we mix it with the CMC in a controlled manner to ensure that we have a polymer coated on this nanoparticles and form these core shell type particles. We remove we take in a composition of 50-50. Then we evaporate the water and we get a solution casted. The film is prepared by solution casting, which is followed by evaporation into self-assembly. And this is the cross-section of the film where you can see the CNC, the rod-like structure is protruding from the cross-section of the. So then we check the mechanical property. Here we see this is the mechanical property of the CMC. This is done at 50% relative humidity. The binary composite, the CNC 50-50 feed ratio, it shows mechanical property around 130 megapascal. But if we do the surface modification, we see there is an enhancement in mechanical property. And from like 6, 12, 24, 48, this stands for the polymerization time of the dopamine on CNC. So here we see that if we go for 48-hour polymerization, the material becomes very brittle. So we optimize the polymerization of dopamine at 24 hours. And the material which we get, the composite, it shows very high strength, 154 megapascal, stiffness is 10 gigapascal, and toughness is 5 megajoule per meter cube. So, and also these are waterborne materials, so everything is hydrophilic and made from water. So there is a chance that the mechanical property will deteriorate if we check the mechanical property at higher humidity. So when we check this mechanical property at almost like low humidity and high humidity, we see that mechanical property drops for a binary composite, but for the ternary composite, the surface modification gives us better interfacial interaction between the polymetric CMC and the filler, so it gives us a very good strength. It retains its mechanical property. And further, we check, 2 minutes? Okay. So further, then we had this 50-50 ratio. Now we want to see if we increase the feed ratio, what will happen. So we increase the feed ratio from 50-50 to 20-80. And here, 80 means we have increase the CNC amount. And because we are using polydopamine, it has this functionality. It has UV shielding property and radical scavenging property. So, this we checked in the polymer. So we see the cross-section after preparing the film. We see the cross-section. This shows this chiral nematic kind of structure which we see for the crabs, and this chiral nematic structure is visible more when we increase the CNC amount. And we also calculate the pitch from our material. This material shows very high mechanical properties, and these properties when we compare with the CNC-based other material, these are so far the best reported mechanical values which we get. Even at high humidity, the ternary nanocomposite retains their very good mechanical properties. Then we checked because of this polydopamine modification, it shows very good UV absorbance both in UVB and UVB and UVA region, and also because of interfacial interaction, we get a thermal stability, higher thermal stability, low water vapor property, low water vapor transmission, and very good radical scavenging property. And prolonged stability also in water. So these are ternary film. This is the binary film which gets dissolved in water after a few hours. And these are also biodegradable, which we tested in soil burial test. So all these properties are very interesting and desirable for packaging. So then we use this for UV shield packaging. We take a fruit piece, we irradiate it with UV lamp. So where there is no this is the bare sample, it shows that degradation happens due to UV irradiation. But when we have this binary, the CNC film, then also we see the degradation happens. But when we take this ternary CNC films, even if we irradiate for 60 minutes, we don't see much degradation, no discoloration. Even after 24 hours, we don't see much change in the color. So this film shows very good UV shield packaging films. Do I have time? 1, 2 minutes?
If you could finish it in 1 minute, that will be great.
Okay. Just very quickly. So this was done in water-based polymer. Then we take PLA. PLA is widely used for packaging, but PLA is hydrophobic. So we modify this CNC with APTS to increase the compatibility with PLA. And here we use a gradient architecture, which I show, the compositional gradient architecture. So from PLA, we take another layer, PLA, CNC 1%, then another layer, PLA, CNC 3%, 5%. So this way we increase the composition. And we see that, we see this is the gradient composite, and this is the non-gradient. Here we have PLA, 1% with 1% CNC loading, 3%, 5%. But in the gradient also we see at different zones the similar structure which is present in the non-graded film. So this film, because of this smooth gradation, shows very good toughening. And when we stretch this material, we also in DMA, we see that for the gradient film, we get a second tan delta hump. And when we do this extensional stress versus strain property at 80 degree, because this hump is obtained at 80 degree centigrade, we see that very good structural elongation happens even in dynamic mechanical analysis. So it gives us an idea that in the gradient structure, when we stress them, the gradients are aligned and the polymer chains are aligned in the gradients, and the CNC which are present is also aligned. So this gives us a structural orientation that leads to very good mechanical properties. And these are also used for fruit packaging, for flexible packaging. And we see when we have only PLA, after 2-3 days, the fruit starts to degrade. There is some enzymatic discoloration. But when we use the gradient film with SCNC, this shows shelf life, enhancement in shelf life up to 4-5 days. Because ASCNC have this amine group, so which helps in having ionic interaction with the bacteria and help in kill the bacteria, because these interrupt the bacterial cells. So also, and this shows biodegradation also. I skipped this. So the conclusion is that biomimetic approaches using the biomimetic approaches, we can prepare structural high performance materials. These materials shows very good mechanical properties even at high humidity, very good thermal properties because of the interfacial interaction between the modified CNC and the polymer matrix. Because of the PDA coating, we can prepare UV blocking property, UV shielding packaging film. These are biodegradable and environmental friendly fabrication process. So this film can be useful for structural, barrier, foils, flexible grain packaging, UV protective packaging, and flexible substrate also for wearable devices. And the one which I have not shown is that this can also be, like Professor Thomas showed, using nanocellulose fibers for filtration, adsorption. Here also CNC can be useful, taking as a cellulose membrane as a substrate, and we can modify it for dye removal, and this shows 96% of dye removal. And also we can check its repeatability for 5 to 6 times. It retains its removal efficiency up to 89%. So thank you. And here we have some students from Cipet, Siddharth, Bhavana, Arti, and I would like to thank all my group members and my funding agency, and thank you all for your kind attention.
Okay, thank you very much, ma'am. And basically, we are running out of the time. Yeah. So I would like to skip this questionnaire session. And I know many of you have some doubts, and that you can be interact with her during the lunch break. I know we are quite hungry, so I have to finish another two talks before the lunch. So we are moving to the next talk with Professor Sujit Adiyanathil. Yeah.
So before that, I'm inviting Dr. Prashant sir to present a memento to Padmita ma'am.
Okay, now we are moving to the next talk by Professor Sujit on the topic super hydrophobic materials inspired by nature. And we already done some work together in this direction, super hydrophobic materials. And Professor Sujit is from National Institute of Technology, Calicut, and he received his PhD from the same institute. And he is the faculty in the Department of Chemistry. And he was a postdoctoral researcher in the Raman spectroscopy at AIST Shinkoku, Japan. And his research interests include biocomposites, biopolymers, polymeric materials, membrane science, and Technology, Raman Spectroscopy, etc. He has published 86 articles, scientific articles in the peer-reviewed international journals, and authored or edited 4 books. He has completed 6 major projects sponsored by DST, CSIR, KCST, NIT Calicut, BRNS, and the Ministry of Earth Science, etc. And he have a good expertise in the electrospinning, and I hope he is going to talk a little bit on the electrospinning over here. Thank you. Now I am cordially inviting Professor Sujit to deliver his talk.
Respected Chair, Professor Prashant Sir, my dear friends, today I am going to talk to you about a mimicry. You know that all of us like mimicry. So this is actually a biomimicry. Almost all the technologies now we are enjoying is actually the contribution from the nature. That is why our great poet said that let nature be your teacher. And about the lotus effect, already we discussed. You see, this actually made it possible. Okay, so you see that there is a spiritual song starting like this. Nalini dalagata jalamati taralam tadvajividam adishaya chapalam. Nalini dalagata jalamati taralam. The song is going like this. The song is telling that water is unstable on lotus leaves. That means just like that, our life is also like that. It's very, very unstable. Okay. You see, this effect makes a lot of applications. You can see in the form of anti-corrosion, oil-water separation, anti-icing, anti-fouling, anti-fogging, lot of biomedical applications, self-cleaning applications, and this effect is known as the super hydrophobic effect. A very good physical example is suppose if your car, this glass is coated with a material which is transparent and also super hydrophobic, means there is no need of wiper. Okay, so please see this picture, and some unusual thing can you see in this picture? So this man is sitting on a nail bed. So please don't imitate this. So I'm showing this picture because actually the water drop is sitting on a nail bed on the lotus leaf. So lotus leaf is actually look like very smooth, but if you are looking through a scanning electron microscope, you can see that a lot of periodic growths on that leaf known as papillae. Actually, this water drop is resting on this type of nail bed. You see, when you look a different type of leaves, when you look through scanning electron microscope, the super hydrophobic leaves periodic structures like this. And very good example is our water strider. So water strider's leg, if you take the scanning electron microscope, you can see a lot of brush-like structures. So due to that, water strider can walk on water. And this can be extended to the case of geckos' feet. And you see, there are a lot of creatures like this. We may feel ugly, but they are really beautiful, because if you look through scanning electron microscope, their skin is actually very, very beautiful. You can see a lot of periodic growths on this, and these growths actually helps their skin super hydrophobic. You see the very fundamental thing about the super hydrophobicity, that is the contact angle, and this theta is the contact angle. And you can also see the different type of angles here. 0 degree means completely wet surface, and it's coming to 90 degree. You can see that some drop, the shape is changed, and you see after 150 degree, you can see there will be no wetting. So this is called the contact angle. How can you quantify these things? Because we have to find out the contact angle. So the instrument used is called goniometer. Goniometer is a very simple instrument which has a light source, and your sample you can keep here, and there is a dispensing system. You can use the syringe and you can dispense water, and this is the important part of this instrument, that is called a high resolution camera. So by high resolution camera you can take the picture and you can measure the angle. Okay, so another important property of super hydrophobic materials is the self-cleaning property. So in the case of lotus leaf itself or colocasia leaves, you can see that so if some dust particle is there, if rain or if you spray water, you can see that all the dust particle will flow with along with water. Okay, so that property is known as self-cleaning. So you see in my in your left side, you can see a hydrophilic surface, and this is a hydrophobic surface. In hydrophilic surface, you can see this red one is dust particles. So when water drop flows like this, means normally the water drop will fall like this, but the dust particle will be there as such. But actually in the case of super hydrophobic surface, the water is rolling on the surface. So due to this rolling, you can see that all the dust particles will be flowing along with the water drop. So that is the mechanism, simple mechanism of self-cleaning. And there are a lot of preparative methods for the super hydrophobic surface. There is spin coating is there, plasma treatment, photolithography, chemical vapor deposition methods, salt gel methods. And what I am focusing here is a technique called electro-spinning. And this is a very simple method for the production of super hydrophobic surfaces. But it looks like very simple, but you can see that it is published in a very good journal, Journal of Material Chemistry A. Simply by using a paraffin, this candle, you can just the flame, you can the soot it's developed on the glass plate can act as a super hydrophobic structure. Okay, so there are certainly there are a lot of chemical methods for the production of super hydrophobic materials. And another method is, I told you, that photolithographic method. Normally you can imitate. The imitation is actually you can do it by lotus leaf itself. Suppose you use a very soft polymethyl disiloxane film. If you just press it on the lotus leaf, normally you will be getting a negative. So if you bake it, hard bake it, you will be getting a template for the same. And if you are using another flexible material, if you press it on the template, you will be again getting a positive. So this is called lithographic technique. Actually, you can imitate the lotus leaf and colocasia leaves like that. I will give you one simple experiment you can perform in your lab for making a hydrophobic filter paper. So this is a very common thing. This is called the beeswax. Beeswax is highly soluble in tetrahydrofuran. So you will be getting a wax solution. You just take your Walkman filter paper, just like you are preparing papadam in your, just like that. You can dip it and dry, then you will be getting a hydrophobic filter paper. So this you can perform in your laboratory for the demonstration of hydrophobicity. It can hold water, but it will pass the kerosene or oils through it. So it can be used for oil water separation. Regarding the electrospinning, so electrospinning is also a very simple technique. It consists of a syringe, and there's a high DC voltage has been applied to the needle, and there will be a collector. The polymer solution is there. So syringe is actually software controlled. Suppose this setup is there. If you are applying the DC voltage, you can see that a Taylor cone is developing at this tip, and it is ejected to the collector. Then you will be getting an electrospun membrane. So this is actually very beautiful when you look through scanning electron micrograph. You can see nanometer shaped, nanometer diameter shape type membranes through the microscope. Actually, this size you can regulate. You can tune the size of the fibers of electrospun material. And there are a lot of applications, especially biomedical applications. A lot of things are there. So one thing I wanted to address about the oil pollution. There we made a material for just like a tissue paper. You can absorb oil drop from the water. So this is actually made by polycaprolactone and beeswax. Beeswax. This is an electrospun membrane with it's a high efficiency of oil water separation. So you can see that the contact angle when we measure the contact angle, it is increases when the beeswax content in the system increases. Okay, so I told you that the method is, suppose you have the water drops oil drop in water. Just like a tissue paper, you can apply this electrospun membrane, and you can see that all the oil particles, oil drops are actually absorbed by the filter paper. So the oil content can be removed from water. And this is also another experiment. I'm not going to explain it because you can see this is a simple gravity-driven oil-water separation. You can keep your membrane here. Suppose you have an oil-water mix here. So this is in a slanting position. You can see the oil will touch the membrane and it will directly come to the beaker, and the water will remains as such. Okay. And you can also introduce some antimicrobial agents in this. Zinc oxide, nano zinc oxide is a very good antimicrobial agent. So you can also introduce some synergic behavior in this type of membrane. I would like to tell you one more thing, important thing in nature. So this, maybe you have seen this in nature. These small creatures are called aphids. So aphids, what they are doing is, aphids will give a honey type material to ants. Ants will eat it. But what ants will do in return? Ants will protect aphid. That means if you touch aphid, and ants will bite. So the problem, one of the problems here is how nature avoids this problem. That is why I am telling. Because these small creatures are producing honey. So honey is very sticky. So that these ants cannot walk. But the nature is beautifully made like this. That means this honey is actually producing not as such, but with a coating, with a super hydrophobic coating, so that it will not stick. So the ants can eat it. So this actually scientists made one of wonderful material from this. That is called the liquid marbles. That means the liquid or water can be coated with a hydrophobic powder, and you can make a liquid marble. So this thing you can see in your kitchen. You can see, suppose you are making chapati, you will first take this wheat powder. So what you have to do is, you just drop one drop of water to the wheat powder. You can see that suddenly these liquid marbles are forming. It may not be stable, but that is the, also you can see that is in the sand. If you just pour one drop of water, actually 1 or 2 drops of water. Otherwise, if the water quantity is very high, means this effect will not be there. So there will be some optimization condition for all these things. Okay, so this is also one of the application. That means the liquid is coated with a hydrophobic system. So this is very helpful for the transportation of liquids and also for small chemical reactions, that is called micro reactors you can produce, not only with water, but also with different type of solvents, this super hydrophobic. That means in a beaker, you can conduct lot of chemical reactions. That means in a single beaker. That means one liquid marble consists of A plus B, other liquid marble consists of C plus D. So you'll be getting a lot of products there without interacting all these things. Okay. So this is actually my presentation. I want to tell you very fundamental things about the hydrophobicity. Thank you very much. Thank you for your kind attention. Thank you.
Dr. Sujit for the wonderful talk, and I wish to thank you for shortening your presentation. So we will. Because of the time limits, I would like to request you to interact with Dr. Sujit during the lunch break.
Sir, please present a memento to Sujit, sir.
Yeah, that's great. I would like to, with the permission from the organizing committee, I would like to invite Dr. Asha from the NCL Pune to hand over this memento to Dr. Sujit. Thank you, ma'am, for this. Okay. So, Harley, we are going to the next session by Dr. Deepti Menon. Yeah, she's here. So, Dr. Deepti Menon is from Amrita Vishwavidyapeetham, Kochi. She's obtained her MSc degree in physics from Kochi University of Science and Technology and a PhD in physics from Indian Institute of Science, Bangalore. She has a postdoctoral training from the Technical University of Eindhoven in the Netherlands, National Cancer Institute, Maryland, USA, and International School of Photonics, Kochi University of Science and Technology, India. Her current research at Amrita is at the interface of nanotechnology and biology for biomedical applications, and is primarily focused on the understanding the potential of nanoscale engineered materials and materials for biomedical applications and medical implants for the translational applications in the field of cancer, nanomedicine, and regenerative engineering. She has an H-index of 51 and is also inventor of 3 US patents and 9 Indian patents. Her research team has produced more than 125 peer-reviewed international publications in the leading journals. And she is the recipient of MRS of India Medal and Young Scientist Fellowship, Boys Cast Fellowship, both from Department of Science and Technology, Government of India, and Young Research Award from International Union of MRS. She serves as the Council Member of Materials Research Society of India and a Task Force Member of DBT, DST, and Nano Safety Regulations in India. And she also have a very good expertise in the electrospinning. And now I would like to invite Dr. Deepti to deliver her talk.
So I know all of you are hungry. I'll make it fast. The title of my talk is Polymeric Nanotextiles. But before I begin, a big thanks to Cipet organizers for inviting me here. And thanks, Dr. Prashant. So let me directly get into the topic. We are from the Amrita Institute of Medical Sciences, which is actually the hospital campus of Amrita, right across. And we have an interdisciplinary team of activity wherein we focus on translation mainly. So clinical research combined with technology and molecular medicine,
We looked into developing low-cost, high-quality products. And thrust research areas include nanomedicine, bioengineering, nanotechnology and renewable energy, and molecular medicine. Just for the students out here, we have interdisciplinary research-oriented teaching, which combines basic science with translation, offering MSc and MTech programs in nanobiotechnology, molecular medicine, nanoelectronics and nanoengineering, as well as PhD. With this, I bring the outline of the talk. Medical textiles is what I'll be introducing. Thanks to Dr. Roy for the introduction. I'll cut it all short. Importance of nanoscale, thanks to Dr. Sujit. I will cut it short again. Electrospinning and nanotextiles, this is the theme that I'll bring forth. And smart nanotextiles, if time permits, I'll be talking about a few implants that we have developed, also drug-eluting depots. So, talking about medical textiles, you see that there are so many materials that are used in medicine, and they can be either for surgery or for healthcare, or it can be even extracorporeal. It can be implantable or non-implantable. All of these have basic constituents, which are polymeric yarns, which are developed from granules. They are either woven, knitted, braided, or it can be non-woven forms. We in general call them as fabrics. Look of them. Cardiac valves are available, vascular grafts, which Dr. Roy talked about, stent grafts. This is just a small purview of the few of the medical devices, but there are very many more, all of which are based on textile technology, wherein there is tunability in size, in shape, porosity, as well as in mechanical strength. The last part, I'm not getting into all these. You can develop all of these by maneuvering their size, shape, porosity, etc. But mechanical strength is actually obtained by the process of interlocking. But the main limitation behind all these polymeric textiles is that they utilize microfibers whose dimensions are greater than 10 micron. So, what's the problem? Always, if you look into your human body, you will see that everything is at the nanoscale. So, nanoscale is very, very important as far as human body is concerned, because the extracellular matrix consists of various proteins as well as polysaccharides, collagen, fibrin, fibronectin, all of them having nanoscale dimensions. And all the fundamental biological processes and interactions occur at the nanoscale. Just a small example is this. A cell which is micron-sized interacts with all kinds of extracellular matrix proteins which are at the nanoscale. That in turn promotes very good cell adhesion, proliferation, and differentiation. Now, coming to the techniques, there are so many techniques which can enable you to develop nanofibers, which include electrospinning, phase separation, chemical vapor deposition, etc. But electrospinning is one of the most versatile techniques that helps you to create continuous fibers, and which is very easy to do in the labs. Conventionally, you have an electrospinning. Dr. Sujit explained in detail. I take up only the last, which is actually a collector onto which you spin the fibers easily. You can get them randomly deposited. That is, a polymer which is taken in the syringe here gets deposited in random ways, forming the fibers like this, or you can get them aligned, depending upon whether you keep it static or rotating. Now, mind you, whether you get it this way or that way, there is no interlocking, it has poor packing, and it's mechanically very, very weak. So, despite being nanofibrous, mechanical properties of these materials are very, very poor, and we cannot utilize them for medical textile applications. So, we looked into nature, adopting lessons from conventional textile technology. All of you are familiar with this, cotton ball, from where such kind of twisted yarns are developed and which can be maneuvered to knitting, braiding or weaving, thus getting properly interlocked structures. You can get constructs of different patterns, and this is possible only because you have high-strength yarns from cotton fibers, typically 500 megapascal. And with such kind of structures, you get bidirectional alignment and interlocking. So the question that we asked ourselves quite some time back was, how can polymeric fibrous yarns be obtained? We made slight modifications. A very brilliant student was there with me at the time who could actually modify the collector which was used for electrospinning and obtain such kind of a point electrodes, which in turn varied the electric field distribution and enabled us to create such kind of continuous fibrous threads. So you can see, despite being a continuous thread, it retains its fibrous architecture. Look into the cross section, you can see thousands of fibers. You can vary the diameter, you can vary the twist angle, you can play a lot with it, and you can get it into various kinds of geometries, anything. And you can load it with drugs, you can vary the mechanical property, but the only thing I want to highlight, it is still extracellular matrix mimicking architecture because it's nanofibers. Increase in fiber packing as a result of twisting leads to higher lateral friction, which in turn increases the mechanical property. But we are now here with a single yarn of electrospun fibers. We have a mechanical strength which is increased to typically 25 megapascal. You said earlier, you saw earlier, 500 megapascal is what we actually require. So the goal is this. Thus, we started thinking about interlocking these fibers, which has fibrous architecture. And that brings us to the field of nanotextiles. We have been utilizing this area of nanotextiles for multitude of applications in biotechnology, in medicine mainly. This is the patent which John Joseph is the architect. With my help, we have a US patent, and this is the first paper that we got in nano letters in 2015, which marked the beginning of this field of nanotextiles. This is actually a very beautiful video. It's not playing, so it makes it easy. No videos are playing. I don't know why. So we made conduits with these fibrous yarns. This looks much like a thread, but we have made conduits of these kinds. I'll just show you the pictures. You can see 0.5 millimeter diameter, very, very small conduits, to something bigger, 4 millimeter, whose cross-sectional SEM is what you're seeing here. This can be made of high packing, medium packing, low packing, etc. Nanofibrous conduits were developed. Microfibrous conduits were developed. You can make any polymer that is electrospinnable into these forms. Now, please note, Dr. Sujit was telling all about nature. We saw that our nanotextiles were also smart. You can see the material which we utilize for most of the applications were the biodegradable polymers of PLA, PCL, etc. Contact angle is typically more than 100. Bulk material or even an electrospun mat. But see this. This is a nanotextile which we made whose contact angle was typically 0. We couldn't even measure that. So I christened it as a smart material. A hydrophobic polymer, PLLA, is transformed to a super hydrophilic material when it is woven as a nanotextile. And beautiful demonstrations of that were made. A dye reservoir in which you can see there is seeping of the dye on nanofibrous structure. These are the corresponding SEM images of a twisted fibrous yarn, nanofibrous yarn which is aligned, microfibrous yarn, and a monofilament. I told you, monofilaments are the ones that are utilized for biomedical applications so far. So you can see that this is very, very wetting. I'm sure this also will not run. Yeah, it runs. Very good. So you can see immediate wetting of a nanotextile, despite it being made from a superhydrophobic material. Rate of wetting in materials can be varied by their packing. So significant differences in various properties of the resultant nanotextile have been observed. I come to the applications. What all can you utilize these nanotextiles for? You can make a vascular graft, a vascular patch, a bone graft, a drug-eluting implant, so on and so forth. For want of time, I might stop in between. I might talk first about a vascular graft. As rightly talked by Dr. Roy, applications of vascular grafts are routine in the clinics. What is now used are mostly high diameter vascular grafts, which are mostly taken from saphenous vein or internal mammary artery. But the moment you reduce the diameter to less than 6 millimeter, it occludes. So, no grafts are now available that cannot occlude below 6 millimeter diameter. So, there is a high demand for synthetic small diameter replacements. World over, people are trying to develop, and we also join the fray. And mechanical properties of a vascular conduit is very, very important. Lot of properties. Suture retention, it should not leak. Water entry pressure, it should not be very stiff. It should not burst when arterial blood pressure comes. It should not kink. It should have good tensile strength. So we developed such kind of a material and tested it. The woven conduit that I showed you was tested for each of these parameters. And I just want your attention towards this Li, Mi, and Hi. This is low, medium, and high interweave compared with electrospun sample. So in all the cases, you can see that the high interweave has very good suture retention, circumferential tensile strength, radial stiffness, and water permeability was the least for the high interweave. And you can see that electrospun, same material, kinks, whereas you can see a high interweave does not have any kink. This material was tested in rabbits in our animal house, and you can see that the material was very, very thrombo-resistant. This is a paper that we published in 2018, transforming nanofibers into woven nanotextile for vascular application. The same material was then tested in porcine model by Dr. Raimondo at University of Bristol in the UK, and you can see that the porcine model was implanted with a woven PLLA conduit as an interposition graft. Not sure if the video will run. No. It's not running. Okay. So you can see that this is a PTFE graft, which is actually the commercial one, which is called as weeping graft, because blood oozes from each of the dots that are generated here due to suture. So there is suture line bleeding that is very, very common for such kind of grafts. But our material, that's what I wanted to show you in this video. There was no suture line bleeding, and it was completely having a very good distal flow after 15 days. Just to show you, ultrasound, Doppler ultrasound showed very good blood flow. You can see the pulse wave mode, and last result is that of your explanted artery, and this is the artery which has the material. You can see the brown color, that is, this represents our nanotextile graft after 1 month of implantation. You can see at 1 month, there was slight thickening of the artery. You can see in 2 weeks, it was not there. So we are trying to work around this. You can see that blood vessels could easily get inside this material, and the tissue bonding with the material was very, very high. I'm not getting into the rest of, we have done a lot of stainings, and I just wanted to show you that this particular lining represents endothelial cells, which is actually very, very important for a blood contacting material. And you can see that in the material, the cells were all packed well. And this is actually an end-phase staining. After you explant, open the vascular graft and stain it for endothelial cells. This is what is very, very important in any kind of biomedical blood contacting material, that endothelial cells should cover the material. This does not happen for the clinical PTFE graft because it does not wet at all and it does not allow this material to the cells to attach to the material. So this work was published in Journal of Nanobiotechnology. The same technology was actually translated to vascular patches, which are made up of PLLA or PCL collagen, which are tightly wound, and we are in the process of doing that. And you can see very good endothelialization on this material at 48 hours. Live dead staining clearly shows that all the cells are alive there, and the preliminary work has been published on a nanotextile vascular patch. An important milestone that actually happened in the process was the development of a nanotextile bone graft. All the patients who come to the clinic with injury to the jawbone need help. So you can see that you can lose jawbone either due to oral cancer or due to some trauma which is inflicted by such kind of accidents. In all these cases, what do surgeons do? They take fibula from your leg and place it in the mandible, but the height of the mandible, height of the fibula will be very less. So you can get a deformed structure. So what is actually done is a vertical augmentation for which a material has been utilized. Here in the clinics, this always happens. So you want to increase the bone height and also allow dental rehabilitation to these patients, wherein you want to keep such kind of metallic dental implants. And that will enhance not only the functional performance, but also aesthetics. So with this view in mind, we developed, myself and my colleague, Dr. Manita Nair, developed such kind of a novel bone extracellular matrix mimicking graft for mandible augmentation. It's not a total graft for the mandible reconstruction. It is meant only for augmentation. So the uniqueness was that it encompassed electrospun fibrous yarns. And it has a biomimetic matrix, which was silica hydroxyapatite gelatin. And it had a very good toughness and mechanical stability without affecting bone regeneration potential. This is a material that we developed. You can see the fibrous yarns which are incorporated in this porous material. And mechanically, it was very, very good. And you can see that the surgeons could actually drill it, cut it, and all the biocompatibility tests were carried out in Sri Chitra. And we did studies in comparison to an autograft in pig mandible having a critical size defect of 3 by 2 by 1 centimeter cube. And you can see that there was reconstruction of your bone material there. And where it stands today is that we have at Amrita a GMP scale-up preparation wherein the material was scaled up, and we called it the Nanotex bone graft. And it has undergone pilot clinical trial in 10 patients at the Amrita Hospital. And the person behind this was Dr. Subramania Iyer, who is a head and neck surgeon, who is a plastic surgeon. He has actually implanted the material that we developed, that is a Nanotex bone graft, successfully in 10 patients, and they are under observation for a 1-year period. So this is where we stand as far as the material is concerned. Just a brief thing about drug elution in ovarian cancer, where ovary is removed, paclitaxel after cytoreductive surgery is what is given intraperitoneally, and the peritoneum is closed. What happens later? Residual tumors come back, peritoneal adhesions can develop. Systemic toxicity also comes up due to the drug that is administered. Disease relapse is the problem. Oncologists at Amrita came and discussed with us and asked us if you can provide a solution to this fatal gynecological malignancy, ovarian cancer. So they wanted a better intervention, providing better tumor responsiveness. So I had my students work on these kind of yarns at the time. I asked the doctor, how long do you want it? So he said, longer the better. I'm talking about a drug-eluting fabric. So we developed this yarn, which was based on, I'll just take 2 more minutes, we utilized polydioxanone as a material, which is a suture material, incorporated it with the drug of choice, which they use in the clinics, that is paclitaxel, and we made fabrics. This is a little weaver that we utilized to make the fabric in the lab. So we developed different kinds of fabrics, looked into the release kinetics. We saw that a very loosely packed material, LP, loosely packed, eluted very good amount of the drug over a sustained period of up to 60 days. Very good. So we tested it in animals after suturing it to the peritoneal cavity. This was also tested in tumor-bearing mice. What you are seeing here is up to 60 days the drug eluted. And you have more to elute further. So you have 2 months period, and this is a work that is already published in Nanomedicine, and we understood that all the peritoneal organs have content of the drug up to about 60 days. In the feces through which this particular drug, paclitaxel, is eliminated, there was drug content up to 16 days, all implying sustained drug retention from the implant. This was tested in vivo. This was done in Northeastern University. This is a tumor-bearing mice which has a bloated belly, but the nanotextile implanted animal have a clean belly and there was no tumor tissue. This is the final picture that I'm showing you. A lot of work has gone into it, and the woven textiles eluted this drug continuously for 60 days. All of these works are patented and published. The same technology has also been applied to converting a metallic biliary stent into a drug-eluting stent. So I conclude, I just skip all this. I conclude, the lessons that we have learned is that nanotextiles with their fibrous morphology have significant advances over conventional polymeric matrices that are now utilized as medical textiles. Substrate-less electrospinning was utilized, and this is a scalable technology. Value-added features, physical property can be altered, chemical property, biological property, all these makes it possible for diverse applications in medicine. Thank you. All the work I submit it to my dear students who work hard to enable me to show all these to others. The team that we have at Amrita, quite interdisciplinary. I am a physicist by training, a material scientist, but I work a lot with the biologists in the group and all the clinicians who made it possible. And but for the help of the animal facility, we would not have reached anywhere. And all this through the benevolent funding from all the funding agencies and my collaborators. Thanks to all my brilliant students. Thank you.
Thank you, Dr. Deepthi, for giving this nice glimpses of your work. And because of the time limit, I am skipping this questionnaire and discussion session.
I'm inviting Prashant sir to present a memento.
Okay. I would like to invite Dr. Roy to present a memento to Dr. Deepthi. So now we are concluding this session. So in this session we have 4 lectures. The first one from Dr. Roy, Sri Chitra Institute of Medical Science, Trivandrum. And second one was from Dr. Das, Indian Institute of Science Education Research, Bhopal. And the third one is from Dr. Professor Sujit on this hydrophobic materials from the NIT Calicut. And the fourth one was from Dr. Deepthi from Amrita Institute of Medical Science, Amrita Vishwavidyapitham, India. And the first talk was on the alginate, the natural polysaccharides and their application in the biomedical and implants materials, followed by Dr. Deepti's talk on the fabrication and the applications of the nanostructured polymeric nanocomposite, basically on the cellulosic nanocrystals. And the third one is basically on the electrospinning and bio-inspired materials for the fabrication of super hydrophobic materials for environmental remedies. And I would like to remember one work we done in the collaboration that is on the same direction, in the fabrication of the lotus, exactly the lotus leaf surface for the oil water absorption using the acrylonitrile butadiene styrene polymer, ABS polymer, incorporated with the zinc oxide nanorods and nano-sized calcium oxalate. And this work is actually not carried out by any researchers. That is carried out by two school-going students from the St. Paul's Higher Secondary School, Kadairippa, Kochi, and they presented this work and they in the global science exhibition in USA, and they received their grand prize for the same. So I would like to thank Dr. Professor Sujit for this one. And the last talk was on the electrospinning and biomaterials for the different biomedical applications. And Dr. Deepthi is beautifully explained how this biomedical implants and the grafts material can be fabricated from the electrospun membranes, and how the properties can be altered, and how she is simply transferred this super hydrophobic material to super hydrophilic material. That is wonders. And I would like to say all for this keynote lectures was insightful, and they are explained in a very, very clear way. And I hope this all four talks is inspired the young minds, and they could think for a better sustainable world. And thank you very much for all the speakers and the students for your great patience. And now I declare this session is closed over here. Thank you once again.
Thank you, Dr. Prashant sir, for chairing this plenary and keynote session. I'm inviting Dr. Roy Joseph sir to present a memento to him. Now it's time for lunch break. The next session will be started at 2:50 p.m. The plenary 3 and invite lecture 2 sessions will be conducted at here, and oral presentation will be conducted at VC Hall parallelly on first floor. So those who are doing oral presentation, go to VC Hall after lunch. All are requested to reach by 2:50 p.m.
Siraj +91.
Hello?
Dr. Nida John is a highly accomplished professor in the Department of Chemical Engineering at St. Giles College of Engineering, Kottayam. She holds a
Yes, yes.
PhD and MTech from Kochi University of Science and Technology and a BTech from Calicut University. Over her 27-year career in teaching and research, Dr. Nida has built an impressive portfolio combining her expertise in chemical engineering with a passion for
So,
advancing scientific knowledge.
uh,
Her research contributions are extensive with 43 published research papers in well-regarded journals, 9 authored book chapters and 36 papers presented at both national and international conferences. Dr. Nida's work reflects a commitment to pushing the boundaries of knowledge in her field. Additionally, she serves as a reviewer for the Journal of Technological Advances and Scientific Research, where she plays a key role in maintaining the integrity and quality of scholarly publications. With her wealth of experience and dedication to both education and research, Dr. Nida John continues to inspire and contribute significantly to the advancement of chemical engineering. I request Dr. Nida John to chair the sessions. I would like to hand over the sessions to the chairperson.
Thank you very much for the nice introduction. Our first session is by Dr. Professor Joseph Takonik. He is PhD from THLM, Germany, and since 2006 he is a head of department Polymer Technology at Chemical Faculty of Gdańsk University, Poland. His special scientific interests are chemistry, characterization and processing of polyurethane, recycling of polymers and rubbers, bio-based polymers, polymer composites, and nanocomposites. J.K. Hopik is author of and co-author of 300 original scientific papers, including 90 published in journals from Philadelphia list. Creator of 10 patents and 25 applications. He is actively collaborated with Mahatma Gandhi University, Kottayam, and he received multiple awards and distinction in outstanding scientific activity. Professor Job Hopek is highly regarded academic teacher with rich achievements. He was a superior in many doctoral programs. A professor is an experienced researcher in the field of polymer composites, polymer blends, and associated materials. He has received a number of prizes and awards for his work. Currently, he is going to present biomass liquefaction processes optimized for generating intermediate products suitable for synthesizing polymer composites. Welcome, sir. You can start your presentation.
yes.
Hello, sir. Can you hear me?
It is a problem with the screen because I cannot stop it. Now I open the presentation and I want to start sharing it just now. Yes, now I'm sharing. Uh, but I cannot move to the next slide. Down. Yes, but it doesn't change. It's a problem. So if I do it, it doesn't react. Nothing happens.
Sir, in the number 6, there is arrow.
In the infinity.
Sir, okay.
So do you see anything from my side?
Yes, sir, there is multiple screens are coming. Can you stop sharing okay.
I can send you it. Yes.
You can send by mail.
Yes. Yes. Yes.
Okay. So can we get the next presentation? Can you wait for some minutes?
Just a moment. I'm looking for the presentation. So here we have changed, then I will change that slide. Yes. I'm just sharing. Okay. By mail you can share. But yes. It is too big. So, can you have it as one drive? One drive. So, yes, okay. Okay, thank you. I'm very sorry. Yes, I have made it
Now I invite Dr. Anandakumar Srinivasan, Professor Associate, Anna University. He has completed PhD from Anna University and post-studies from De Montfort University, UK, and Institute of Polymer Composite University, Minho, Portugal. He served as Assistant Director in Central Entrepreneur Development, Anna University. He has more than 65 publications in reputed journals and contributed 8 book chapters in international publication like CRC, Apple, Wheelie, etc. He is editor of Eco-Friendly Nano-Hybrid Material for Advancing Engineering Application. He has completed several national and international funded projects from DST, DRDO, Anna University, etc. He received Active Researcher Award for the year 2014 from His Excellence late Dr. APJ Abdul Kalam for his outstanding contribution in nano-hybrid coating and composites. His team won Runners-Up Award for Technology Innovation and Nanomaterials from Honorable Central Minister of Anandakumar is in the year 2015 during APM 2015 held in Bangalore. Recently, he received Technology Innovation Award 2021 from Honorable Education Minister of Tamil Nadu. Last year, he was awarded a Scientist Medal by IAM, which he received in Stockholm, Sweden, in 28 August 2023. Furthermore, he received Dr. N. Mangalingam College of Engineering Bisanitary Polymer Science Award. I invite him for his presentation, Semi-IPN Coating for Paper and Wood-Based Bio-Based Polyurethane PU and Biodegradable Polylactic Acid PLA. Dr. Anandakumar S. As he is getting ready for the online presentation, in between, I am inviting Dr. Ravi Babu V, Senior Scientist at Electrochemical Process Engineering Division, CCRE, Karaikudi, Tamil Nadu. He received his PhD from Indian Institute of Technology, Guwahati. Before joining SICRI, he was Technical Officer at Cipet IPT. His research interests include biopolymers for smart packaging, polymer for medical applications, 3D printing, etc. There are 25 publications, 10 book chapters, and 3 patents to his studies. He developed 6 innovative technologies and transformed 3 in the industries. He completed 7 major projects and currently principal investigator of 3 sponsored projects. Currently, he is presenting tailoring of biometric scaffolds for tissue engineering, 3D bioprinting techniques in regenerative medicine. I welcome Dr. Ravi Babu sir for his presentation. Welcome, sir.
Yes, good afternoon, everyone. Yeah. So, first of all, I'd like to thank organizers, especially Dr. K. Rajesh, and who invited me for this wonderful conference. And actually, I want to tell you that I was former Cipet employee, and I was there with the CBPST for 2 years from 2015 to 17. So we had a very close association with Cipet Kochi. Okay. Yeah. So actually, we are working on biomaterials, our group, and as well as we are also working on 3D printing technique for using for aerospace applications and other fields. So here I'm going to talk more on to the 3D bioprinting. So our major work is on tailoring of biomimetic scaffolds for bone tissue engineering using bioprinting technique in regenerative medicine. Okay, so so here it is. Actually, we are working on multiple materials. And here I want to talk about cranial burr hole plug. We are developing cranial burr hole plugs for bone tissue engineering applications. So as we know that when we want to have any brain surgery, so usually they used to cut the scalp and then they used to drill the skull to make a hole to operate in brain. So once it is when they are drilling the skull, at that time it will become a powder. Once the operation is completed, there won't be any bone to fill that particular portion. So that is the challenge. So olden days when they are doing it, they used to, there will be a durafilm between the skull and as well as the brain, and they used to cut and they used to do the operation. After that, they will close the durafilm and then they will close the scalp, but the burr hole is empty. And nowadays they are using titanium-based burr holes, which is a metal-based scaffolds. But the issue with the titanium-based scaffolds are it will be a permanent implant in our body. So that's actually, as we know that it is a titanium, it's a metal, maybe in the downline there may be an issue with the corrosion and other issues. So here what we are developing here, it is biodegradable bone implant, okay, cranial burr hole plug. So that's where, as we know that the bio materials, we can make it by using the metal and alloys, ceramics. So here it is, when you're talking about the metal, there is any limitations. I don't want to go in deep about it. And ceramic also is having the limitation. So that's where actually we want to make it a combination of composite material which can overcome the issues with the metal and as well as the ceramic scaffolds. So here it is actually, when we are talking about bioprinting or 3D printing, which we want to use it for this biomaterial applications. So the reason is that why we want to use this biomaterial, printing. When we are talking about any conventional technique, if you're using for the bio implants, so what it will happen, there will be an issue. We cannot make it like, patient specific implants. So it means if you want to make any implant for a specific patient, it means it is expensive. The reason is that as we know that as a plastic engineers or the chemist, if you want to make a specific shape, you have to make a die and then you have to make a particular shape. So the patient to patient, the size of the defects will vary. So then it is an expensive. And at the same time, when you are talking about conventional scaffolds, it may not be a porous structure and there will be a less surface area. So that's where actually we have to have a combination of this, porosity and as well as at the same time patient specific. Then we have to move on to this 3D printing technique. So here, if you're seeing it, so how we used to do that. I don't want to give more on, basics of this bioprinting because morning Professor Royce already has given about this, 3D printing, and he made my job is very easy, right? So here you can see it. Actually, we'll make polymer and as well as the ceramic material, and we'll make the bio ink, and then we will go for a printing. And these are the biocompatibility, bioactivity, cell mineralization, all these studies we used to do it. So this is the schematic diagram, what we used to do it. So here it is, we have, here it is, why we are selecting this, MBZ, mesoporous bioactive glass. As we know that the ceramic, if you're talking about the bone, it is a combination of organic and inorganic material, right? So if you're seeing the natural bone is having a 70% of inorganic and 30% of organic compound. right? So that's where the limitations with the pure ceramic composites as well as the metal composites. Okay, so if we are able to mimic this too, to make it as a natural bone composition, 30 and 70%, then it is having a better application. So that's where the reason we have selected the mesoporous bioactive glass. So bioactive glass means it will have a bioactivity, and it's not only the people are working on this bioactive glass for the past few years, and hydroxyapatite and other things. Beyond that, we should have a nice porosity to have a controlled functionalization, right? For that we should have a high surface area, and at the same time we should have a groups which can be tuned according to our requirement. So that's why we have prepared the bioactive glass, and you can see that TEM image how the pores are nice, nanopores are formed in our bioactive glass. This is where actually getting this nice structured porosity without having a breaks is a challenging, and reason is that very minute changes in the parameters. We observe that the change when you are preparing a material, the temperature, even if you are having a difference of even 3 to 5 degrees difference in synthesis process, pores are forming, but you will see that disconnected pores, so that it won't work. So that's where the repeatability or understanding the material is very important. So here we can see that we have taken the polylactic acid is 30%, MBG is 70%. As we know that the natural bone composition is 70% is inorganic and 30% is organic. So based on that we have selected, and then we have printed. So here it is the challenge here in this, especially the printing part. As we know that the morning Dr. Royce already mentioned about bio-ink preparation. Right? So is it that simple to make or print the composite scaffold? Because as we know that when 3D printing means it will print the first layer and then again the second layer it will print, right? So when you're making the ink, so once you when you're printing it, it should not spread, right? It should have the thread should be it should maintain its own shape, right? And when you're printing another layer, so it means that you are putting a weight on it, right? So it should not spread, right? So, and at the same time, the flow should be uniform. How we are going to achieve the uniform flow, and at the same time, how you are going to retain or maintain the shape of the scaffold is a challenging. So making of the bio ink and controlling these ink formulations, and then while you're printing it, lot of parameters are there. How much pressure you're applying to push your bio ink to print, and at the same time how much is the the speed of your printer is moving. So lot of parameters you have to optimize to get a nice printed scaffold. That's where the challenges are lies to go for any 3D printable scaffolds. So we have optimized the conditions and we are able to print, and this particular paper is already published in International Journal of Biological Macromolecules. So and you can see that how we have optimized this printing, right? So you see that we have to we have to make bio ink, and we have to understand the printing speed. You can see it, and at the same time we have to understand the rheological characteristics of this particular ink. So when you are preparing the bio ink, and we have to understand what is the viscosity and what is the all the shear rate and shear thickening behaviors and all. And once we are able to optimize this rheological characteristics of our bio ink, and then we have to move on to the 3D printing parameters. So there majorly what are the 3D printing parameters can have influence on your scaffold printing. So you see that the printing speed, when you are doing the printing speed, and at the same time the pressure you applied. So, and at the same time it may not be the same parameters when you are talking about the composites and as well as the pure polymer, right? So because when you are having the composite, you will have a different rheological behavior of your ink. So that's where it will have an a difference in the printing conditions. Okay, so then After printing, then we have done the studies for bone formation. So what is our scaffold? Is that it will regenerate the bone. So once if you put the scaffold in a defected area, that particular scaffold, it should be able to regenerate our own bone, and at the same time it has to dissolve. So for that we have to understand whether really it is happening or not. So that studies we have done, and you can see that this is a pure PLA and PLA MBG. First day you can see it, how this nice formation of hydroxyapatite is formed, and with the zoomed images, and when it is coming to this 14 days, it is completely covered with hydroxyapatite. It means that our scaffold can have a nice bone formation when it is done. And at the same time, it should have a mechanical stability also is a matters, because when you are playing with these materials in bone implants, and we can see that elasticity and other characteristics also we have performed. Then so after printing and after understanding this hydroxyapatite formation, so we have done the in vitro studies, and you can see that the cell proliferation is happening. So incubation period we have tested up to 21 days. You can see that how the cell proliferation is happening, and cell viability also, you can see that the cell viability is there. And we have done the gene expression also, and ARS staining also we have done, and you can see that in the composite case we got an excellent performance. And here we can see that ALP studies, and we are able to get a very good performance in case of this composite. But the issue is that you can see here there is some dead cells. There is some reason. Okay, so to overcome that reason, again we have gone for the further modification of mesoporous bioactive glass with amine grafting. So MBG will have a mesoporous bioactive glass, will have a hydroxyl groups, and we have grafted the amine to this mesoporous bioactive glass, and then we have done the further modification with even the PLA. So then based on that, we have done the first one is mesoporous bioactive glass we have modified. Then we have also modified the polylactic acid. Then finally we are able to make the scaffold. And this particular work, actually we have filed a patent because it is performing far better than the previous one. So here you can see this actually what happened. So not only the particle size, when we want to go for good adhesion or fluorofilation of cells, we should have a positive side, the zeta potential. So pure MBG case, which we have loaded in previous formulation, the zeta potential value is in the negative side. Once you do the modification, move on to the positive side. That's where actually we wanted to have a better performance to avoid the cell death ratio. Okay. So, and we have done AFM studies to understand the surface morphology, and we have done the XRD and other studies. So we have also performed the antibacterial studies, and we can see that hydroxyapatite formation, and you can see here IDAX values. Here we can understand that what is the hydroxyapatite formation composition, we got it. And then for this also we have done the cell proliferation and cell adhesion. So here you can see that the dead cells is not there. So okay, so this is where actually we want to achieve. So having even with all these functionalized composites, we are able to control the death rate of cells. Okay, so then. For this one, after having this, so we plan to proceed for a patent, and we want to do some in vivo studies. So for that, we had a collaboration with Sri Venkateswara Veterinary University, and we have done the cranial burr hole implants to a mouse, and then you can see that after 12th week, and it is completely covered once it is implanted our scaffold. So this is where actually we are, and further studies we are doing on this particular activity before going for clinical trials. So then this bio implants, like bone implants, we are working continuously, is going on, but we are also started working on skin patches. So this is actually this is also a patent we submitted, so that's why we are not much disclosing these things. So here it is actually we have developed the 3D printed PLA QNLC scaffold. Here it is actually you can see that nice pores. So this type of scaffold making in a conventional process is very difficult, right? So controlled porous things. So to make this nice mats, you see that how nicely it has printed without having any disturbance in the porosity, right? So that's where the ink formulation and the printing parameter optimization, it will take a very long time to optimize. And here we have loaded the we have developed the nanolipid carriers, and then we have loaded the quercetin in that, and then we have reinforced in the polylactic acid, and we made a bio ink, and then we have optimized the all printing parameters, and we are able to achieve a nice 3D printed skin patches. So we have done the all antibacterial studies. So you can see here how it is working PLA QNLC, and we have done the PLA quercetin and then PLA nanolipid carrier with quercetin. So that is performing far better than the pure PLA with a drug. So for this, actually, after doing all whatever we have discussed earlier for related to in vitro studies, so then we move on to the animal models and means in vivo studies. So you can see that this is a control, and we have created a defect, and that defect, without having any scaffold, you can see that even after 21 days it didn't heal. And then whereas in case of the pure blank PLA 3D printed one, we have implanted, and you can see that still it is not cured even after 21 days. And here it is the drug loaded in PLA scaffold. You can see that still it is there is a defect. But whereas in case of our formulation, nanolipid carrier and loaded with the quercetin and then made a PLA QNLC composite, within 14 days it is able to cure completely, and you can see that there is no any abnormalities on the skin. So it means that if any wounds are there, and if you are able to place our patches, it can cure within 14 days of time. This is one of the major finding we got it, and we have also done the biochemical assessment and histological studies also we have performed, and we can see that there is no any deformations in this. And then we are also working on corneal patches. Okay, so the corneal patches for this one, this is also we have published, and we can see that how we are able to print the corneal patches. This is our bioprinter where we can print the all cells and as well as the biomaterial, and we can see that transmittance of cell loaded hydrogels, because when we are using these corneal patches, transmittance is the one of the major parameter how it is performing it. So this is performing well, and this is a pore size of the hydrogels for these corneal patches we prepared, and this is all MTT and live dead assays we performed for this one. And we have also published another one more paper on these corneal patches. Okay, and this is what, yeah. So on biomaterials we have done, and we are continuously working on this and for variable materials. Now actually I want to give some glimpse related to the health, especially like air pollution. The reason is that here also we are working on polymer composite which can separate the carbon dioxide. Okay, so here it is, we have a benchmark technology, global benchmark technology at present. We have transferred technology to the industry for to capture the carbon dioxide from the industrial flue gases, and at the same time we are having multiple applications in biogas enrichment, converting biogas to the CNG, which can be used for the automotive fuel. Okay, and in this case, actually, we are having a special mission from the government of India. Reason is that Delhi pollution, we know it, how, Delhi people are struggling for the pollution. So, because of the pollution. So that's where actually we are, assigned to demonstrate, ambient particulate matter and carbon dioxide capture unit in indoor and semi-indoor conditions. So actually we planned for the outdoor setting up, air purification. It's a big challenging. Actually already few people tried from IIT Bombay, IIT Delhi, and as well as BHL and our own sister laboratory CSIR NEERI. But the results are not prominent. Then we move on to the indoor and semi-indoor. The reason is that people will stay at office 8 to 10 hours per day, and they will stay at home 8 to 10 hours. If you are able to provide hygiene air at least 80 to 90% time duration, that's great achievement. So based on that, we have designed for the indoor and semi-indoor. Okay, and you can see that air or Delhi breathe. So you can understand the where we are now. So 364 daily average AQI at 4 p.m. one day we have taken, and you can see that it's tremendous pressure in there with the public also, because the reason is that there is a lot of health issues related to this particular pollution. So that's where actually we have worked. And another thing is that especially in outdoor, we will find the particulate matter, right? So PM10 and PM2.5, which is PM2.5, which is coming out from the especially from automotive in vehicles, right? So from vehicles. But the issue is that that's where actually Delhi sometimes they will announce outside pollution is so high, be there at home. They used to announce. Is really we are indoor is safe. Then we started working on it. So you can see it actually, World Health Organization is telling that not only the particulate matter, CO2 also can have an effect on our health. So 350 healthy and general indoor air, okay? But at present outdoor is around 417 to 420, and after 1000 it will have an effect on us. Can you guess how much will be the CO2 at this present in this auditorium? Do you know that definitely it will be more than 3000 ppm? I can assure you if you check it. Okay, so it means where we are. Okay, so because we have done extensive studies, I am not telling just like that. Okay, and you can see that how our health can damage when you'll go for higher CO2 concentrations. Okay. And in this case, you may have a doubt. We are already having indoor air purifiers. What new are going to do it? Is it or not? So there is a lot of indoor air purifiers available. But all the indoor air purifiers are having only activated carbon one, which can remove maybe the VOC, or maybe they're having HEPA filters, which can remove maybe the particulate matter, or maybe bacteria and other things. None of the indoor air purifiers are having CO2 separation. So that's where actually, and only now the solitaire power globally, only one company from the Finland, they have come up with this technology, and they are now already they have installed in more than 5 shopping malls, and in Singapore they are going to plan in a big way, and you can see our results, how we are working on it. You see that we have done a study at our, we are having one BTech, one program, and there 9 to 9:30, 9 o'clock we started taking reading. The class started at 9:30. So it means all people are occupied, and within 45 minutes, it reached to 3,500 ppm in a classroom. So where we are staying it. But in Delhi, we are telling that you people don't go outside and sit at home. Close the doors. So is it really healthy? So, and then we have done a variation of CO2 level inside the car with 4 persons. Right? So nicely we are closing the windows and sitting inside and switching on AC, and we are traveling hours together, 3 to 4 hours, 5 hours without non-stop. So 10:42 and 11:06, it's hardly like 20-25 minutes with the 3-4 persons here they have mentioned, and it reached to the 6,000 ppm. Can you imagine? 25 minutes. So that's where actually, and in our auditorium, it's a capacity of 240, and there it reached to the 3,000 ppm. So like that, and the living room at your home, where it is, right? So you can see that from 500 to 2,500. So with the people of 1 or 2, it will reach. So for that case, we have come up with the technology. At present, this particular technology is already reached to the TRL level 7 to 8, and we got a certification from as per the standard of OSHA and as well as ASHRAE, and about to release this technology into the market. So here it is that we are able to remove the particulate matter with the efficiency of 95.6% at Delhi, and you can see that the World Health Organization limit is 15, and the inlet at that day it is 114 PM2.5, and outlet is 5. It is a far lesser than World Health Organization. Okay, so and PM10 is 45 is a World Health Organization limit, but the there it is 269, and we brought down to 6. So it means it is far below the World Health Organization limit if it is processed in our, this one. And this is these studies we have done there in Nizamuddin railway station at Delhi, and you can see that from 1150 to we brought down to 600 ppm. So this extensive studies, and this is Amity University at Delhi. We have done the studies, and there also we are able to reduce the CO2 levels. And you can see that. Can you play this video? So this is our last slide. Okay. Yeah. So. So actually, in this, the challenges, here it is, we are having a technology for industrial flue gases. Already we have proven, and already we transferred to the industry, and we are, making in a larger units. But when it is coming to the flue gas cases, the CO2 level is more than 10 to 15%. All other gases are there. So in that, selectively picking the CO2 at the high concentration is somewhat okay. But whereas in case of air, the CO2 level is in ppm level, right? So if you're seeing that all other gases, nitrogen, carbon dioxide and other gases are there, how it is going to take selectively at the ppm level CO2 alone is a challenge. That we have achieved, and it's bad luck. You can see that the 448 ppm is gone inside the system, and then outlet is a 0 ppm at the ppm level concentration. That is a breakthrough in this particular technology, and this is already certified, and now for the first 5 months it is running in the industry where the 20 people are sitting and working whole day, and now it's about to launch to the industry. It means commercialization. So soon, maybe in another 2 to 3 months, it's going to be there in the market. So that's what our technology. Yeah. Thank you. So yeah. Actually, I want to say thanks to my funding agencies, my collaborators, and all my group members. We are having a very big group. I can say that handling of more than 22 members are our group strength, and all are working in different domains, working on CO2 capture for indoor flue gas, biogas enrichment to CNG, and biomaterials, 3D printable, indigenized 3D printable materials. And we have transferred two technology to the industry, indigenized 3D printable filaments to Monotech System Limited, and that is already in the market. So that's what. Thank you, Honorable.
Thank you very much, sir. Very nice presentation. Multiple subjects also you covered. Biomaterials as well as carbon dioxide capture. Very much interesting and currently relevant also. And hope any doubts are there. Now we can clear it from the audience.
Yes. Perfect question. Yeah. So at present, whatever the technology is having indoor air purifiers, which is having all setup PM, then VOC removal, and then virus and bacteria. So good system at present in the market is in India, it's 65,000 to 75,000. But this system as of now, because it is in the initial stage of development, the cost is going around 2 lakhs. Okay. So again, putting a profits on all, it may go beyond that. When you'll go for a larger production, so here it is, we are using a PLC based system. When in ACs and all, they used to use HMI system, then the cost will drastically, it will come down. And then they're using fiber, outer bodies, and we are using metal body. So, and again, we are planning to bring down to less than 1 lakh. I don't know how much is feasible, but our target is to bring down to less than 1 lakh the price. At present, it is coming around 2 lakhs plus it is there. Yeah. So, if there is no questions.
Any more questions?
Yeah. Thank you.
Thank you very much.
I'm inviting Dr. Nida John to present a memento to Devi Babu sir.
We are resuming the talk from Joseph Honip. Can you hear, sir? Excuse me, can you hear?
So I'm not sure if you can hear me.
I can hear you. We can hear you. Please present your
message.
slide. Yeah.
Yes,
Welcome.
so it's okay. Maybe my speaker doesn't work at the time. So that's okay. So thank you very much for the invitation to your conference, and especially to Dr. Rajesh. It's a great privilege for me to talk to you. I'm very sorry for the technical problems. We should have checked it before, but Google Meet is probably not the best means. I will talk about biomass liquefaction, especially wood liquefaction, which we do at our laboratory. Please move. Please move to the next slide. Please move to the next slide. Yes, okay. So we are located in Gdańsk, Poland, so you can see the route to Gdańsk. If you go on feet, you will need about 1 year. If you can go 10 hours a day, but the connection is better. For the flight, I need about 20 hours to come to Kerala. And please, next slide. And the Gdańsk University of Technology is the largest technical university in Poland. And we have different faculties. Chemical faculty is one of them. Please, next slide. The connection was broken, excuse me. And at our Department of Polymer Technology at the Chemical Faculty, we are working now on many environmental friendly approaches, like new raw materials for polyurethanes, no isocyanate polyurethanes, biodegradable polymer composition, and so on. And one of the problems we are working on are polyols obtained by liquefaction of lignocellulosic biomass. Please, next. Please, next slide. And lignocellulosic wastes for polyurethane components could be used after liquefaction from wood or waste wood. In this way, we can obtain polyols, but these are not like usual polyols used for polyurethanes, because there are different fragments of cellulose structure, and the functionality is not exact 2 or 3S in usual polyols for polyurethanes. There are branch structures coming from lignin, and for this reason, these polyols are especially suitable for cross-linked polyurethane matrices for different composites. As you can see, the wood is composed from cellulose, which is about 1/2, lignin about 20%, and hemicellulose the next 20%. So starting for the composition, we can expect different particles after splitting chemical bonds by diols or triols used for this approach. Please, next slide. And next slide, please. And this approach, generally speaking, obtaining for polyurethane wood composites or polyurethane fiber, glass fiber, or different fiber composites is based on obtaining biopolyols by liquefaction of wood, of different origin wood, and the polyols are complex mixtures. As you can see, there could be glycerol, polyethylene glycols, which are used for this process, and also condensated glycols and cellulose and levulinides. So there's a mixture, and the problem is to influence the composition of the mixture to obtain best results as composites or polyurethanes. When we produce by polyurethanes woods composite, then there's also possible reaction with with wood fragments, with reaction of wood structures with isocyanide groups, and at a pressure and higher temperature, the binding between wood particles and polyurethane during the reaction of polyol and the isocyanide is obtained. This next slide. Then there were different approaches, like using alderwood sawdust from a factory, and the sawdust was liquefied with glycerol and polyethylene glycol. You can see what is crucial is using the high mass ratio of solvent to biomass. It can be even about 10. Then the problem is that the obtained polyols still contain rather big amounts of solvent because it's not separated. I think it is a bigger problem, the biggest problem now, which doesn't allow to get high quality polyols. But nevertheless, the polyols we obtained are quite useful. And after selecting the best condition, like temperature and time. Please, next slide. Then the liquefaction is solvolysis degradation of the wood structure. This next slide, which is catalyzed by acids, sulfuric acid in this case. Please, next slide. And so we have investigated the effects of temperature and reaction time. And after that, the reaction was controlled by measurements of hydroxyl number, water content, degree of biomass conversion, and also by a polyol viscosity to select the best raw material to obtain polyurethane resins. Please, next slide. So there's a picture of it. So alder or oak sawdust, shredding, solvolysis, liquefaction, and biopolyol due to some degradation and oxidation. It is brownish, and after that different biocomposites were obtained. Like here, one of the biocomposites was produced using basalt, mud, and also with addition of flame retardants to obtain polyurethane composites with very low flammability. Please, next slide. It is an illustration of dependency of the hydroxyl number during liquefaction with process condition like solvents, temperature, catalyst, and time. Please, next slide. And depending of the condition, you can see different hydroxyl numbers were measured from about 250 to about 700, and the conversion was in many cases over 90%. Water content was low, and the obtained polyols could be used without without dehydration of water. Please, next. The mechanical properties, as you can see, were quite different. It were investigated also after thermal or UV aging to find a sample, a polyol which could deliver best impact strength, high mechanical strength, and high stress transfer capacity. Please, next. Dynamic mechanical analysis show the dependency of modulus on temperature, and the dependency is dependency is similar, and the glass temperature refer to the polyol used, but as we can see, the character, the mechanical character is like of rigid cross-linked systems. Please, next. And about this shortly presented results, we can see then it was possible to obtain biopolyols in environmentally friendly way using waste materials, and the content of biocomponents in the polyurethanes was about 90%, and biocomposites were obtained with basalt smart and flame retardants showing high flexural strength and good adhesion of polyurethane resin to the basalt fibers. So in this way, a safe material was created for fire protection applications. Please, next slide. To to get the best result, different biopolyols were investigated using polyethylene glycols with different molecular masses in the course of biomass liquefaction process, and the impact of molecular mass was stated by the properties of obtained polyurethanes. Then again, we have here possible reactions which may occur during the biomass liquefaction, but in the result we still have a mixture of different components and a quite big amount of unreacted polyethylene glycol of different molecular weight, and and depending on the amount of components, we can have different rigidity and different mechanical stress of the obtained polyurethanes. Please, next. Please, next slide. And we have checked that the process of biomass liquefaction is more intense when we use shorter polyethylene glycol chains, and it leads to higher biomass conversion. And there's dependency of viscosity. The viscosity is important for technical processing of polyurethanes. Dependency on molecular weight on used polyethylene glycols. But the increase of viscosity was connected with lowering of the biomass conversion ratio. We have used special Herschel-Barkley model, shows the behavior of polyols depending on shear stress during the mixing, and the products showed shear thickening behavior, which is typical. Please, next slide. Also, average molecular weight decreases with the use of polyethylene with shorter chains, which should be expected. And one of the findings was that difference between samples were smaller than predicted, which means that the reaction proceeds until a certain molecular weight is reached. The functional groups were identified using infrared spectroscopy, and the different structures are shown on the picture. Also, the GPC delivered the average molecular weight from about of the value about 4,000, but as I already mentioned, there is a really visible amount of unreacted glycols in this mixture. Please, next slide. For the polyols thermal analysis has shown, then higher molecular weights of polyethylene glycol increases the degradation temperature of obtained polyol, which is shown here on the result, where DTG traces show us the highest conversion at specific temperatures, which is also visible in the table showing result of thermogravimetric analysis of the bio-based polyols. Please, next slide. Due to the time restriction, I cannot discuss it in details, but it is already published. It belongs to the PhD thesis of Olszewski, who has just finished his work and will defend his thesis maybe in 2 or 3 months. And some of the experiments was carried out in partnership with Latvian State Institute of Wood Chemistry. And in this investigation, we produced polyurethane foams, also polyurethanes, polyisocyanurate foams with higher temperature of application. The structure, microstructure of manufactured forms is quite good, as you can see. Please, next slide. And there are characteristic of the forms like average pore size, diameters, and so on. It was all investigated during this process to find best structure. Please, next. And also the forms were checked by compression tests, and the difference between perpendicular and parallel directions are obvious, but not so big as sometimes it occurs. It depends on the geometry of forms, of bubbles, foam bubbles. Please, next. There are results of thermogravimetric analysis as we compare the traces for forms obtained with different molecular weight biopolyols. So there are not big differences. Please, next slide. But in details, we could check that the temperature of losing 5% of white increased from 200 to 200, almost 250, depending on the foam time. You know, it also depends on the presence of short chain polyols in the structure, and also the maximal degradation temperature shifted of about 30 centigrade due to increase of cross-linking density in that forms. Please, next slide. So here are selected parameters of combustions, which was characterized by heat release rate of the obtained forms. Please, next slide. It is from the report of Mr. Olszewski. And there was increase of total heat release with increasing amount of bio-based polyols, because the used polyols were a mixture of biopolyols and commercial polyols. Also, biopolyols caused difficulties in forming a stable char layer on material surface. That's why the degradation was higher in that case. Also, with increasing of total smoke generation. Then it means that the flammability of the obtained forms with using of biopolyols must be reduced, also by better choice of polyols or by addition of flame retardants. Please, next slide. And these polyurethanes and polyols were used to produce polyurethane wood composites when there were pine wood shavings, small particles below 2 millimeters, and polyurethanes matrix produced from the biopolyols.
Sir?
It means
Can you
produced
finish by 5 minutes?
with the help of wood liquefaction. In this way, the wood derived chemicals in the composition of produced composites was quite high. And please, next.
Me, sir.
Next.
Can you finish by 5 minutes? We are running short of time.
Yes, I will finish just now. So please, next slide. So we have obtained the composites, polyurethanes, wood composite. Please, next slide. And we have expected it for voids and mechanical bonding. Please, next. So there are mechanical properties for different amounts of biopolyols. Please, next. The more biopolyols means here lower impact strength and lower mechanical properties. Please, next. So, please, next. Water absorption. Please, next. Mechanical properties and thermal properties for different amount of biopolyols. Please, next. Then the storage modulus in the dependency of temperature. You can see that the highest values are for polyols without biopolyols, unfortunately. Please, next. So please, next. And here is the table with thermal properties. Please next. And generally, our studies have shown the possibility of producing polyurethane wood composites with different amount of wood waste, and the manufactured composites showed mechanical properties comparable to commercially available products such as chip boards and medium density fiber boards. Please next. So
Thank you very much, sir. It was nice presentation. Thank you so much for joining.
And there is a picture of our Faculty of Chemistry. Please next. And the picture of main building of Gdańsk Technical University taken today is on the next slide. So thank you very much.
Thank you, sir. Thank you so much.
Thank you very much for your attention, and greetings from Gdańsk University of Technology.
Thank you. Thank you. We'll move to the next presentation by Dr. Anandakumar S. from Department of Chemistry, College of Engineering, Guindy, Anda University. Hope you are online, sir.
Now it's time for tea break. After 5 minutes, we can continue the sections.
Once again, sir.
Hello, sir.
Yeah, I'm just downloading my To all of you, sorry for the inconvenience.
Sir, 1 second. 1 second.
Yeah.
Sir, we will tell one introduction, then you can start. I'm giving the mic to our chairperson, Dr. Needa John.
Hello, sir. Hello.
Yeah, can I present?
Yeah. So I'll give a small introduction. Dr. Anandakumar Srinivasa, professor, Anna University, completed PhD from Anna University and postdoctoral from Denford University, UK, and Institute of Polymer Composite University, Minho, Portugal. He served as Assistant Director of Central Entrepreneur Development, Anna University. He has more than 65 publications in reputed journals and has contributed 8 book chapters for the international publishers like CRC, Academic Press, etc. And he is editor of eco-friendly nano-hybrid materials for advanced engineering application. He has completed several national and international projects funded DST DRDO. He received Active Researcher Award for the year 2014 from late Dr. APJ Abdul Kalam for his outstanding contribution in nano-hybrid coating and composite. His team won Runners-Up Award for Technical Innovation Nanomaterial from Honorable Central Minister Anandakumar in the year 2015 during APM 2015 held in Bangalore. Recently, he received Technology Innovation Award 2021 from Honorable Education Minister of Tamil Nadu. Last year, he was awarded Scientific Medal from IAAM, which he received from Stockholm, Sweden on 28th August 2023. Furthermore, he received Dr. Mahalingam College of Engineering Biocentenary Polymer Science and Technology Award also. So welcome, sir, for this international conference, Bpgc 2024. Welcome, sir.
So thank you very much for the introduction, and my topic is on semi-IPN coatings for paper and wood based on bio-based polyurethane and biodegradable polylactic acid. Can you move to next slide? Yeah, so the background of this investigation, as you know, both sustainable development and green economy, they require brand new materials. So natural polymers, biopolymers and synthetic polymers based on annually renewable resources are the basis for the present century portfolio. So the bio-resourced materials, they are going to gradually replace the conventional fossil fuel based polymers as they have become cost and performance competitive. And the reason why we started working on biopolymers due to the following reasons. They are lightweight materials, they have very good corrosion resistance, they are abundantly available, they are eco-friendly, they are compostable, and they do have a unique property like thermal acoustic insulation, and apart from all, they are less expensive. So these are the reasons why we started working on bio-based polymers and biopolymers. Next slide, please. So the need for bioplastic, as you know, the following are the needs which I have summarized here. Inadequate fossil fuel resources. There is a speculation that the fossil fuels are going to last for another 30 years. Therefore, we have to have an alternative. So the best alternative is the plant-based polymers, or there are routes where the polymers can be obtained from soil, and you can get it from microorganisms. These are all the possible ways by which we can synthesize polymers. And there is a pricing instability of fossil fuel as well. And contribution of fossil fuel as a feedstock to climate change, because when you start using fossil fuel, you know the culprit is carbon, and we are witnessing a lot of problems here in India. Globally also there is a climate change because of the fossil fuel polymers. And its association with the waste disposal. You know, the polymers obtained from fossil fuels, they are very difficult to dispose. Therefore, it becomes a very big solid waste issue will be there. So moving to the above reason, we started synthesizing on polymers, or we started using polymers from plants and animals. So one of the bio-based biodegradable polymer is polylactic acid, which is a forerunner as far as the several industrial applications are concerned. Hence, we have chosen polylactic acid for our study. So a bio-based metal is a significant portion of carbon is based on plant. That is 90% of the carbon from biocarbon, whereas 10% of the carbon is from fossil fuels. So that combination, what we call as a bio-based polymer. And the conventional biodegradable plastics, these are the plastics which will undergo degradation by the action of heat, microorganisms, and they will break down into products like carbon dioxide and water. Next one. So there are two different kinds of polymers, that is bio-based polymers and biodegradable polymers. Some of the bio-based polymers need not be biodegradable. But polylactic acid is a bio-based biodegradable polymer. That's why we have chosen polylactic acid for our study. Next slide, please. Okay, so what we have done is we have made a corrosion-resistant coatings based on polylactic acid. Why we have chosen corrosion-resistant coating is corrosion is a universal problem where lots of countries are spending almost 7% of GDP for the prevention of corrosion alone. India alone spends 5% of GDP for corrosion prevention because corrosion is a natural process which cannot be avoided, which can only be prevented. The best method by which corrosion can be prevented is corrosion prevention coating. As I already indicated, there are several synthetic coatings which are available in the market for the prevention of corrosion. But owing to the reason which I already mentioned, bio-based polymers, they play a pivotal role as far as coating development is concerned. So we have made up polymer coatings because they are widely used for the corrosion-resistant application. So the importance of bio-based polymer coatings have already indicated that they will reduce the environmental impact, and we need not rely on fossil fuel based polymers. So that is one of the reasons, we need to work on this bio-based polymeric material. And the key challenges with PLA, as far as PLA is concerned, it's a very brittle material, therefore it causes cracking in the coating, and the high cost also limits its usage for specific end-use application. And it has got poor antimicrobial property because it is completely biodegradable. And therefore modification of PLA with several additives inevitable. Accordingly, we have carried out the research project for this particular work. Next slide, please. So the main objective of work is to develop a semi-interpenetrating polymer network by utilizing PLA and polyurethane we obtained from castor oil, because one of the ingredients used for polyurethane synthesis, isocyanate, which is toxic in nature, and also the polyol. We use several polyols, but we have used plant-based polyol for our synthesis. So we formed a semi-interpenetrating network between polylactic acid and polyurethane, which we made it as a coating formulation. We applied on mild seal specimen to study its anti-corrosive behavior. So the purpose of polyurethane is to enhance the toughness behavior of polylactic acid, because as I told you before, polylactic acid is very brittle in nature. So in order to make it soft and flexible, you need to have a toughening agent. Therefore, the castor oil based polyurethane was used as a toughening agent for polylactic acid. And also it will enhance water and antibacterial resistance, for which we have used a Schiffs-based compound. So we made a co-PU, that is polylactic acid polyurethane copolymer, to which Schiffs-based compound is added in order to increase the antibacterial property and the corrosion resistant property as well. So specific objective is synthesis of PLA-PU copolymer, and to incorporate Schiffs base into this copolymer, we make a anti-corrosive coating, and to assess the suitability of the coating for the intended application, especially for corrosion resistant application. Next slide, please. So for which these are all the materials that we have taken, that we have utilized for fabrication of coating material. Polylactic acid, which is we got it from Nature Tech, and castor oil based polyurethane, which we obtained from plant based materials. So we obtained here there is a place in Tamil Nadu called Banruti. That is where we got this particular resin, castor oil. And Schiff's base, we have synthesized the Schiff's base, and the methylene diisocyanate is used as a isocyanate component for the preparation of polyurethane. Next slide, please. So this is how the coating was made. We have a PLA polymer and a castrol PU. Both of them are mixed together. They form a semi-interpenetrate. They form a copolymer network to which we add Schiff's base, and PLA PU forms a semi-IBN through which the Schiff's base will be impregnated in the copolymer networks of PLA and PU. And finally, the coating is applied on wood and paper. So next slide, please. Okay, so this is how the Schiff's base was made. So vanillin and paraphenylene diamine were reacted together to form paraphenylene diamine based Schiff's base compound. As I indicated before, the importance of Schiff's base is it provides antimicrobial property, enhances flexibility and compatibility. Next one. Okay, so the properties of castor oil based polyurethane. So we have added 1% castor oil is mixed with 1% of Schiff's base, and we did the high shear rate stirring for about 12 hours. And when we do so, what happens? We are able to get uniform dispersion of Schiff's base in the polyol, which is then made to react with the MDI to get castor oil based polyurethane. And why castor oil? Because the hydroxyl value of castor oil is very high, 90%. Therefore, it is an ideal component for the synthesis of polyurethane. A lot of hydroxyl groups are there which can be reacted with the NCO to make a polyurethane coating formulation. Next one. Okay. So PLA PU synthesis. PLA, we dissolved in DCM, and while PU is prepared separately, both of them are mixed together, and they form a homogeneous coating material, which is applied as a coating on wood, any substrate. It can be applied on mild steel, can be applied on wood and glass as well. So the semi-interpenetrating net is formed by combining a cross-linked polyurethane network with a non-cross-linked PLA. So to get this PLA PU semi-IPN network coating composition. Next one. Okay, so we have studied the interaction of the PLA PU by means of IR. So from the IR, we were able to understand there is a successful dispersion of co-PU into PLA. That is, castor oil-based polyurethane were impregnated or dispersed evenly in PLA, which is confirmed by type 2 hydrogen bonding. In fact, there are 3 different types of hydrogen bonding which I have indicated here. Type 1 hydrogen bonding is the hydrogen bonding of NH with the carbonyl group. Type 2 is NH with the OH group. And type 3 is NH with the N group. So we observed different types of hydrogen bonding as far as the co-PU and PLA is concerned. So the successful dispersion of co-PU into PLA is confirmed through type 2 hydrogen bonding that is formed between the OH and NH groups. And the Schiff's gas incorporated system enhances the flexibility of PLA, which we realized by means of type 3 hydrogen bonding. Therefore, there is a bonding between PLA and PU and the Schiff's base with this network, so which are confirmed by means of IR spectroscopy. And also the formation of a hydrogen bond between PLA and PU is confirmed. The absence of NCO group indicates the completion of the reaction, and we get the polyurethane coating. So the hydrogen bonding leads to improved flexibility and the toughness in the PLA-PU network. So that is the purpose of the main purpose of the research work, is to enhance the toughness of this polylactic acid, which we were able to achieve by means of bringing the castrol-based polyurethane into polylactic acid, and the antibacterial property is substantially increased by the incorporation of Schiff's base, and this was confirmed by spectroscopy studies. Next one, please. And we have also done the SEM analysis. and we could see, from the electron microscope, we see the shift-based compounds creates a free volume in the PLA matrix, which leads to flexibility formed in the SiPn. So when we took the SEM, so it shows the plastic deformation. The plastic deformation indicates the PLA matrix has been toughened by the incorporation of polyurethane. Next slide, please. Okay. Similarly, we took the XRD pattern. As you can see, the top one with blue color corresponds to PLA, co-PU, SiPn network, whereas the bottom one corresponds to neat PLA. So PLA exhibits characteristic crystalline peaks, while PLA-PU shows a reduced crystallinity. Therefore, what happens? The crystallinity of PLA is reduced by the incorporation of co-PU, so which is again confirming the fact that the PLA-PU act as a toughening material for PLA. The incorporation of PU disrupts the crystallinity of PLA, leading to a more flexible semi-interpenetrating nucleus. The XRD of PLA, PU, SiPn blend exhibits broad characteristic peak of PLA at 2 theta is equal to 17.9. So this is the 17.9, and the other one is 19.48. Okay, so what happens? The crystalline behavior of the PLA is disrupted by the incorporation of PU. As a result, what happens? The PLA-PU becomes amorphous, whereas the neat PLA is a crystalline nature, which is confirmed by XRD analysis. Next slide, please. And interestingly, we observed a decrease in the glass transition temperature. For neat PLA, the glass transition temperature is slightly higher, and the crystallization temperature is also slightly higher. So when we incorporate the polyurethane segments into PLA, what happens? There is a decrease in the crystalline temperature. The crystallization temperature there is a 5-degree decrease in the crystallization temperature, and there is also a decrease in the glass transition temperature, which again proves the fact that the polyurethane segment is acting as a toughening agent for polylactic acid. Next slide, please. So once the coating formulation was made, so what happened? We tried to use it for different applications. One of the applications for corrosion resistance. So we already published some papers using this material, and we thought of using it for different substrate. In this case, we have tried using this for wood substrate. That is MDF, that is medium density fiber wood we have chosen, and on which we applied this coating. So the PLA-PU coatings showed better adhesion to the kraft paper due to its semi-crystalline nature, and the coating weight was obtained by a dull coat over the kraft paper, which is found to be 1.52 plus or minus 0.082 gram per centimeter squared.
Excuse me, sir.
And accordingly,
sir, excuse me. Can you finish?
Next slide, please. I'm going to finish. Next slide.
Sir, thank you.
You go to the conclusion, please. So the previous slide, please. Yeah, this is what MDF wood water absorption is found to be very, very minimum. When you apply this on wood, what happens? The water absorption seems to be very low because of the presence of the IPN and also due to the presence of the shift space. So finally, conclusion. Can you go to concluding slide? Okay. So in our work, we were able to modify PLA with co-PU using a semi-interpenetrating network, and the IR spectra shows there is a possible interaction that occurred between PLA-PU and the PLA-PU semi-IPN with shift space. The DNC analysis proves increased blend compatibility with a reduction in the melting point, crystallization temperature, and glass transition temperature. And the incorporation of shift space in co-PU enhances antimicrobial property as well. Similarly, the coating of SiPn on kraft paper and wood shows a superior adhesion properties when compared to neat PLA. Hence, this particular coating can be used as a suitable replacement over synthetic coating that are existing for the substrates like wood, steel and glass materials. Next slide please. And the key findings, the PLA SPN coatings offer superior properties. They can be used as an eco-friendly alternative to the existing fossil-based coating systems. And for future potential optimization of the formulation for specific industrial applications such as packaging, furniture and building materials can be done. Next slide. So improve the antibacterial property, again test performance under real world conditions. Similarly, potential applications for the developed coating systems or developed polymer systems can be in packaging, wood protection and medical devices. Next slide. Okay. So thank you for your patience, and I thank Cipet Kochi for giving me this opportunity. I'm sorry that I am unable to, I'm traveling. That's why if there is any a delay or any technical smack, I request your apology for that. Thank you very much.
Thank you, sir. Thank you very much. As we are running short of time, we are skipping the questions and we are moving to the next presentation. Thank you once again, sir. Thank you.
Thank you.
Next presenter is Dr. K.N. Shiba, is Associate Professor in the Department of Chemical Engineering, NIT Trichy. She completed BTech in Chemical Engineering from Madras University and MTech in Energy Engineering from Bharatidas University Trichy. She obtained a doctoral degree in the field of energy engineering from National Institute NIT Trichy. She has undergone training program biomass gasification in University of Saskatchewan, Canada. She has completed major projects DST, MNRC, 3 major process sponsored DST, Agrotech, SCAR and CPB, and currently undergoing under her supervision. He has published more than 50 research articles in peer-reviewed journals. Currently, she is presenting sustainable development in biofilm utilizing ultrasonic assisted glycerol organazole processing derived cellulose from banana pseudostem. Welcome, madam, to this presentation. Over to K.N. Shiba.
Madam, thank you for the invitation. I'm just connecting with the presentation. Are you able to see my presentation? One second.
No, madam, no.
One second. Are you able to see now?
Yes, ma'am. Okay.
Yeah, thank you for the opportunity. It's already late. I'll just move on to my presentation. I'm just here presenting few of my works that are done using the biopolymers and predominantly extracted from the banana pseudostem. Second, I'm able to move the slide. Are you able to see now? Okay, so this is our wonderful institute. I invite on this occasion, I invite you all to visit our institute, NIT Tiruchirappalli, which is a beautiful 800 acres campus, much larger than the campus of IIT Madras. So this work, a part of the work that I'm going to present here is based on the project that that is funded by the National Agricultural Science Fund, in which NRCB, National Research Center for Banana, is a lead center, and there are 7 cooperating centers, in which one of the cooperating institute is the Cipet Kochi. So I think I don't have to give much introduction on the biopolymers part, because so much is talked about biopolymers, and you know how it is being derived. There are synthetic biopolymers. There are polymers which are extracted from biomass, and polymers that are being biopolymers that are being directly produced by microorganisms. Because biopolymers are usually biodegradable and they are also biocompatible. That's why it is being preferred for a variety of applications, ranging from packaging to medical, textiles, agri-food sector, electronics, and cosmetics. And out of this biopolymer, we have utilized two predominant biopolymers. One is the cellulose that is extracted from the banana pseudostem, as well as we have used tapioca starch for another application. So we'll be focusing more on the cellulose-based biopolymers in this presentation. So as you know, banana is the most sought after perennial tree. Every part of this banana plant has its own values. You might be aware of it, and it's actually a perennial tree and gets cultivated most of the times. And much of the waste of banana plant or tree after harvesting the bunch is being discarded as a waste in most of the places. So this project is aimed at utilizing many parts of banana plant for better utilization or for better development of value-added products. And because the cellulose that is actually present in this banana pseudostem is highly rigid in structure, so it needs a
Excuse me. Excuse me. Excuse me, madam. Excuse me. Can you can
Ma'am, to present a memento to the Nita ma'am.
Good evening, esteemed guests, faculty, students, and staff. We have come to the end of this remarkable conference. On behalf of the organizing committee of Bpgc 2024 and on my personal behalf, I welcome all to this valedictory function. It's our privilege to have our distinguished guest, Shri Mithilesh Singh, General Manager, Petronet LNG Limited, Kochi, to grace this occasion. I request Joint Director and Head, Cipet IPT Kochi, Dr. K. Rajesh, to address the gathering. So before that, I would like to welcome all the guests to the dais. So please.
A very warm good evening, one and all present here. We are now coming to the fag end of our International Conference 2024. I hope you all enjoyed last 2 days. Compared to last year, this year we had also not only the academicians and scientists, we also had the industries presence also this year. So that was the highlight of the conference. And also regarding the participation, I could found that there is a good number of participation. So the credit goes to all of you. You people have already, last 2 days you have devoted the time for attending here. So needless to tell, all the sessions were quite interesting, and they have presented their the research work. So the last 2 days I had been attending most of the sessions, so I could find that it was very interesting, and I hope last days also, especially Balasubramanian sir speech might have motivated all the students also, I could tell, and other speakers were also telling presenting their research work, and this is all possible because of the sponsorship and support from different departments and also industries. In this occasion, I must thank the DST and also CSIR for supporting us for the fund support for this program, and also our platinum sponsor Petronet LNG Limited. Give them a very big big applause to them, because it was an essential part through which we could make it in a successful manner. Not only as a CSIR and the thing only meet the travel and other travel expenses of this only, but for conducting it requires more and more this thing. And also the other industries like NatureTech, PAPMA and other sponsors also have contributed to their extent so that this can be met. And in this regard, now I request there was oral presentation and poster presentation also. I hope the results are ready. We can go for the validity session and give the prizes. And also on the dais, Dr. Roy Joseph sir is there. He's from, you might be knowing, he's from Sri Chitra Tirunal Institute. And from the inception of our Cipet Kochi Center, sir is well associated with us for making, the curriculum and also giving the inputs. And also, sir has also has taken, various sessions for the faculties, also for the students here on the biomedical devices earlier. And sir is also recipient of the award from Ministry of Chemicals and Fertilizers, Government of India, 2 times. Yeah. So we have been fortunate. And Ashish ji is always supportive. He is here. And I also would like to congratulate my team who is behind, behind the screen, who has wholeheartedly given their contribution to make this success, especially from the Dr. Manjula. She was working for the last 3 months, and in association with Dr. KP Bhuvana, who was well experienced in organizing the conferences, and of course the other faculty members and also the officers and all other colleagues. They came and together to make this as a success. So needless to mention that Team Cipet Kochi has taken a wonderful team effort to make this as a success. So we should give an applause to all of them. So now the results are there ready. So I request Dr. Manjula Madam to announce the results. And also I request Midlesh Singh to give the winners, the certificates to the winners, please.
It is happy to announce the winners of this oral presentation of this conference. First prize goes to Mr. Joby KV, St. Joseph College, Mola Mattam. Second prize for oral presentation, Ashwini S. Warrior, CSIR, NIST, Thiruvananthapuram. And third prize goes to Saranya SS, SCTIMST, Trivandrum. In the poster presentation section, first prize goes to Aditya Salvi, Cochin University of Science and Technology. Second prize is, sir, please kindly. Second prize for poster presentation, Mr. Arjun Somarajan, Indian Institute of Space Science and Technology, Thiruvananthapuram. Third prize, Sabir Ujayam Padi, National Institute of Technology, Calicut. Thank you so much. Thank you so much. Dear participants, I request to kindly give your feedback about this conference on biopolymers and green composite Bpgc 2024. Kindly. Winners, please come and share your experience about this conference. Oral presentation, second prize winner, Ashwini S. Warrior.
Thank you, madam. Actually, it was really a good experience because it has been a long time that I have participated in seminars. So yesterday also I was speaking with somebody that I was doing an oral presentation after about 10 or 11 years. So because actually I'm a student and an old age student like that. So after a very long time attending a seminar felt like really rejuvenating. And over and above, something that particularly I want to speak out is regarding the hospitality of Cipet. Because from the time when I stepped into the campus, what I felt was that I have to really appreciate the hospitality of the staff and students of Cipet IPT. And I thank the Institute for this opportunity. Thank you all.
Sharanya, oral presentation, third prize. Sharanya is there.
Good afternoon all. I am Sharanya. I am from Srijitra. Actually, this is my first oral presentation. I actually participated in different types of poster presentation. At that time, I'm not feel any shyness because I already have experience. But this is my first platform for participating the first oral presentation. I'm just a few about myself, but this give very good opportunity. I just thank to my institute because they give that much facilities provided for characterization purpose, and they are actually molding very well. Then I also thanks to the organizers of this institute also. I got the third prize, so I'm so happy to hear. Thank you so much.
Aditya Salvi.
Hi everyone, I'm Aditya. I'm research scholar from KUSAT. First of all, I would like to thank all the organizers, Cipet, for conducting this conference and making it a grand success. And I would like to thank my guide, Professor Shailaja, for pushing me to participate in this conference. Thank you, everyone. And I also had a very good knowledge sharing session. We had a lot of talks. It was really a benefit, and thank you.
Sabir Ujampadi, please.
Hello, good evening to all. In this magnificent juncture, first of all, I will congratulate this Cipet institution and management to sponsor the wonderful today. It is a first experience in my life to post a presentation. I am actually a MSc student from NIT Calicut. Experience very good, especially the hospitality and also food also very good. I will eating more than 2 times in a lunch time. That's why some sessions, unfortunately, I am feeling some sleeping mood. Otherwise, I am enjoying very happy. Thank you.
I request our student, Ms. Reza, will tell about the conference. MS. Anita. So.
Today is the first experience. I experienced the poster presentation for the first time. I think it was a great opportunity to me to present it in international conference on biopolymers and green composite. We, the Cipetarians, conducted national conference until the last year, the 18 series. Now it renamed as international. There were so many lecture sections which were so informative, and also especially I am thanking to our HOD Bhuwana ma'am, our head Rajesh sir and Mansula ma'am. The work was started from 2 or 3 months before, and the result is here. The smiling faces in front are the result of the hard work. Thank you, one and all.
It's our pleasure to honor our distinguished guest with a small token of our gratitude. I request the Joint Director and Head, Cipet IPT Kochi, Dr. K. Rajesh, to honor Petronet LNG Limited, Kochi, with the memento. So thank you all for joining us today. I would like to express my sincere gratitude to our distinguished guests from Petronet LNG Limited, Kochi. I would like to thank all the speakers, award winners, organizers, faculty, staff and students, event management team for their invaluable contribution to the success of this conference. Thank you all. As we have come to the end, let's wind up this session. So I would like to request all the students of Cipet IPT Kochi to retain in the hall. So students, please stay here. Others, very thank you to all.